edited by Francis Rolt-Wheeler. The Science History of the Universe. Geology. This earth whereon man lives, by which he has his being and to which he returns, was to the ancients a riddle inexplicable. What mighty hand, they wondered, could have upreared the mountain peaks whose glittering summits pierced the very clouds? What fearsome figure lurked in the volcanic forge where subterranean rumblings seemed to tell of life within? What stupendous power could evoke from nowhere the shrieking tempest which destructively could mock the puny efforts of the world of men? Answers there must be, and the beginnings of geology are the cosmogonies devised by inexact observation and by fancy to propound a suitable reply. The earliest efforts at the interpretation of nature found their expression in the mythologies and cosmogonies of primitive peoples, which varied in type from country to country, according to the climate and other physical conditions under which they had their birth. Geological speculation may thus be said to be traceable in the mental conceptions of the remotest pre-scientific ages. Among these first gropings after truth, the Babylonian account of the creation holds an honored place, not only by reason of its completeness, but also because modern knowledge of it is gained from tablets of extreme antiquity, tablets which in themselves hold high rank in the records of historical importance. With the Babylonians, creation begins with chaos. The gods arose before heaven and earth had taken shape, while the tumultuous floods of oceans were still intermingled in the universal chaos. The gods chose Marduk to be their champion against Tiamat, the disturbing, chaotic ocean flood. Marduk armed himself with lightning flash and thunderbolt, and called the winds to his assistance. Marduk vanquished Tiamat and divided his corpse into two parts. From the one part he created the heavens, and from the other the earth and the sea. Marduk peopled the heavens with stars, the dwellings of the great gods. Then followed the creation of plants and animals, and finally the creation of the two first human beings out of clay. The Mosaic account of the creation far excels the Babylonian in its noble simplicity and in the strength and beauty of the language. In it the origin of the world, of the earth and its inhabitants, is represented as the work of a personal God. The Mosaic account, which is especially distinguishable among early cosmogonies by its recognition of the existence of light before the actual orb of the sun was visible, due to dense aqueous atmosphere, was incorporated in the Bible of the Christian Church, and, unfortunately, became invested with a scientific value which was mistakenly embroiled with the idea of verbal inspiration and infallibility. This retarded the development of geology for many centuries, inasmuch as theologians regarded the Mosaic account as a divine revelation and sought to suppress any investigations and writings of scientific interest which did not harmonize with their interpretation of it. The Greeks were less inclined than the Oriental nations to interweave the ideas of mythology, religion, and science. They viewed natural events from a more critical standpoint and treated them as subjects of philosophical speculation. In their early Ionian days, however, their understanding of the cosmogony was comparatively primitive, though heightened and made of interest by the imaginative force with which they peopled that portion of the earth's surface which was remote to them. Homer's contributions to ancient geography were large and curious, but cosmogonical ideas do not seem to have occurred to him. He presupposed that the earth was flat, and that the sun truly sank into the sea. Hesiod, in his Theogony, tells of the birth of the world, and time, Chronos. He describes the wars of the older and the Olympian gods, but he seems to have accepted the prevalent conception of the world as a flat disk with Greece at the center. These early cosmogonies, while differing greatly in style, elaboration of detail, and the degree to which they expressed the conceit of the author, had certain points in common. They all agree on successive alternate creations and destructions of the world. These speculations were closely interwoven with their religion, as were all the sciences, and the destructions were supposed to come when man's sin had become intolerable to the then ruling deity. The following creation included a race of men free from sin and taint of all kinds, who immediately proceeded to gradually degenerate. In the Institutes of Menu, the sacred volume of the Hindus, is the following verse: "There are creations also and destruction of worlds innumerable. The being supremely exalted performs all this with as much ease as if in sport, again and again, for the sake of conferring happiness." There are at the same time such puerile conceits and monstrous absurdities in this cosmogony, says Sir Charles Lyell in his famous Principles of Geology, that some may be disposed to impute to mere accident any slight approximation to truth or apparent coincidence between the Oriental dogmas and observed facts. This pretended revelation, however, was not purely an effort of the unassisted imagination, nor invented without regard to the opinions and observations of naturalists. There are introduced into it certain astronomical theories, evidently derived from observation and reasoning. Thus, for instance, it is declared that, at the North Pole, the year was divided into a long day and night, and that their long day was the northern, and their night the southern course of the sun. And to the inhabitants of the moon, it is said, one day is equal in length to 1 month of mortals. The Brahmins and Chinese corroborated this notion of successive creations and destructions, and also described a great flood. Plutarch tells us that this was the subject of one of the famous hymns of Orpheus. In his verses he sets a definite period for each cycle or life of a world. Orpheus assigned 120,000 years, while Cassandra took it to be 360,000 years. The Egyptian priests were aware not only that the soil beneath the plains of the Nile, but also that the hills bounding the Great Valley contained marine shells, and it could hardly have escaped the observation of Eastern philosophers that some soils were filled with fossil remains, since so many national works requiring extensive excavations were executed by Oriental monarchs in very remote eras. Thales of Miletus, the contemporary of Croesus and Cyrus, who considered that everything animate and inanimate was derived from water, added but little to early cosmology, save that his theory presupposed a condition of constant flux. His gifted scholar, Anaximander, circa 611 BC, arrived at a higher conception of nature. He depicted an infinite, all-pervading primeval substance, possessing an inherent power of movement from the first. The energy of this primeval matter determined heat and cold, and the mixture of these conditions gave origin to the development of fluid. The earth, the air, and a surrounding circle of fire differentiated from the fluid state. The stars sprang from fire and air. The earth rested in the center of the whole universe, and, under the influence of the sun, brought forth the animals which inhabit it. These, including human beings, were at first fish-like in form, consistent with the semi-fluid state of their environment. Xenophanes of Colophon, 614 BC, is reported by later writers to have observed the shell remains of pelagic mollusca on mountains in the middle of the land, impressions of laurel leaves in the rocks of Paros, as well as various evidences of the former presence of the sea on the ground of Malta, and to have attributed those appearances to periodic invasions of the sea, during which men and their dwellings must have been submerged. The historian Xanthus of Sardis, circa 500 BC, also drew attention to the occurrence of fossil shells in Armenia, Phrygia, and Lydia, far from the sea, and concluded that the localities where such remains occur had been formerly the bed of the ocean, and that the limits of the dry land in the ocean were constantly undergoing change. Herodotus, 484 BC, mentioned the presence of fossil shells of marine bivalves in the mountains of Egypt and near the oasis of Ammon. From this fact, as well as from the salt constitution of the rocks, Herodotus formed the opinion that Lower Egypt had been at one time covered by the sea, and that the material carried down by the Nile had been discharged into the sea basin between Thebes and Memphis and the current delta, and gradually filled it up. Herodotus could not form any definite opinion as to the cause of the Nile inundations, although he gave a careful report of the hypothesis then in favor. The gorge of Tempe, previously referred to, also came under the notice of the father of history. He says that the gorge of Tempe was caused by Poseidon is probable. At least one who attributes earthquakes and chasms to that god would say that this gorge was his work. It seemed to me to be quite evident that the mountains had there been torn asunder by an earthquake. Heraclitus, 535 BC, thought there was in the universe nothing stable, nothing lasting. Everything was in a state of constant change, like a stream in which new waves endlessly supplant the old. For him fire was the primeval force which unceasingly transformed itself, pervaded every portion of the universe, produced individuals and again destroyed them. Fire became the ocean, and that again earth, and the breath of life. The rising vapors burned in the air and formed the sun, which was renewed from day to day. Thus Heraclitus taught that although the universe always had been, and always would be, no portion of it had ever been quiescent, and that from time to time a new world was constructed out of the old. Pythagoras, who was born at Samos about the year 582 BC and afterward went to Crotona in Italy, is one of those eminent leaders of thought around whose name and teaching much that is mythical has gathered. His followers, suggests Carl von Zittel in his History of Geology and Paleontology, sought to explain natural phenomena chiefly by analogy with definite numerical relationships. An ordered universe depended, according to the Pythagoreans, upon the principle of numbers. According to Diogenes Laertius, Pythagoras imagined the universe in the form of a sphere. The earth was in the center, and bore the axis around which the firmament revolved. The principle of constant change taught by Pythagoras and Heraclitus was also a leading feature in the doctrines of Empedocles of Agrigentum, 492 to 432 BC. Empedocles supposed that everything had its origin in, and took its components from, four elements: earth, water, air, and fire. That these elements were without beginning and imperishable, but subject to never-ending change. From these elements the world at one time took shape, and it must at some future time be again dispersed. The course of the world's existence resolved itself into a history of recurring periods and phases. Geology owes one distinct step in advance to this philosopher. Whereas the Pythagoreans had conjectured the presence of a central fire in the universe, Empedocles taught that the earth's center was composed of molten material. Empedocles formed this opinion on the basis of his actual observation of the volcanic activities of Mount Etna. Tradition says that he met his death by falling into the crater of that volcano. Plato, 427 BC, in his Cosmology, is a follower partly of Heraclitus and partly of Anaxagoras. According to Plato, the universe is the production of divine intelligence and of the necessary development of nature. The form of the whole universe is spherical. In the center lies the earth as a motionless sphere. An interesting account is given in the Timaeus of a submerged Atlantic continent, Atlantis, on the other side of the Pillars of Hercules, Gibraltar. The idea of such a submerged continent has again and again received credence. In Plato's account, Atlantis was larger than Asia and Libya together. It had been inhabited 9,000 years before his time, and since its destruction by earthquakes and inundations, navigation in the Atlantic had been impossible owing to the fine mud and detritus left by the vanished land. Another of Plato's theories related to the origin of rivers. He attributed them to a common underground source. The work of Aristotle, 384 to 322 BC, marks the culminating point reached by the Greeks, both in the domain of speculative philosophy and in that of empirical observation. His treatises furnish an admirable exposition of the state of natural knowledge in his time. When he wrote, the geocentric view of the universe was still publicly accepted without question. But he had firmly grasped certain truths regarding the globe, which, though taught long ago by some of his predecessors, were not yet generally admitted. Accepting the common belief that the world consisted of 4 elements, he looked on these as arranged according to their relative densities. He said, "The water is spread as an envelope round the earth. In the same way above the water lies the sphere of air, while outside of all comes the sphere of fire." With regard to the surface of the planet, Aristotle had formed some sagacious conclusions, though mingled with certain of the misconceptions that were prevalent in his time. He remarks that earthquakes are due to a commingling of moist and dry within the earth. Of itself, the earth is dry, but from rain it acquires much internal humidity. Hence, when it is warmed by the sun and by the internal heat, wind is produced both within and without its mass. Wind, being the lightest and the most rapidly moving body, is the cause of motion in other bodies, and fire united with wind becomes flame which is endowed with great rapidity of motion. It is neither water nor earth which causes an earthquake. It is the wind, when what is vaporized outside returns into the interior. Aristotle regarded earthquakes and volcanic eruptions as closely related phenomena. He states that it had been observed in some places that an earthquake has continued until the wind from the interior has rushed out with violence to the surface, as had then recently happened at Heraclea on the Euxine, and before that event at Hiera, volcano, one of the Lipari Isles. At this latter locality the ground rose up with a great noise, and formed a hill that broke up, and allowed much wind to escape from the fissures, together with sparks and cinders which buried the whole of the neighboring town of the Liparans. The shock was even felt in some of the towns on the opposite mainland of Italy. Aristotle was further led to propose an explanation of the great heat that forms part of the volcanic phenomena. The fire within the earth can only be due to the air becoming inflamed by the shock, when it is violently separated into the minutest fragments. What takes place in the Lipari Isles affords an additional proof that the winds circulate underneath the earth. This idea that volcanic action was mainly due to the movement of wind imprisoned within the earth obtained wide credence in antiquity. Aeolus, the god of the winds, was believed to have his abode under the so-called Aeolian Isles, which are all of volcanic origin, and among which eruptions have been taking place since before the dawn of history. This tireless observer of antiquity also discusses the phenomena presented by rivers, and shows considerable acquaintance with the drainage system on the north side of the Mediterranean basin. He criticizes previously expressed opinions as to the source of rivers, particularly ridiculing the suggestion of Plato that all rivers flow directly from a vast mass of water under the earth. He appears to have held the opinion that just as the vaporized moisture in the atmosphere is condensed by cold and falls in drops of rain, so the moisture beneath the earth is similarly condensed and forms the sources of rivers. He states that the mountains, by their cold temperature, condense the atmospheric moisture and receive a vast quantity of water, so that they may be compared to an enormous suspended sponge. He shows by geographical illustrations, drawn from Asia and the Mediterranean basin, that the largest rivers descend from the loftiest ground, where the water accumulates in numberless channels. He admits the possible existence of underground lakes, from which rivers may issue, and alludes to the disappearance of some streams into subterranean channels. No writer of antiquity has expressed himself more philosophically than Aristotle regarding the past vicissitudes of the earth's surface. Having studied so carefully the operations of the various agents that are now modifying that surface, he recognized how greatly the aspect of the land must have been transformed in the course of ages. His remarks on this subject have a strikingly modern tone. He contemplates the alternations of land and sea and furnishes illustrations of them, much as a geologist of today might do. The sea now covers tracts that were formerly dry land, and land will one day reappear where we now find sea. These phenomena escape our notice because they take place successively during periods of time which, in comparison of our brief existence, are immensely protracted. Whole nations may disappear without any recollection being preserved of the great terrestrial changes which they have witnessed from beginning to end. The deluge of Deucalion, Aristotle suggests, affected Greece only, and principally the part called Hellas, and it arose from great inundations of rivers during a rainy winter. But such extraordinary winters, though after a certain period they return, do not always revisit the same places. He concludes with these remarkable words: "It is clear that, as time never stops and the universe is eternal, the Tanais and the Nile, like all other rivers, have not always flowed. The ground which they now water was once dry. But if rivers are born and perish, and if the same parts of the land are not always covered with water, the sea must undergo similar changes, abandoning some places and returning to others, so that the same regions do not remain always sea or always land, but all change their condition in the course of time." The great advances along certain lines of thought under the impetus of the Roman leadership infused a more realistic spirit into the investigations of all great workers in natural science, especially those interested in geology. Among the latter, the first place must be given to the historian and traveler Strabo, circa 63 B.C., whose geography, comprising 17 volumes, was written about the beginning of the reign of Tiberius. It contains not a few important facts in regard to the general effects of subterranean energy. Thus he cites a number of earthquakes by which chasms in the ground were formed. Thousands of people were destroyed and cities were swallowed up. He also gives some information regarding volcanic eruptions which had taken place within the historical period in the Mediterranean region. In his time, Mount Vesuvius was not only quiescent, but was not known ever to have been active. His quick eye, however, detected the true origin of the mountain. From the aspect of its summit he inferred that it was once a volcano, with live craters which had become extinct on the failure of the subterranean fuel, and he compared its slopes to the ground around Catania, where the ashes thrown out by Etna have formed an excellent soil for vines. He recognized the truly volcanic nature of the whole district from Etna to the Phlegraean fields, under which Typhon, as Pindar sang, lay crushed on his burning bed. In his excellent account of the ascent of Etna, Strabo compares the molten lava to a kind of black mud which, liquefied in the craters, is ejected from them and flows down the sides of the mountain, cooling and congealing in its descent, until it becomes a motionless dark rock like millstone. He also attributes earthquakes to the force of winds pent up within the earth. The doctrine that volcanoes are safety valves, therefore, which has been quoted as a modern idea, is prior in origin to the beginning of the present era. The oceanic islands far from any mainland have, according to Strabo, been thrown up by subterranean fires. In support of this view, Strabo cited the case of a volcanic eruption in the year 196 B.C., between Thera and Therasia. For 4 days flames rose from the ocean, and as these died down, it was observed that a new island had been formed, measuring 12 stadia in circumference. Strabo is therefore rightly regarded as the father of modern theories of mountain-making. He pointed out that Sicily in his time was less frequently disturbed by earthquakes than it had been in previous ages, before volcanic discharges were known in the district, and he correlated the comparative tranquility of the ground with the means of escape afforded for explosive underground vapors by the volcanic vents that had opened at Etna, in the Lipari Isles, and in Ischia. It speaks highly for Strabo's powers of observation that he should have recognized in Vesuvius a volcanic mountain, although it was then quiescent. Probably the most acute scientific observer of Roman times was Seneca, the physician of the Emperor Nero, 2 BC to 65 AD. Quite recently, Nering has placed the importance of the work of Seneca in its true light. The Quaestiones Naturales contain detailed communications about earthquakes, volcanoes, and the constructive and destructive agencies of water. Seneca explains earthquakes partly as a result of the expansion of gases accumulated in the earth, partly by the collapse of subterranean cavities. He appears to have been much impressed by the earthquake which did so much damage in Campania on February 5, 63 AD, for he refers to it again and again, and furnishes from the lips of eyewitnesses some interesting particulars regarding it. Thus he tells how a flock of 600 sheep were killed in the district of Pompeii, a fate which he attributes to the rise of pestilential vapors from the ground. He was informed by a most learned and serious friend that when he was in the bath, the tiles on the floor were separated from each other, and were then driven together again, while the water at one moment sank through the open joints of the pavement, and thereafter boiled up again and was jerked out. The philosopher's account is the earliest detailed description of an earthquake which has come down to us. Seneca regarded volcanic eruptions simply as an intensified form of the same series of phenomena, and volcanoes themselves as canals or vents between local subterrestrial reservoirs of molten material and the Earth's surface. In speaking of two outbreaks at Santorin, he remarks that an island rose out of the sea by protracted eruptions from below, and he notes that the internal fire is neither extinguished by the weight of the superincumbent depth of sea, nor prevented from rushing to a height of a couple of 100 paces above the water. He speaks of Etna having sometimes abounded in much fire and thrown out a great deal of burning sand, day being turned into night, to the terror of the population. On such occasions thunder and lightning are said to have abounded, but these came from the concourse of dry materials and not from ordinary clouds, of which probably there were none in such a raging heat of air. A shrewd anticipation of the modern distinction between ordinary atmospheric electric discharges and those evoked during the ejection of vapors, gases, dust, and stones from a volcanic orifice. The earth to him, however, was primitively a watery chaos, and it is more especially in his treatment of the action of water in dissolving and carrying away rock material, together with his explanation of the origin of sediments and deltas, that Seneca has shown his remarkable insight and sound judgment. His ideas on the origin of river water were no further advanced than those of his predecessors. He agreed with them in attributing all rivers to an inexhaustible internal source. Water, being one of the four elements, forms a fourth part of nature. Why then, he argued, should there be surprise if it can always keep pouring out? Just as in the human body there are veins which when ruptured send forth blood, so he thought in the earth there are veins of water which are found even in the driest places, at depths of 200 or 300 feet, and which when laid open issue in springs and rivers. The water at these depths, so far below the limits to which rain can moisten the earth, is not regarded by him of atmospheric origin, but living water, aqua viva. The learned historian, Pliny the Elder, 23 to 79 AD, has handed down to us a compendium that embraces the whole scientific knowledge of antiquity. By a tragic decree of fate, this untiring student and naturalist met his death while engaged in observing the grandest geological event of historical antiquity, the first outbreak of Vesuvius in the year 79 AD. He died in the open field, probably suffocated by the volcanic vapor and ash. His corpse was found unharmed 3 days later, when the darkened sky finally became clear. The younger Pliny's vivid description of the eruption of Mount Vesuvius and the accompanying earthquake is one of the most remarkable literary productions in the domain of geology.
In the ancient records, there is considerable doubt as to who were the earliest voyagers. Some authorities uphold the claims of the Greeks, some the Phoenicians, others the Egyptians, and still others the Chinese. Advocates of the Chinese claim base their conclusion on the location of the Ark of Noah. It is alleged that the Ark rested on one of the mountains of Armenia, and that Scythia was the first land to be inhabited, it being of high altitude and therefore the first to appear after the flood. But such an argument, based upon a local tradition, not upon scientific evidence, has little force. Mankind, at least that portion whose history is familiar, dwelt upon the borders of an inland Mediterranean sea. They had never heard of such an expanse of water as the Atlantic, and certainly had never seen it. The landlocked sheet which lay spread out at their feet was at all times full of mystery and often even of dread and secret misgiving. Those who ventured forth upon its bosom came home and told marvelous tales of the sights they had seen and the perils they had endured. Homer's heroes returned to Ithaca with the music of the sirens in their ears and the cruelties of the giants upon their lips. The Argonauts saw whirling rocks implanted in the sea to warn and repel the approaching navigator, and as if the mystery of the waters had tinged with fable even the dry land beyond it, they filled the Caucasus with wild stories of enchantresses, of bulls that breathed fire, and of a race of men that sprang like a ripened harvest from the prolific soil. If the ancients were ignorant of the shape of the earth, it was for the very reason they were ignorant of the ocean. Their geographers and philosophers, whose observations were confined to fragments of Europe, Asia, and Africa, alternately made the world a cylinder, a flat surface begirt by water, a drum, a boat, a disc. The legends that sprang from these confused and contradictory notions made the land a scene of marvels and the water an abode of terrors. It is now generally conceded that the date of the maritime enterprises which rendered the Phoenicians famous in antiquity must be fixed between the years 1700 and 1100 BC. The renowned city of Sidon was the center from which their expeditions were sent forth. About 1250 BC, their ships ventured cautiously beyond the Straits of Gibraltar and founded Cadiz upon a coast washed by the Atlantic. A little later, they founded establishments upon the western coast of Africa. Homer asserts that at the Trojan War, 1194 BC, the Phoenicians furnished the belligerents with many articles of luxury and convenience, and their ships brought gold to Solomon from Ophir in 1000 BC. About the period of Tyre's greatness, 600 BC, the Phoenicians, though under Egyptian commanders, appear to have succeeded in the circumnavigation of Africa. The enterprise was undertaken by order of Necho, king of Egypt, and is commented on by Herodotus as follows. Having in this manner consumed 2 years, in the third they passed the Pillars of Hercules and returned to Egypt. This story may be believed by others, but to me it appears incredible, for they affirm that when they sailed round Libya, they had the sun on their right hand. In the time of Herodotus, the Greeks were unacquainted with the phenomenon of a shadow falling to the south, one which the Phoenicians would naturally have witnessed had they actually passed the Cape of Good Hope, for the sun would have been on their right hand, or in the north, and would thus have projected shadows to the south. As this story was not one likely to have been invented in the time of Necho, suggests F.B. Goodrich in his Man Upon the Sea, from which some of these adventures are condensed, it is the strongest proof that could be adduced of the reality of the voyage. The first maritime adventure among the Greeks which lays any claim to authenticity, and the most celebrated in ancient times, is the expedition of the Argonauts to Colchis. The date of the expedition, if it took place at all, may be safely fixed at the year 1250 BC. A theory propounded by Sir Isaac Newton would connect it with the year 937, but this is regarded with less favor than the earlier date. Its alleged object was the Golden Fleece, but what this was can only be conjectured. Jason, the son of the king of Thessaly, being deprived of his inheritance and having resolved to seek his fortune by some remote and hazardous expedition, was induced to go in quest of the Golden Fleece in Colchis. He enlisted 50 men and employed Argus to build him a ship, which from him was called Argo, the adventurers being named Argonauts. The Argonauts started their voyage from Iolcos in Thessaly, and with a south wind sailed east by north. The narrative of the expedition is full of wonders. They landed at the island of Lemnos, where they found that the women had just murdered their husbands and fathers. The Argonauts supplied the place of the assassinated relatives, and Jason had 2 sons by one of the bereaved Lemnians. When the vessel arrived at the entrance to the Euxine, the narrow strait now called the Bosphorus, they built a temple and implored the protection of gods against the Symplegades, or whirling rocks, which guarded the passage. A seer named Phineus was consulted upon the probability of their sailing through unharmed. The rocks were imagined to float upon the waves, and when anything attempted to pass through, to seize and crush it. Phineus advised the loosing of a dove to judge from its fate of the destiny reserved for them. They did so, determined to push boldly on if the bird got through in safety. The pigeon escaped with the loss of some of its tail feathers. The Argo dashed onward and cleared the formidable rocks with the loss of a few of its stern ornaments. From this time forward, the legend adds, the Symplegades remained fixed and were no longer a terror to navigators. The Argonauts, after entering the Black Sea, sailed due east to the mouth of the river Phasis, now the Rione. Aeetes, the king, promised to give Jason the fleece upon certain conditions. These he was enabled to fulfill by the aid of Medea, a sorceress and daughter of Aeetes. They then fled together to Greece. This route, followed by the Argonauts upon their return, is differently given by the various poets who have told the story and the commentators who have illustrated it. The Greeks, like the Hebrews, were ignorant of the real figure of the earth. It is in Homer that is found the first written trace of the widely prevalent idea that the earth is a flat surface begirt on every side by the ocean. This was a natural belief in a region almost insular like Greece, where the visible horizon and an enveloping sea suggested the idea of a flat circle. Homer took the lead among the poetic geographers of Greece, and his authority gave to the subject a fanciful cast, the traces of which are not yet obliterated. Beneath the earth, he placed the fabled regions of Elysium and Tartarus. Above the whole rose the grand arch of the heavens, which were supposed to rest on the summits of the highest mountains. The sun, moon, and stars were believed to rise from the waves of the sea and to sink again beneath them on the return from the skies. Homer's distribution of the land was even more fantastic. Beyond the limits of Greece and the western coasts of Asia Minor, his knowledge was uncertain and obscure. He had heard vaguely of Thebes, the mighty capital of Egypt, and in his verse sang of its 100 gates and of the countless hosts it sent forth to battle. The Ethiopians, who lived beyond, were deemed to be the most remote dwellers upon the habitable earth. Toward the center of Africa were the stupendous ridges of the Atlas Mountains. Homer defined the highest peak and made it a giant, supporting upon his shoulders the outspreading canopy of the heavens. The narrow passage leading from the Mediterranean to the Atlantic, and now known as the Straits of Gibraltar, was believed to have been discovered by Hercules, and the mountains on either side, Gibraltar and Quetta, were, from him, called the Pillars of Hercules. Colchos, upon the Black Sea, was believed to be an ocean city, and here Greek fancy located the palace of the sea. It was here that the charioteer of the skies gave rest to his coursers during the night, and from whence in the morning he drove them forth again. Colchos, therefore, was Homer's eastern confine of the globe. On the north, Rhodope, or the Rhipaean Mountains, were supposed to enclose the Hyperborean limits of the world. Beyond them dwelt a fabled race, seated in the recesses of their valleys and sheltered from the contests of the elements. They were represented as exempt from all ills, physical and moral, from sickness, the changes of the seasons, and even from death. A race directly the converse of the ideal Hyperboreans were the Cimmerians, located at the south of the Sea of Azov, who are described by Homer as dwelling in perpetual darkness and never visited by the sun. He imagines the existence of numerous other nations who long continued to hold a place in ancient geography. The Cyclops, who had but one eye, were placed in Sicily. The Arimaspians, similarly affected, inhabited the frontiers of India. The Pygmies, or dwarves, who fought pitched battles with the cranes, were supposed to dwell in Africa, in India, and in fact, to occupy the whole southern border of the earth. In the time of Homer, says F.B. Goodrich again, all voyages in which the mariner lost sight of land were considered as fraught with the extremest peril. No navigator ever visited Africa or Sicily from choice, but only when driven there by tempest and typhoon, and then his woes usually terminated in shipwreck. A return was not merely a marvel, but a miracle. Homer made Sicily the principal scene of the lamentable adventures of Ulysses, and sufficient traces are furnished by the Odyssey of the distorted and exaggerated notions entertained in the poet's time of the character of places reached by a voyage at sea. The existence of monsters of frightful form and size, such as Polyphemus, of treacherous enchantresses such as Circe, of amiable goddesses like Calypso were prefigured by the early geographers and the location of their homes marked on the early charts. The radius of the territories described by Homer with any degree of precision was hardly 3 miles in length. Hesiod, who lived a century after Homer, thus states the scientific attainments of his time. The space between the heavens and the earth is exactly the same as that between the earth and Tartarus beneath it. A brazen anvil, if tossed from heaven, would fall during 9 days and 9 nights and would reach the earth upon the 10th day. Were it to continue its course toward the abode of darkness, it would be 9 days and 9 nights more in accomplishing the distance. Anaximander, 400 years after Homer, held that the earth, instead of being flat, was in the form of a cylinder, convex upon its upper surface. Its diameter was 3 times greater than its height, and its form was round, as if it had been shaped by a turner's lathe. The Oracle of Delphi was the center of his system. At a period which is no longer possible to settle with precision, but certainly anterior to 5th century BC, the Carthaginians, then in the height of their maritime and commercial prosperity, ordered a navigator by the name of Hanno to make a voyage beyond the Pillars of Hercules and to found cities along the western shore of Africa. He set sail with a fleet of 60 vessels, each of which was impelled by 50 oars. He carried with him 30,000 men and women with abundant supplies and provisions. The narrative, as given by Hanno himself, hardly fills 2 octavo pages. Volumes of commentaries have been written upon it by geographers and antiquaries. The most probable of the various hypotheses formed upon it is that Hanno's voyage extended to Sherbro Sound, a little south of Sierra Leone. The features of man and nature, as described by Hanno, are to be found in tropical Africa only.
While Hanno was thus exploring the western coast of Africa, another Carthaginian named Himilcon was sent by his countrymen to the north of Europe. From a very vague description of his voyage, given in a Latin poem entitled Ora Maritima, it is plain that he crossed the Bay of Biscay and found upon islands, as is asserted, but probably upon the mainland, a race of athletic people who went fearlessly to sea in barks made of skins sewed together. They crossed, in the space of 2 days, to a place called the Sacred Island, Ireland, which is not far from another island named Albion, England. No further details of this expedition have been preserved. A colony which had been established at Massilia, now Marseille, about 600 years before Christ by the Phoenicians was, in the year 340 BC, at the height of its commercial prosperity. The citizens, being desirous of extending their maritime relations, sent at this period upon an expedition to the north of Europe, through the Pillars of Hercules, a learned geographer and astronomer by the name of Pytheas. He started with a single ship. He passed the Pillars on the 16th day from Massilia, and on the 20th day he arrived at the Sacred Promontory, the extreme western point of Iberia or Spain. A temple to Hercules had been erected at this spot. The inhabitants of the promontory declared during the time of Pytheas, and indeed for 200 years afterwards, that as the sun plunged at evening into the sea, they heard a hissing like that of a red-hot body suddenly dropped into water. Following the coasts of Iberia and of Celtica, he came to the point of land now known as Finisterre in France, and the promontory Calbium. Turning east, he was surprised to find himself in a wide gulf, with Celtica on his right and an immense island on his left. The gulf was the British Channel, and the island the Albion that Himilcon had vaguely described some centuries before. It was at this point that Pytheas may be said to have begun his career, and the discovery of Great Britain may safely be attributed to him. He described the island as having the form of an isosceles triangle. 3 promontories formed the 3 right angles. Belerium, being now Land's End, Cantinum, Cape Pepernus, and Orcus, Duncansby Head. He found the inhabitants of the southern coast industrious and sociable, peaceable, honest, and sober. They raised wheat and worked rich mines of tin. As he sailed northward along the eastern coast, he noted that the days grew sensibly longer, and at Point Orcus 19 hours elapsed between the rising and setting of the sun. He sailed still northward, and 6 days after leaving Orcus, he came to an island or continent he knew not which he called Thule. As he found he could go no further to the north, he spoke of the spot as Ultima Thule, an expression which has passed into the figurative language of all modern nations as one denoting any remote point. Thule is generally considered to have been Shetland, although theories have been ardently advocated making it respectively Iceland, Sweden, and Jutland. The narrative of Pytheas, which has been thus far clear and reliable, assumes at this point a fabulous aspect. He declares that north of Thule there was neither earth, nor sea, nor air. A sort of dense concretion of all the elements occupied space and enveloped the world. He compared it to the thick, viscid animal substance called pulo marinus, a sort of mollusk or medusa. He said that this substance was the basis of the universe, and that in it earth, air, and sky hung, as it were, suspended. This illusion has been explained by the dreary spectacle of fogs, mists, rains, and tempests, which at this point of his voyage must have met the gaze of the daring navigator. It would have been difficult for any mind in those early ages to have been on its guard against the sinister impressions likely to result from the contemplation of a scene so appalling. It must be remembered that Pytheas was accustomed to the pure and transparent atmosphere, the dazzling sky, and the phosphorescent waters of the Mediterranean. It would have been astonishing if a man educated among the splendors of an almost tropical climate had not been oppressed by influences so gloomy. In the year 863, a Dane of Swedish origin, named Gardar, adventurously pushed off into the Northern Ocean, discovered the rock island whose appropriate name is Iceland. 11 years later, a navigator named Ingolf colonized the country. The colonists, many of whom belonged to the most esteemed families in the north, establishing a flourishing republic. In 877, a sailor named Gunnbjorn saw a mountainous coast far to the west, supposed to be now concealed or rendered inaccessible by the descent of Arctic ice. Eric the Red, who had been banished from Norway for murder and had settled in Iceland, was in his turn outlawed thence in 983. He sailed to the west and discovered a land which he called Greenland, because, as he said, people will be attracted hither if the land has a good name. He returned to Iceland, and in the year 985, a large number of ships, according to some authorities, 35, followed him to the new settlement and established themselves on its southwestern shore. In 986, Bjarni Herjolfsson Bjarni, son of Herjulf, in a voyage from Iceland to Greenland, was driven a long distance from the accustomed track. Various data furnished by this narrative in the original Iceland records have enabled geographers to determine the various coasts dimly seen by Bjarni, but upon which he did not land. They are supposed to have been those of Long Island, Rhode Island, Massachusetts, Nova Scotia, and Newfoundland. In the year 994, Leif Erikson, Leif the son of Eric the outlaw, bought Bjarni's ship and engaged 35 men to navigate it, as he intended to sail upon a voyage of discovery. He asked his father, Eric, to be the captain, but Eric declined, being, as he said, well stricken in years. They sailed away into the sea and discovered first the land which Bjarni had discovered last. They went ashore, saw no grass but plenty of icebergs and an abundance of flat stones. From the latter circumstance they named the place Helluland, Hellu signifying a flat stone. There can be no doubt that the spot thus named is the modern Newfoundland. They went on board again and proceeded on their way. They went ashore a second time, where the land was flat and covered with wood and white sand. This, said Leif, shall be named after its qualities and called Markland, woodland. Again embarking and sailing to the south, they reached Vinland, so called because of the wild grapes. This was probably the first recorded landing on the eastern shore of what is now the United States. Thus beginning from a fearful restraint of venturing upon the sea, the ancients first explored the Mediterranean, then, growing bolder, ventured beyond the Straits of Gibraltar and crept along the African coast and up toward the north of Europe. The perils of the open ocean were first dared by the Norsemen, to whom is due the honor of having first landed upon and truly discovered the continent of America, an honor furthered by Columbus, Amerigo Vespucci, and later navigators. The next great event was the doubling of the Cape of Good Hope by Bartholomew Diaz in 1486. He had indeed doubled it without knowing it, for having taken a wide sweep to sea after a long southern voyage, and on again making for the land, he could find none. Only on turning to a more northerly course did he see land 100 miles to the eastward of the formidable cape which never before had been passed. It avails little to tell the voyage of Columbus and his discovery of the West Indies in 1492, or the curious circumstances which led to the use of Amerigo's name. The Florentines were eager to have Amerigo's work recognized, and when a Frenchman of Saint-Dié republished his narrative, making an error in the date which made it seem that Amerigo preceded Columbus, Florence took it up, and Spain made no protest in favor of Columbus, whom she had allowed to die in penury and disgrace. Sebastian Cabot, a true navigator, discovered Hudson's Bay in 1518. Vasco da Gama, in 1497, followed the track of Bartholomew Diaz and reached India by doubling the Cape of Good Hope. It did not occur to him, however, to continue his journey, and in returning to Portugal he retraced his path. In 1519, Ferdinand Magellan found the straits between the Atlantic and the Pacific, which are known as the Magellan Straits to this day. With the Atlantic and the Pacific thus laid open, navigators followed close upon each other's heels, and scarce a year passed that did not see some portion of ocean crossed or some new point of coastline charted. The circumnavigation of the world speedily became a matter of no comment, and the once appalling ocean became as familiar a highway as a city street. Exploration, in the true sense of the word, thereafter was mainly devoted to land expeditions, which were of great physiographical benefit when the large continents were first crossed. Thus the Spaniards in the south of North America and in Mexico and Peru added vastly to the world's knowledge. Likewise in Africa, the names of such men as Mungo Park, Speke, Grant, Livingston, and Stanley are to be remembered, and in Australia, the first man to cross the continent, John McDowell Stuart, in 1862. But modern exploration has been devoted mainly to polar search, and now that late in the summer of 1909 the announcement is made that the North Pole has been reached, and Lieutenant Peary has brought back the records of his valuable trip, it may be well to point out the northward progress of successor polar expeditions. In the reign of Henry VIII, Dr. Robert Thorne declared that if he had faculty to his will, the first thing he would understand, even to attempt, would be if our seas northward are navigable to the pole or no. Accordingly, 2 fair ships set forth on May 1527. One was wrecked off Newfoundland, the other does not seem to have returned. A similar fate met Sir Hugh Willoughby, who left in 1563, who lost one vessel on the Muscovy coast, and who, with all his companions, perished miserably in Lapland. Martin Frobisher, the great navigator, reached latitude 63 degrees as his most northerly point, and in 1585 Captain John Davis reached latitude 80 degrees, and on a third voyage pushed even farther, reaching a point he named Cape Sanderson. Henry Hudson, the explorer of the Hudson River, whose tricentennial discovery of the Hudson River, coupled with the celebration of Robert Fulton in September and October 1909, brought representatives to New York from all civilized countries to do them honor, was also one of the furthest north men. In 1607, in an attempt to reach the Pacific by the long-sought Northwest Passage, he attained the latitude of 81 degrees. The last of the early explorers was William Baffin, who, with Robert Bylot, in 1615 sailed around Greenland, giving his name to Baffin's Bay. The 19th century was remarkable for strenuous endeavor. In 1818, Sir John Parry overtopped all earlier efforts and reached as far north as 82 degrees. The hopes of the world, however, rose high when, in the spring of 1845, Sir John Franklin sailed for polar waters. The silence of the Arctic winter fell over the expedition, and rescue parties later found the bodies of Franklin and his men, who had died in forwarding their quest. Scarcely less tragic was the loss of the American De Long expedition in 1881. The great figure in polar work during the 19th century unquestionably was Commander Robert E. Peary, who in 1886 first attacked the Arctic terrors. His first expedition was to Greenland, and from that time he has been almost constantly in the Arctic region under the auspices of several learned and scientific societies. But in spite of his indefatigable efforts, a Norwegian, Dr. Nansen, carried off the banner for the highest point reached in the 19th century. He built a vessel to withstand ice pressure and trusted that the currents would carry him to the pole. He reached latitude 86 degrees 14 minutes and brought back a mass of extremely useful scientific information. An attempt to reach the North Pole by balloon was made by Professor Andre in 1897. The expedition was never heard from, for aerial navigation had not then made the wonderful advances compassed in the first decade of the 20th century. The last year of the century saw the northern mark again pushed forward. An expedition under the command of the Duke of Abruzzi sailed in 1899. Dr. Nansen's furthest point was passed, and a dash was being made for the pole when the leader of the expedition was severely frostbitten, and he transferred the command to Captain Cagney, who reached the point of latitude 86 degrees 34 minutes. Two important Arctic expeditions may be mentioned. The Ziegler expedition commanded by Anthony Fiala in 1903 and that of Captain Amundsen. Fiala spent 2 years above the 81st parallel and added greatly to polar knowledge, and Amundsen achieved the long-sought feat of the Northwest Passage in the little ship Goa. Early in September 1909, Dr. Frederick A. Cook cabled news that he had reached the North Pole. The unexpectedness of the report and the fact that the traveler was known to be far less elaborately equipped than most polar explorers caused the news at first to be received with a great deal of hesitation in scientific circles. Far other was the reception accorded the news received a week later that Lieutenant Peary had reached the pole, touching the coveted spot on April 6, 1909. The priority of Dr. Cook's claim, duly substantiated, would be indisputable, but would be of less scientific value by reason of the less adequate facilities he possessed for meteorological, geographical, and astronomical observations. Whether first by Dr. Cook or by Lieutenant Peary, two facts stand out clearly high above all the rest: that the North Pole has been reached, and that the first flag to fly there was the Stars and Stripes. But one quest remains for the explorer, the South Pole, and the year 1909 is as memorable in Antarctic as in Arctic discovery. In one of the finest ice journeys ever made, Lieutenant E. H. Shackleton of the British Navy planted the Union Jack at 88 degrees 23 minutes south, or but 111 miles from the South Pole, the flag being hoisted on January 9, 1909. Thus, in the same year, an American and an Englishman stood almost at the two poles of the earth, practically completing the exploration of the world.
The decline of the Roman Empire, while, as has been seen, it did not prevent the growth of the adventurous spirit, was a sore blow to scientific study. Life was too insecure to permit leisure, and the governmental situation was uncertain in all countries. From the middle of the 8th century onward, for some 500 years, the Arabs alone kept alive the feeble flame of interest and researches into the secrets of nature. With great labor and at large cost, they procured as much as they could obtain of the literature of ancient Greece and Rome, and studied and translated into their own language the works of the best writers in philosophy, medicine, mathematics, and astronomy. They were thus able to some extent to enlarge the domain of these subjects. But geology was a subject to which the students of the caliphates never took kindly. Albert the Great, 1205 through 1280 A.D., the most learned man of his time, mentions that a branch of a tree was found on which was a bird's nest containing birds, the whole being solid stone. He accounted for this strange phenomenon by the vis formativa of Aristotle, an occult force which, according to the prevalent notions of the time, was capable of forming most of the extraordinary objects discovered in the earth. One of the keenest observers, whose opinions have been recorded, was the illustrious painter, architect, sculptor, and engineer Leonardo da Vinci, 1452 through 1519. His attention having been aroused by the abundantly fossiliferous nature of some of the rocks in northern Italy, in which canals were cut, he concluded that the shells contained in these rocks had once been living on the sea floor and had been buried in the silt washed off the neighboring land. He ridiculed the notion that they could have been produced by the influence of the stars, and he asked where such an influence could be shown to be at work now. But he pointed out that besides the shells, there were at various heights terraces of gravel composed of materials that had evidently been rounded and accumulated by moving water. The Neapolitan Alessandro degli Alessandri, 1461 through 1523, mentions petrified conchiglia in the Calabrian mountains, and ascribes their presence to an inundation of the continent by the ocean, caused by some exceptional catastrophe or by a change in the axis of rotation of the earth. Fracastoro, in the year 1517, gave clear expression to his convictions about fossils, which were in accordance with those of Leonardo da Vinci. During the building of the citadel of San Felice in Verona, the workers found fossil mussels in the rocks and laid them before Fracastoro, begging him to explain the marvel. Fracastoro repudiated the doctrine of a vis plastica in the earth as impossible, and just as little did he give credence to the view that explained fossils as creatures left by the Great Flood. The flood, he said, was of short duration, and in the nature of things, it would have left not marine but freshwater mussels behind. Further, on the assumption that the mussels had been carried from the ocean to the land by the flood, their remains would have been scattered over the surface of the land, and would not have been buried deep in the earth where the quarrymen had found them. There was left, he continued, only one possible explanation, that the fossils were the remains of animals which had once lived in the localities where their remains are now embedded. Far more illustrious than the majority of his contemporaries in science was George Bauer, better known by his nom de plume of Agricola. Werner calls him the father of metallurgy and the originator of the critical study of minerals. Agricola's observations on crystalline form, cleavage, hardness, weight, color, luster, etc., have served as a model for all subsequent descriptions of minerals. On the other hand, Agricola's remarks about fossils are of much less value. He had devoted little attention to the fossil remains of animals and plants, and he unfortunately united under the name fossilia both minerals and petrified organisms. This use of the term fossils was perpetuated for 2 centuries in the literature, having been more especially adopted by the famous Wernerian school. Giulio Cardano, 1552, pointed to fossil shells as certain evidence that the sea once covered the sites of the hills. His contemporary, Mattioli, on the other hand, supported the old figment of the materia pinguis, though admitting that porous bodies, such as the bones and shells, so abundant in Italy, might be turned into stone by being permeated by a petrifying juice. He is said to have been the first writer who published a reference to the fossil fishes of Monte Bolca. The skillful anatomist, Gabriele Falloppio, 1562, when he met with bones of elephants, teeth of sharks, shells, and other fossils, refused to admit them to be anything but earthy concretions, because he deemed that to be a simpler solution of the problem than to suppose that the waters of the deluge could have reached as far as Italy. Olivi of Cremona, in 1584, writes of the fossil conchiglia of the famous Calceolarian collection in Verona as mere sports of nature. Michel Mercati prepared good illustrations of fossil bivalves, ammonites, and nummelites in the museum of Pope Sixtus V, and these were published between 1717 and 1719 in the Metalloteca Vaticana by Lancisi, the physician of Pope Clement XI. Mercati names the fossils according to Pliny, and after long discussion comes to the conclusion that they took origin under the influence of the stars. It is astonishing to find how tenaciously, until the middle of the 18th century, so many authors clung to such absurd ideas, even although the fossils were being made known by means of good illustrations to an ever-increasing number of observers. The works of Aldrovandi, Athanasius, Kircher the Jesuit, Sebastian Kirkmeyer, Alberti, Balbini, Geyer, Hartley, and many others in the 17th century contained good figures and extended the knowledge of the fossils found in various European localities. The fossils were, however, treated usually as mineral curiosities, or as illusions of nature, sometimes as forms called forth in the earth by vis plastica, or some other force, sometimes compared with living mussels, snails, sea urchins, and plants, and named accordingly. In the crowd of writers who took part in the long geological controversy, by far the most illustrious was Nicolas Steno, 1631 through 1687. Born and educated in Copenhagen, he traveled to Leyden, Paris, and Austria, and eventually settled in Florence as physician to the Grand Duke Ferdinand II. While here, he renounced Protestantism for Romanism. Shortly after this, he was persuaded to return to his native land, where his religious beliefs caused him so much unpleasantness that he went back to Florence and was made a bishop. He wrote much on theology and anatomy, but it is his writings in geology which won for him the high position among scientists accorded him by posterity. In 1669, there appeared in Florence his treatise De solido intra soliam naturaliter contento, which must be regarded as one of the landmarks in the history of geological investigation. In this, he says that the strata of the earth are such as would be laid down in the form of sediment from turbid water. The objects enclosed in them, which in every respect resemble plants and animals, were produced exactly in the same way as living plants and animals are produced now. Where any bed encloses either fragments of another, and therefore older bed, or the remains of plants or animals, it cannot be as old as the time of the creation. If any marine production is found in any of these strata, It proves that at one time the sea has been present there, while, if the enclosed remains are those terrestrial plants or animals, the sediment must have been laid down on land by some river or torrent. Steno's treatise stands out far above all the writings of his own or of previous generations in respect to the minuteness and accuracy of his observations of nature, and the originality and truth of most of the deductions which he drew from them. He was the first, clearly, to perceive that the strata of the Earth's crust contain the records of a chronological sequence of events, and that the history of the Earth must be deciphered from them. He laid down for the first time some of the fundamental principles of stratigraphy. Another notable Italian writer, Anton Lazzaro Moro, appeared in the first half of the 18th century. A large part of Moro's work is devoted to a destructive criticism of the cosmogonies of two of his contemporaries. He discussed the possibility of explaining the position of fossil shells in the mountains by reference to the Noachian deluge, and dismissed this supposition as untenable. After giving an account of the uprise of a new volcanic island in the Greek archipelago in the year 1707, of the appearance of Monte Nuovo near Naples in 1538, and of the recorded eruptions of Vesuvius and Etna, and starting with the proposition that the fossil shells are really productions of the sea, he proceeds to unfold his theory that the position of these shells and the origin of the rocks that enclose them are to be assigned to the operation of volcanic action. In the beginning, he says, the globe was completely covered with water, which was then fresh and perhaps not more than 175 perches in depth. No prominences diversified the smooth, stony surface of the globe, which underlay the water. On the third day of creation, however, when it pleased the Almighty to reveal the solid earth, vast subterranean fires were kindled, whereby the surface of stone was broken up, and huge masses of it began to appear above the water, so as to form the land and mountains. These disrupted masses, while rising, or after they had risen, and in some cases even before they appeared above the water, were rent open by the violence of the subterranean fires, and they discharged from their orifices vast quantities of material, such as earth, sand, clay, stones, both solid and liquid, metals, sulfur, salts, bitumen, and every kind of mineral substance. Part of this material flowed in river-like streams down the sides of the mountains into the water below. Part fell in showers from the air, into which the ejected detritus had been hurled by the impetuosity of the fire. The saline and bituminous ingredients now began to give to the water the salt and bitter taste which the sea has retained ever since, while the other insoluble substances formed a new bottom above the original stony surface. As yet, no plants or animals existed, but while the water continued to grow more saline, plants began at last to appear, both in the sea and on land. Animals too entered upon the scene, first in the sea, living in the soft sand and among the debris cast out by the mountains, and seldom wandering far from their native places. The dry land became covered with verdure and gave birth to terrestrial animals, finally followed by the advent of man, who then took his place as an inhabitant of this first and most ancient land surface. In course of time, the same sequence of events continuing, new mountains emerged from the bosom of the earth, and like their predecessors, vomited forth fresh materials, which were once more spread out over the floor of the sea and the surface of the land. The strata that were thus deposited in the sea would contain marine productions, while those formed on the land would preserve terrestrial remains, including articles in metal, marble, or carved wood, as relics of a human population. Some of these land surfaces, remaining long exposed to the open air, were covered with new strata, which, when they differed in composition from those buried below them, would produce plants and animals distinct from any of those which had previously existed on the same sites. And since the newer strata were not all laid down universally and at the same time, but successively during the course of centuries and at different seasons of the year, seeds and fruits in mature and immature condition would be entombed, as may be illustrated by many examples that have actually been obtained from excavations in which, at different levels, old soils represent inhabited and cultivated surfaces of land. Morrow had to take care that his cosmogony did not contradict, but only supplemented the orthodox reading of the first chapter of the book of Genesis. The following semi-tragic, semi-comic event was a decided setback to the prevailing belief in the theory of the direct origin of fossils, that is, that they were imitations produced in the rocks by some unknown causes. Johannes Bartholomew Berenger, a professor in the University of Würzburg, published in 1726 a paleontological work entitled Lithographia Virceborgensis. In it, a number of true fossils were illustrated, belonging to the Muschelkalk or Middle Trias of North Bavaria, and beside these were more or less remarkable forms, even sun, moon, stars, and Hebraic letters, said to be fossils, and described and illustrated as such by the professor. As a matter of fact, his students, who no longer believed in the Greek myth of self-generation in the rocks, had placed artificially concocted forms in the earth, and during excursions had unveiled the credulous professor to those particular spots and discovered them. But when at last Berenger's own name was found apparently in fossil form in the rocks, the mystery was revealed to the unfortunate professor. He tried to buy up and destroy his published work, but in 1767 a new edition of the work was published, and the book is preserved as a scientific curiosity. Many of the false fossils, Lichtenstein, may be seen in the mineral collections at Bamberg, and there are also specimens in the university collections of Würzburg, Munich, and other places. Palissy, a French writer on the origin of springs from rainwater and of other scientific works, undertook in 1580 to combat the notions of many of his contemporaries in Italy that petrified shells had all been deposited by the universal deluge. He was the first, said Fontenelle, when in the French Academy he pronounced his eulogy nearly a century and a half later, quote, "Who dared assert in Paris that fossil remains of testacea and fish had once belonged to marine animals?" Unquote. Palissy's ideas were violently attacked by his compatriots, and he was denounced as a heretic in his philosophical and scientific writings, just as he was a Huguenot and a heretic in his religion. Next among the notable workers was the versatile B.F. Guettard, who traveled through France, England, Germany, and Poland, and whose great desire it was to reproduce his scientific observations on maps. Guettard's mineralogical map of France and England gives so much accurate information regarding the local occurrence of rocks and minerals, and the position of mines, quarries, fossil localities, mineral springs, hot springs, and coal, that it can still be used with advantage. The map is not colored. Guettard described the processes of land denudation effected by the solvent and destructive agency of rain and rivers, and by the abrasion of the waves. This is probably the first paper in which a systematic account of denudation is given in its relation to changes in the configuration of the Earth's surface. The most brilliant of Guettard's achievements was his discovery of the volcanic rocks in the Auvergne region. Nicolas Desmarest, a French professor, opposed Guettard's erroneous conception that the Auvergne basalt pillars had crystallized from a watery fluid, and demonstrated the resemblance of the Auvergne basalt to certain recent lavas. He was supported by F. de Saint-Fond, 1742 to 1819, professor in the Museum of Natural History in Paris, who brought forward conclusive evidences of the igneous origin of basalt. Toward the close of the 18th century, the idea of distinguishing the mineral masses on our globe into separate groups and studying their relations began to be generally diffused. Of these investigators, Pallas and Saussure were among the most celebrated, whose labors contributed to this end. After an attentive examination of the two great mountain chains of Siberia, Pallas announced the result that the granitic rocks were in the middle, the schistose at their sides, and the limestones again on the outside of these, and this he conceived would prove a general law in the formation of all chains composed chiefly of primary rocks. In his Travels in Russia in 1793 and 1794, he made many geological observations on the recent strata near the Volga and the Caspian, and adduced proofs of the greater extent of the latter sea at no distant era in the Earth's history. His memoir on the fossil bones of Siberia attracted attention to some of the most remarkable phenomena of geology. He stated that he had found a rhinoceros entire in the frozen soil, with its skin and flesh. An elephant found afterward in a mass of ice on the shore of the North Sea removed all doubt as to the accuracy of such a remarkable discovery. The subjects relating to natural history, which engaged the attention of Pallas, were too multifarious to admit of his devoting a large share of his labors exclusively to geology. Saussure, on the other hand, employed the chief portion of his time in studying the structure of the Alps and Jura, and he provided valuable data for those who followed him. Querini, in 1676, contended that the diluvian waters could not have conveyed heavy bodies to the summit of mountains, since the agitation of the sea never extended to great depths, and still less could the testacea, as some pretended, have lived in these diluvian waters, for, quote, the duration of the flood was brief, and the heavy rains must have destroyed the saltness of the sea, end quote. He was the first writer who ventured to maintain that the universality of the Noachian cataclysm ought not to be insisted upon. The great mathematician Leibniz published his Protogaia in 1680. He imagined this planet to have been originally a burning, luminous mass, which, ever since its creation, has been undergoing refrigeration. When the outer crust had cooled down sufficiently to allow the vapors to be condensed, they fell and formed a universal ocean, covering the loftiest mountains and investing the whole globe. The crust, as it consolidated from a state of fusion, assumed a vesicular and cavernous structure, and, being rent in some places, allowed the water to rush into the subterranean hollows, whereby the level of the primeval ocean was lowered. The breaking in of these vast caverns is supposed to have given rise to the dislocated and deranged position of the strata, which Steno had described, and the same disruptions communicated violent movements to the incumbent waters, whence great inundations ensued. The waters, after they had been thus agitated, deposited their sedimentary matter during intervals of quiescence, and hence the various stony and earthy strata. We may recognize, therefore, says Leibniz, a double origin of primitive masses, the one by refrigeration from igneous fusion, the other by concretion from aqueous solution. By the repetition of similar causes, the disruption of the crust and consequent floods, alternations of new strata were produced, until at length these causes were reduced to a condition of quiescent equilibrium, and a more permanent state of things was established. Robert Hooke, 1635 through 1703, was one of the most brilliant, ingenious, and versatile intellects of the 17th century. Among the many subjects to which he directed his attention and on which his remarkable powers of acute observation and sagacious reflection enabled him to cast light, some of the more important problems of geology must be numbered. In 1705 appeared the Posthumous Works of Robert Hooke, M.D., which contained a discourse on earthquakes. However trivial a thing, he says, a rotten shell may appear to some, yet these monuments of nature are more certain tokens of antiquity than coins or medals, since the best of those may be counterfeited or made by art and design, as may also books, manuscripts, and inscriptions, as all the learned are now sufficiently satisfied, has often been actually practiced. And though it must be granted that it is very difficult to read them, the records of nature, and to raise a chronology out of them, and to state the intervals of the time wherein such catastrophes and mutations have happened, yet it is not impossible. He accounts for the shells found in mountains by saying that such things may be due to the action of earthquakes, quote, which have turned plains into mountains, and mountains into plains, seas into land, and land into seas, made rivers where there were none before, and swallowed up others that formerly were, and which, since the creation of the world, have brought many great changes on the superficial parts of the earth, and have been the instruments of placing shells, bones, plants, fishes, and the like in those places where, with much astonishment, we find them. End quote. About 1690 appeared Thomas Burnet's Theory of the Earth. The title is characteristic of the age, the sacred Theory of the Earth, containing an account of the original of the earth and of all the general changes which it had already undergone, or is to undergo, till the consummation of all things. Even Milton had scarcely ventured in his poem to indulge his imagination so freely in painting scenes of the creation and deluge, paradise and chaos. He explained why the primeval earth enjoyed a perpetual spring before the flood, showed how the crust of the globe was fissured by the sun's rays so that it burst, and thus the diluvial waters were let loose from a supposed central abyss. Not satisfied with these themes, he derived from the books of the inspired writers, and even from heathen authorities, prophetic views of the future revolutions of the globe, gave a most terrific description of the general conflagration, and proved that a new heaven and a new earth will rise out of a second chaos, after which will follow the blessed millennium. The celebrated naturalist John Ray, 1627 through 1705, participated in the same desire to explain geological phenomena by reference to causes less hypothetical than those usually resorted to. In his essay on Chaos and Creation, he proposed a system agreeing in its outline and in many of its details with that of Hooke, but his knowledge of natural history enabled him to elucidate the subject with various original observations. Earthquakes, he suggested, might have been the second causes employed at the creation in separating the land from the waters, and in gathering the waters together into one place. He mentions, like Hooke, the earthquake of 1646, which had violently shaken the Andes for some hundreds of leagues, and made many alterations therein. In assigning a cause for the general deluge, he preferred a change in the Earth's center of gravity to the introduction of earthquakes. Some unknown cause, he said, might have forced the subterranean waters outward, as was perhaps indicated by, quote, the breaking up of the fountains of the great deep, end quote. Among the contemporaries of Hooke and Ray, John Woodward, 1665 through 1722, a professor of medicine, had acquired the most extensive information respecting the geological structure of the crust of the earth. He had examined many parts of the British strata with minute attention, and his systematic collection of specimens, bequeathed to the University of Cambridge and still preserved there as arranged by him, shows how far he had advanced in ascertaining the order of superposition. He conceived, quote, the whole terrestrial globe to have been taken to pieces and dissolved at the flood, and the strata to have settled down from this promiscuous mass as any earthy sediments from a fluid, end quote. In corroboration of these views, he insisted upon the fact that, quote, marine bodies are lodged in the strata according to the order of their gravity, the heavier shells in stone, the lighter in chalk, and so of the rest, end quote. Ray immediately exposed the unfounded nature of this assertion, remarking truly that fossil bodies are often mingled heavy with light in the same stratum, and he even went so far as to say that Woodward, quote, must have invented the phenomena for the sake of confirming his bold and strange hypothesis, end quote, a strong expression from the pen of a contemporary. It is interesting to turn from the physico-theological disputes of the Germans and English to follow the steps of the Italians and witness the real progress they were making at this time, the while that they refuted and ridiculed the theories of Burnet, Woodward, and Ray. An illustrious observer in the geological domain appeared in Italy when Steno, in his 25th year, was rapidly rising into fame as an anatomist. Antonio Vallisneri, 1661 through 1730, became professor of medicine in Padua, In the course of his journeys, he had opportunities of seeing much of the geology of his native country, and of forming a clearer conception of the fossiliferous formations of the great central mountain chain than any one had done before him. His works were rich in original observations. He attempted the first general sketch of the marine deposits of Italy, their geographical extents, and most characteristic organic remains. In his treatise on the origin of springs, he explained their dependence on the order and often on the dislocations of the strata, and reasoned philosophically against the opinions of those who regarded the disordered state of the earth's crust as exhibiting signs of the wrath of God for the sins of man. Although reluctant to generalize on the rich materials accumulated in his travels, Vallisneri had been so much struck with the remarkable continuity of the more recent marine strata from one end of Italy to the other, that he came to the conclusion that the ocean formerly extended over the whole earth, and after abiding there for a long time, had gradually subsided. The last, and not the least, of the cosmogonists was G. L. Leclerc de Buffon, 1707 through 1788, one of the greatest pioneers who figured so conspicuously in the history of France. At first interested in physics and mathematics, he gradually broadened his field of observation, taking in the whole realm of nature. He adopted the theory of an original volcanic nucleus, together with the universal ocean of Leibniz. By this aqueous envelope, the highest mountains were once covered. Marine currents then acted violently and formed horizontal strata by washing away solid matter in some parts and depositing it in others. They also excavated deep submarine valleys. The level of the ocean was then depressed by the entrance of a part of its waters into subterranean caverns, and thus some land was left dry. Soon after the publication of his Natural History, in which was included his Theory of the Earth, he received an official letter, dated January 1751, from the Sorbonne, or Faculty of Theology in Paris, informing him that 14 propositions in his works, quote, were reprehensible and contrary to the creed of the Church, end quote. The first of these obnoxious passages, and the only one relating to geology, was as follows, quote, the waters of the sea have produced the mountains and valleys of the land. The waters of the heavens, reducing all to a level, will at last deliver the whole land over to the sea, and the sea, successively prevailing over the land, will leave dry new continents, like those which we inhabit. End quote. Buffon was invited by the college in courteous terms to send in an explanation, or rather a recantation of his unorthodox opinions. To this he submitted, and a general assembly of the faculty, having approved of his declaration, he was required to publish it in his next work. The grand principle which Buffon was called upon to renounce was simply this, quote, that the present mountains and valleys of the earth were due to secondary causes, and that the same causes will in time destroy all the continents, hills, and valleys, and reproduce others like them. End quote. Now, whatever may be the defects of many of his views, it is no longer controverted that the present continents are of secondary origin. The doctrine is as firmly established as the earth's rotation on its axis, and that the land now elevated above the level of the sea will not endure forever is an opinion which gains ground daily in proportion as experience of the changes now in progress is enlarged. Taglioni, 1751, opposed Buffon in his theory regarding the origin of valleys. Buffon attributed them principally to submarine currents, while the Tuscan naturalist labored to show that both the larger and smaller valleys of the Apennines were excavated by rivers and floods, caused by the bursting of the barriers of lakes after the retreat of the ocean. He was a contemporary of Werner, who ushers in a new era.
With the freeing of geological study from the trammels of ecclesiasticism arose a rejuvenating significance in the determined spirit that prevailed to discountenance speculation and to seek untiringly in the field and the laboratories after new observations, new truths. Interest was directed, in the first place, toward the investigation and description of the accessible parts of the earth's crust. The composition and arrangement of the strata were studied with enthusiasm. The bolder inquirers ventured into wild recesses of mountain chains and climbed snowy peaks, whose difficulties had hitherto been thought insurmountable. Travelers explored the uninhabited plains of Siberia, the remote mountain ranges of Asia and America, and brought home with them new scientific material and observations of the highest importance for comparative research. Together with this arose the realization of the value of understanding the works of the geologists of the past. For the first time, a history of geology became possible. As Sir Archibald Geikie said, "In no department of natural knowledge is the adoption of this historical method more necessary and useful than it is in geology. The subjects with which that branch of science deals are, for the most part, not susceptible of mathematical treatment. The conclusions formed in regard to them, being often necessarily incapable of rigid demonstration, must rest on a balance of probabilities. There is thus room for some difference of opinion both as to facts and the interpretation of them. Deductions and inferences which are generally accepted in one age may be rejected in the next. This element of uncertainty has tended to encourage speculation. Moreover, the subjects of investigation are themselves often calculated powerfully to excite the imagination. Quote, "The story of this earth since it became a habitable globe, the evolution of its continents, the birth and degradation of its mountains, the marvelous procession of plants and animals which, since the beginning of time, has passed over its surface, these and 1,000 cognate themes with which geology deals have attracted numbers of readers and workers to its pale, have kindled much general interest and awakened not a little enthusiasm, but the records from which the chronicle of events must be compiled are sadly deficient and fragmentary. The deductions which they suggest ought frequently to be held in suspense from want of evidence, yet with a certain class of minds fancy comes in to supply the place of facts that fail, and thus geology has been encumbered with many hypotheses and theories which, plausible as they might seem at the time of their promulgation, have one by one been dissipated before the advance of fuller and more accurate knowledge. Yet before their overthrow it may often be hard to separate the actual ascertained core of fact within them from the mass of erroneous interpretation and unfounded inference that forms most of their substance." End quote. The modern period begins with the advent of a man who bulks far more largely in the history of geology than any of those with whom up to the present we have been concerned. A man who wielded an enormous authority over the mineralogy and geology of his day. Through the loyal devotion of his pupils, he was elevated even in his lifetime to the position of a kind of scientific pope, whose decisions were final on any subject regarding which he chose to pronounce them. During the last quarter of the 18th century, by far the most notable figure in the ranks of those who cultivated the study of minerals and rocks was unquestionably Abraham Gottlob Werner, 1749 to 1817. The vast influence which this man wielded arose mainly from his personal gifts and character, and especially from the overmastering power he had of impressing his opinions upon the conviction of his hearers. Werner was born in 1749 at Wehran, in Upper Lapatia, of a family which had long been interested in the iron industry. Thus, from infancy, he was in intimate contact with people interested in topics akin to geology. He early became interested in mineralogy, and his tendency in this direction was encouraged by his father. The latter desired his assistance in the smelting houses at Werran, but the boy's ambition to devote himself to minerals had taken too deep root, and he decided to go to the riding academy at Freiburg. He was a most ardent student, and all his spare moments were spent in neighboring mines. In 1771 he went to the University of Leipzig, where he prosecuted the study of law for 2 years, but eventually returned to his first love, mineralogy. When only 25 years of age, he published a book on minerals, then a wonder of arrangement, largely as a result of which he was appointed to the post of professor of mineralogy in the School of Mines at Freiburg, where he had formerly studied. His manner of discourse also was so attractive and stimulating that he riveted the attention of his pupils, incited them to pursue the studies that he loved, and fired them with a desire to apply his methods. Ostensibly he had to teach mineralogy, a science which in ordinary hands can hardly be said to evoke enthusiasm. But Werner's mineralogy embraced the whole of nature, the whole of human history, the whole interests and pursuits and tendencies of mankind. From a few pieces of stone, placed almost at random on the table before him, he would launch out into an exposition of the influence of minerals and rocks upon the geography and topography of the earth's surface. He would contrast the mountainous scenery of the granites and schists with the tamer landscapes of the sandstones and limestones. Tracing the limits of these contrasts of surface over the area of Europe, he would dwell on their influence upon the grouping and characteristics of the nations. He would connect, in this way, his specimens with the migration of races, the spread of languages, the progress of civilization. He would show how the development of the arts and industries of life had been guided by the distribution of minerals, how campaigns, battles, and military strategy as a whole had been dependent on the same course. The artist, the politician, the historian, the physician, the warrior were all taught that a knowledge of mineralogy would help them to success in their several pursuits. It seemed as if the most efficient training for the affairs of life were obtainable only at the mining school of Freiburg. The first feature of his grasp, distinguishable in every part of his life and work, was his overmastering sense of orderliness and method. When Werner entered upon his mineralogical studies, the science of minerals was an extraordinary chaos of detached observations and unconnected pieces of knowledge. But his very first essay began to put it into order, and by degrees he introduced into it a definite methodical treatment, doing for it very much what Linnaeus had done some years before for botany. Like that great naturalist, he had to invent a language to express with precision the characters which he wished to denote, so that mineralogists everywhere could recognize them. For this purpose he employed his mother tongue and devised a terminology which, though artificial and cumbrous, was undoubtedly of great service for a time. Uncouth in German, it became almost barbarous when translated into other languages. What would the modern English-speaking student think of a teacher who taught him, as definite characters, that a mineral could be distinguished as hard or semi-hard, soft or very soft, as very cold, cold, pretty cold, or rather cold, as fortification-wise bent, as indeterminate curved lamellar, as common angulo-granular, or as not particularly difficultly frangible? Werner arranged the external characters of minerals in so methodical a way that they could readily be applied in the practical determination of species. Yet strangely enough he neglected the most important of them all, that of crystalline form. From the individual minerals, he proceeded to the consideration of their distribution and the character and origin of the different rocks in which they occur. To this branch of inquiry he gave the name of geognosy, or knowledge of the earth, and he defined it as the science which reveals in a methodical order the terrestrial globe as a whole, and more particularly the layers of mineral matter whereof it consists, informing as to the position and relations of these layers to each other, and enabling the formation of some idea of their origin. The term geology had not yet come into use, nor would either Werner or any of his followers have adopted it as a synonym for the geognosy of the Freiburg school. They prided themselves on their close adherence to fact as opposed to theory, They boasted of the minuteness and precision of their master's system, and contrasted the positive results to which it led with what they regarded as the vague conclusions and unsupported or idle speculations of other writers. Werner arranged the crust of the earth into a series of formations, which he labeled and described with the same precision that he applied to the minerals in his cabinet. But never in the history of science did a stranger hallucination arise than that of Werner and his school when they supposed themselves to discard theory and build on a foundation of accurately ascertained fact. Never was a system devised in which theory was more rampant, theory, too, unsupported by observation, and, as is now known, utterly erroneous. One of the fundamental postulates of the Wernerian doctrines was the existence of what were termed universal formations. When he elaborated his system, Werner had never been out of Saxony in the immediate adjacent regions. His practical knowledge of the earth was, therefore, confined to what he could see there, and so little was then known of the geological structure of the globe as a whole that he could not add much to his acquaintance with the subject by reading what had been observed by others, though there can be little doubt that he stood greatly indebted to Lehmann and Fuchsel. With this slender stock of acquirement, he adopted the old idea that the whole globe had once been surrounded with an ocean of water, at least as deep as the mountains were high, and he believed that from this ocean there were deposited by chemical precipitation the solid rocks which now form most of the dry land. He taught that these original formations were universal, extending round the whole globe, though not without interruption, and that they followed each other in a certain order. Werner affirmed that the first formed rocks were entirely of chemical origin, and he called them primitive, including in them granite, which was the oldest, gneiss, mica slate, clay slate, serpentine, basalt, porphyry, and concluding with syenite as the youngest. Succeeding these came what he afterwards separated as the transition rocks, consisting chiefly of chemical productions, greywack slate, and limestone, but comprising the earliest mechanical depositions and indicating the gradual lowering of the level of the universal ocean. Still newer, and occupying, on the whole, lower positions, marking the continued retirement of the waters, were the Floetz rocks, composed partly of chemical, but chiefly of mechanical, sediments, and including sandstone, limestone, gypsum, rock salt, coal, basalt, obsidian, porphyry, and other rocks. Latest of all came the alluvial series, consisting of recent loams, clays, sands, gravels, sinters, and peat. This system was not put forward tentatively as a suggestion toward better comprehension of the history of the earth. It was announced dogmatically as a body of ascertained truth about which there could be no further doubt or dispute. Quote, "In recapitulating the state of our present knowledge," end quote, Werner declares with his characteristic emphasis, quote, "It is obvious that we know with certainty that the Floetz and primitive mountains have been produced by a series of precipitations and depositions formed in succession from water which covered the globe. We are also certain that the fossils which constitute the beds and strata of mountains were dissolved in this universal water and were precipitated from it. Consequently, the metals and minerals found in primitive rocks and in the beds of Floetz mountains were also contained in this universal solvent and were formed from it by precipitation. We are still further certain that at different periods different fossils have been formed from it. At one time earthy, at another metallic minerals, at a third time some other fossils. We know, too, from the position of these fossils, one above another, to determine with the utmost precision which are the oldest and which are the newest precipitates. We are also convinced that the solid mass of our globe has been produced by a series of precipitations formed in succession, in the humid way, that the pressure of the materials thus accumulated was not the same throughout the whole, and that this difference of pressure and several other concurring causes have produced rents in the substance of the earth, chiefly in the most elevated parts of its surface. We are also persuaded that the precipitates taking place from the universal water must have entered into the open fissures which the water covered. We know, moreover, for certain that veins bear all the marks of fissures formed at different times, and, by the causes which have been assigned for their formation, that the mass of veins is absolutely of the same nature as the beds and strata of the mountains, and that the nature of the masses differs only in the locality of the cavity where they occur. In fact, the solution contained in its great reservoir, that excavation which held the universal water, was necessarily subjected to a variety of motion, while that part of it which was confined to the fissures was undisturbed and deposited in a state of tranquillity its precipitate." End quote. It would be difficult to cite from any other modern scientific treatise a series of consecutive sentences containing a larger number of dogmatic assertions of which almost every one is contradicted by the most elementary facts of observation. The habit of confident affirmation seems to have blinded Werner to the palpable absurdity of some of his statements. For example, the theory of a universal primeval ocean occupying an excavation that was so deep that it overtopped the highest mountains was superficially most ridiculous. If this ocean covered the entire globe, where was the excavation and how did this deep ocean disappear? It may be interesting to know how Werner explained this natural question, but none of his writings satisfactorily answer it. In one place he thinks it possible that, quote, "one of the celestial bodies which sometimes approach near to the earth may have been able to withdraw a portion of our atmosphere and of our ocean." End quote. But if once the waters were abstracted, how were they to be brought back again so as to cover all the hills on which his highest flowets formations were deposited? One might have thought that, having disposed of the universal ocean, even in this rather peremptory fashion, the Wernerians would have been in no hurry to call it back again and set the same stupendous and inexplicable machinery once more going, but the exigencies of their theory left them no choice. Having determined as an incontrovertible fact that certain rocks had been deposited as chemical precipitates in a definite order from a universal ocean, when these philosophers, as their knowledge of nature increased, found that some of these so-called precipitates occurred out of their due sequence and at much higher altitudes than had been supposed, they were compelled to bring back the universal ocean and make it rise high over hills from which it had already receded. Not only had they to call up the vasty deep, but they had to endow it with rapid and even tumultuous movement as it swept upward over forest-clothed lands. Having raised it as high as their so-called flowets formations extended, and having allowed its waters to settle and deposit precipitates of basalt and greenstone, they had to hurry it away again to the unknown regions where it still remains. So early as 1768, before Werner had commenced his mineralogical studies, Raspe had truly characterized the basalts of Hesse as of igneous origin. Arduino had pointed out numerous varieties of trap rock in the Vincentine as analogous to volcanic products and as distinctly referable to ancient submarine eruptions. Desmarest had, in company with Fortis, examined the Vincentine in 1766 and confirmed Arduino's views. In 1772 Banks, Solander, and Troyle compared the columnar basalt of Hecla with that of the Hebrides. Coligny, in 1774, recognized the true nature of the igneous rocks on the Rhine between Andernach and Bonn. In 1775, Guettard visited the Vivarais and established the relation of basaltic currents to lavas. Lastly, in 1779, Faujas published his description of the volcanoes of the Vivarais and Velay and showed how the streams of basalt had poured out from craters which still remain in a perfect state. Leopold von Buch, 1774 to 1852, was the most illustrious of the geologists taught by Werner. He was born in the castle of Stolp in Pomerania, the son of a nobleman with considerable property. While still a boy, he displayed a passionate love of scientific inquiry, and his fondness for chemical and physical mineralogical studies led him to select the Mining Academy of Freiburg for his collegiate course. While there, Alexander von Humboldt and Freiesleben were among his fellow students, and with them he formed close ties of friendship. He made his home for nearly 3 years, 1790 to 1793, with Professor Werner, for whom he entertained the deepest sentiments of reverence and friendship, and these were in no way altered when, in after years, some of his opinions began to diverge from the teaching of Werner. Von Buch examined the raised beaches and terraces of Scandinavia and came to the conclusion that the Swedish coast was slowly rising above the level of the sea. In this he agreed with the opinion that had been formed by Playfair with regard to the raised beaches of Scotland. In 1809, von Buch was chiefly engaged in the mineralogical and geological researches in the Alps. Meanwhile, great interest had been roused throughout Europe by the results of von Humboldt's brilliant volcanic studies in Central and South America, and von Buch determined to make a special study of some volcanic district. Accompanied by the English botanist Charles Smith, he visited the Canary Isles and in 1815 convinced himself that they had been the center of intense volcanic activity. In his famous monograph, A Physical Description of the Canary Islands, published in 1825, he enunciated his hypothesis of upheaval craters and distinguished between centers and bands of volcanic action. In 1817 he travelled to Scotland and visited Staffa and the Giant's Causeway. When he again returned to the Alps, he renounced the Wernerian doctrines of the origin of basalt and other volcanic rocks, and ascribed the upheaval of the Alps to the intrusion of igneous rocks. At the time when Werner was in the zenith of his fame, during those 70s and 80s of the 18th century when young geologists were flocking to hear the wisdom from the lips of the prophet of geognosy in Freiburg, a private gentleman, living quietly in Edinburgh, was deliberating and writing a work on the Earth's surface that will live forever in the annals of geology as one of its noblest classics. His work and that of his contemporaries is ably reviewed by Carl von Zittel. James Hutton, 1726 to 1797, the author of the famous Theory of the Earth, was the son of a merchant and received an excellent education at the high school and university of his native city. His strong bent for chemical science induced him to select medicine as a profession. He studied at Edinburgh, Paris, and Leyden, and took his degree at Leyden in 1749, but on his return to Scotland he did not follow out his profession. Having inherited an estate in Berwickshire from his father, he went to reside there and interested himself in agriculture and in chemical and geological pursuits. From his early days he had always taken a delight in studying the surface forms and rocks of the earth's crust, and had lost no opportunity of extending his geological knowledge during frequent journeys in Scotland, England, in northern France, and the Netherlands. At last Hutton set himself to the work of shaping his ideas into a coherent, comprehensive form, and in 1785 read his paper on The Theory of the Earth before the Royal Society of Edinburgh. The publication of the work attracted little favorable notice, partly due to the involved, unattractive style of writing. In larger measure, however, it was due to the fact that the learning of the schools had no part in Hutton's work. For the best part of his life he had conned them, tossed them in his mind, tested them, and sought repeated confirmation in nature before he had even begun to fix them in written words or cared to think of anything but his own enjoyment of them. Hutton's work was projected upon a plane half a century beyond the recognized geology of his own time. Hutton's audience of geologists had to grow up under other influences than polemical discussions between Neptunists and Plutonists, and had to learn from Hutton himself how to tap the fountain of science at its living source. In 1793, a Dublin mineralogist, Kirwan, attacked Hutton's work, and the great Scotsman, now advanced in years, resolutely determined to revise his work and do his best by it. Valuable additions were made, and the subject matter brought under more skillful treatment. In 1795, the revised work appeared at Edinburgh in independent form and in 2 volumes. It was his last effort. He died 2 years later from an internal disease which had overshadowed the closing years of his life. The original treatise of Hutton is divided into 4 parts. The first 2 parts discuss the origin of rocks. The Earth is described as a firm body, enveloped in a mantle of water and atmosphere, and which has been exposed during immeasurable periods of time to constant change in its surface conformation. The events of past geologic ages can be more satisfactorily predicted from a careful examination of present conditions and processes. The Earth's crust, as far as it is open to investigation, is largely composed of sandstones, clays, pebble deposits, and limestones that have accumulated on the bed of the ocean. The limestones represent the aggregated shells and remains of marine organisms, while the other deposits represent fragmental material transported from the continents. In addition to these sedimentary deposits of secondary origin, there are primary rocks, such as granite and porphyry, which, as a rule, underlie the aqueous deposits. In earlier periods, the Earth presented the aspect of an immense ocean, surmounted here and there by islands and continents of primary rock. There must have been some powerful agency that converted the loose deposits into solid rock and elevated the consolidated sediments above the level of the sea to form new islands and continents. According to Hutton, this agency could only have been heat. It could not have been water, since the cement material, quartz, feldspar, fluorine, etc., of many sedimentary rocks is not readily soluble in water and could scarcely have been provided by water. On the other hand, most solid rocks are intermingled with silicious, bituminous, or other material which may be melted under the influence of heat. This suggested to Hutton his theory that at a certain depth, sedimentary deposits are melted by the heat to which they are subjected, but that the tremendous weight of the superincumbent water causes the mineral elements to consolidate once more into coherent rock masses. He applied this theory of the melting and subsequent consolidation of rock material universally to all pelagic and terrestrial sediments. In the third part, it is shown that the present land areas of the globe are composed of rock strata which have consolidated during past ages in the bed of the ocean. These are said to have been pushed upward by the expansive force of heat, while the strata have been bent and tilted during the upheaval. Hutton next describes the occurrence of crust fissures both during the consolidation of the rock and during the elevation of large areas and the subsequent inrush of molten rock or mineral ores into the fissures. He regards volcanoes as safety valves during upheaval, which by affording exit at the surface for the molten rock magma and superheated vapors prevent the expansive forces from raising the continents too far. The evidences of volcanic eruption in the older geological epochs are next discussed. Hutton expresses the opinion that during the earlier eruptions the molten rock material spread out between the accumulated sediments or filled crust fissures, but did not actually escape at the surface. Consequently, that the older rock magmas had solidified at great depths in the crust and under enormous pressure of superincumbent rocks. He calls the older eruptive rocks subterraneous lavas, and includes among them porphyry and the whinstones, e.g. trap rock, greenstone, basalt, whack, amygdaloidal rocks. Granite was also added in a later treatise. Hutton points out that the subterraneous lavas have a crystalline structure, whereas those that solidify at the surface have a slaggy or vesicular structure. In the fourth part, Hutton concentrates attention on the pre-existence of older continents and islands from which the materials composing more recent land areas must have been derived. He likewise discusses the evidence of pre-existing pelagic, littoral, and terrestrial faunas from which existing faunas must have sprung, but, he continues, the existence of ancient faunas assumes an abundant vegetation, and direct evidence of extinct floras is presented in the coal and bituminous deposits of the Carboniferous and other epochs. Other evidence is afforded in the silicified trunks of trees that occasionally are found in marine deposits and have clearly been swept into the sea from adjacent lands. Hutton then sets forth, in passages that have become classic in geological science, the slow process of the subaerial denudation of land surfaces. He describes the effects of atmospheric weathering, of chemical decomposition of the rocks, of their demolition by various causes, and the constant attrition of the soil by the chemical and mechanical action of water. He elucidates with convincing clearness the destructive physical, chemical, and mechanical agencies that affect the dissolution of rocks, the work of running water in transporting the worn material from the land to the ocean, the steady subsidence of coarser and finer detritus that goes on in seas and oceans, lakes and rivers, and the slow accumulation of the deposits to form rock strata. Hutton impresses upon his readers the vastness of the geological eons necessary for the completion of any such cycle of destruction and construction. In proof of this, he calls attention to the comparative insignificance of any changes that have taken place in the surface conformation of the globe within historic time. Hutton was thus the great founder of physical and dynamical geology. He, for the first time, established the essential correlation in the processes of denudation and deposition. He showed how, in proportion as an old continent is worn away, the materials for a new continent are being provided, how the deposits rise anew from the bed of the ocean, and another land replaces the old in the eternal economy of nature. The outcome of Hutton's argument is expressed in his words, quote, "that we find no vestige of a beginning, no prospect of an end." End quote. When Hutton's theory of the Earth's structure is compared with that of Werner and other contemporary or older writers, the great feature which distinguishes it and marks its superiority is the strict inductive method applied throughout. Every conclusion is based upon observed data that are carefully enumerated. No supernatural or unknown forces are resorted to, and the events and changes of past epochs are explained from analogy with the phenomena of the present age. Hutton's explanation of the uprising of continents, owing to the expansive force of the subterranean heat, was not altogether new, nor was it satisfactory. Neither had Hutton any clear conception of the significance of fossils as affording evidence of a gradual evolution. Yet in spite of these disadvantages, Hutton's theory of the Earth is one of the masterpieces in the history of geology. Hutton's genius first gave to geology the conception of calm, inexorable nature working little by the raindrop, by the stream, by insidious decay, by slow waste, by the life and death of all organized creatures, and eventually accomplishing surface transformations on a scale more gigantic than was ever imagined in the philosophy of the ancients or the learning of the schools. Hutton's scientific spirit and genial personality won for him many friends and adherents among the members of the Edinburgh Academy. The most distinguished of these were Sir James Hall and the mathematician John Playfair. Hall, 1762 to 1831, contested the validity of the opinion held by some of Hutton's opponents, that the melting of crystalline rocks would only yield amorphous glassy masses. Hall followed experimental methods. He selected different varieties of ancient basalt and lavas from Vesuvius and Etna, reduced them to a molten state, and allowed them to cool. At first he arrived only at negative results, as vitreous masses were produced, but then he retarded the process of cooling and actually succeeded in obtaining solid, crystalline rock material. By regulating the temperature and the time allowed for the cooling and consolidation, Hall could produce rocks varying from finely to coarsely crystalline structure, and he therefore proved that under certain conditions, crystalline rock could, as Hutton had said, be produced by the cooling of molten rock magma. Hall then put to the test Hutton's further hypothesis that limestone was melted and recrystallized in nature. To this hypothesis the objection had been made that the carbonic acid gas must escape if limestone were brought to a glowing heat and the material would be converted into quicklime. This was Hall's first experience. Then he devised another experiment. He introduced chalk or powdered limestone into porcelain tubes or barrels, sealed them and brought them to a very high temperature. The carbon dioxide gas could not escape under these conditions. The calcareous material was thus subjected to the enormous pressure of the imprisoned air and converted into a granular substance resembling marble. Hall also conducted experiments on the bending and folding of rocks. He spread out alternate horizontal layers of cloth and clay, placed a weight upon them and subjected them to strong lateral pressure. These and similar experiments have often been repeated within recent years, and it is well known that in this way phenomena of deformation can be artificially produced which bear the closest resemblance to the phenomena of rock deformation under natural conditions. In his desire to vindicate Hutton's theory, Hall became himself one of the great founders of experimental geology. At the same time, John Playfair, 1748 to 1819, whose interest in geology had been roused by Hutton's companionship, became the enthusiastic exponent of Hutton's theory. It was Playfair's literary skill that opened the eyes of scientific men to the heritage Hutton had left for them. He did for Hutton's teaching what 50 years after was done for Darwin's doctrines by the gifted Huxley. Playfair's Illustration of the Huttonian Theory is a lucid exposition of that theory in the form of 26 ample discussive notes. Playfair's work differs in no essential point from the views held by his master and friend, but many subjects which receive a subordinate treatment in the theory of the earth are brought into prominence by Playfair and placed for the first time on a firm scientific basis. His treatment of valley and lake erosion is extremely able, and Playfair was the first geologist who realized that the huge erratic blocks might have been carried to their present position by former glaciers. His insight in this respect would have alone won him for a lasting fame, for the erratics on alpine slopes and plains had long been observed by geologists and an explanation vainly sought.
With Hutton's work, as a basic point, geology took new life. The theory, in the main, was sound. It remained but to classify the results of the past and to prepare for the reception of the observations of the future. The 19th century witnessed the great development of the process of the Earth's formation from stratigraphical geology set forth. Jean-Baptiste Pierre-Antoine de Monet, Chevalier de Lamarck, 1744 to 1829, came from an ancient but somewhat decayed family and was born in a village of Picardy as the 11th and youngest child of the Seigneur de Barne. The earlier part of his career was devoted first to soldiering, then to botany, and then to zoology. Though Lamarck wrote little on geology, the extent to which he had pondered over the problems of the science, which in his time had hardly taken definite shape, is well illustrated by the little volume which he published in 1802 under the title of Hydrogeology. He recognized that nothing can ultimately resist the alternating influence of wetness and drought, combined with that of heat and cold, and that the disintegration of mineral substances by these atmospheric conditions prepares the way for the erosive action of running water in all its various forms. To him, it was clear that every mountain which had not been erupted by volcanic action or by some other catastrophe had been cut out of a plain, so that the mountain summits represent the relics of that plain, save in so far as its level has been lowered in the general degradation. He admits that in many mountains, the component strata were often vertical or highly inclined. But he will not in that account believe in any universal catastrophe, such as has been demanded by many previous writers, and was still loudly advocated in his own time by his fellow countryman Cuvier. Lamarck conceived the ocean basin to owe its existence and preservation to the perpetual oscillation of the tides and partly also to the general westerly movement of the water. He supposed the tidal oscillation to be a gigantic force, which has actually eroded the basin and now prevents it from being shallowed through the deposit of land-derived sediment, by continually scoring this sediment out and casting it along the more sheltered shores of the land. No one before his time had been able to follow so clearly the successive stages through which organic remains pass until they become crystalline stone, presenting no trace of their original organic structure. During the last 10 years of his long life, he suffered from total blindness and had to rely on the affectionate devotion of his eldest daughter for the completion of such works as he had in progress before his eyesight failed. The world is becoming more conscious now of what it owes to the genius of this illustrious naturalist. Among those students of science who have the most reason to cherish his memory, geologists should look back gratefully to his services in starting the science of paleontology, in propounding that the doctrine of evolution, and in affirming that the great insight of some of the fundamental principles of modern geology. Georges Cuvier, 1769 to 1832, a French naturalist and founder of the science of comparative anatomy, effected a great and noble advance in the science of paleontology. It is to Cuvier that the world owes its first systematic application of that science of comparative anatomy, which he himself did so much to place upon a sound basis, to the study of the bones of fossil animals. He demonstrated that extinct animals could be reconstructed from fragmentary remains by applying the law of correction of growth. It is true, as pointed out by Professor Huxley, that he placed more confidence and security in this law than its empiric nature and exceptions would justify. Cuvier, in his work in the geology of the Paris Basin, was greatly assisted by his friend Alexandre Brongniart. Brongniart was early trained in scientific pursuits. In 1807, he published a treatise on mineralogy, which became a standard work. He became professor of mineralogy at the Jardin des Plantes, and in 1808 appeared the work on the Paris Basin. Cuvier and Brongniart drew up a systematic table of the succession of the stratigraphical horizons in accordance primarily with the sequence of the deposits in the ground and with the particular fossils characterizing each group of deposits. The varieties of rock and the thicknesses and distribution of the different deposits were also fully considered and carefully mapped. Omalis de Holoy, 1783 to 1875, the Belgian geologist, made an examination of the formations of the Auvergne, Valais, and in parts of Italy and Germany, and in all cases proved conclusively that the fossil remains had been embedded in the deposits of freshwater marshes and were not remains which had been accidentally swept into marine deposits. The Belgian geologist supplemented the observations of Cuvier and Brunier with great success. Early in his career, de Holoy had regarded the position of the strata, their horizontal, slightly or highly inclined, or vertical position, of great importance in determining the age of the strata. He thought the horizontal strata corresponded to Werner's Floats formations, and all inclined strata to Werner's transitional formations. But his subsequent visit to the Alps and Ural Mountains caused him to modify these views. The fearful earthquake, which destroyed Lisbon in 1755, was made the subject of a large number of scientific inquiries into the causes of earthquakes. William Stukeley's theory, attributing earthquakes to electrical disturbances, gained a certain amount of support abroad. Another Englishman, Reverend John Marshall, suggested that sudden expansion of vapors enclosed in fissures and cavities in the Earth's crust caused earthquakes and volcanoes, the upheaval of mountain systems, and the deformation of rocks. In 1760, he published a series of observations on earthquakes in mountain structure. This paper was accompanied by an ideal section through a mountain system, showing a central core composed of the crystalline massive rocks on either side in succession of uptilted and upheaved strata covered in their turn by younger, slightly tilted or horizontal deposits composing the neighboring plains. Marshall, however, did not draw any general conclusions, yet he deservedly ranks as the great pioneer of the modern science of seismology. Another English observer was John Whitehurst, 1713 to 1788, who published in 1778 an Inquiry into the Original State and Formation of the Earth. This work was the last effort of the fantastic English school of cosmologists. Amid absurd speculations as to the condition of chaos and other equally visionary topics, he wrote well on organic remains and showed that he clearly grasped the stratigraphical succession of the formation in Derbyshire and other parts of England. Quote, "The strata invariably follows each other," end quote, he remarks, quote, "as it were, in alphabetical order," end quote. "And though they may not be alike in all parts of the earth, nevertheless, in each particular part, how much soever they may differ, yet they follow each other in a regular succession." He was one of the many who were interested in the origin of the basalt pillars of the Giant's Causeway, and who endeavored to interpret their origins. One of the most active and interesting of those who devoted themselves with ardor to the study of the Italian volcanoes was Gatta di Dolomule, 1750 to 1801. His attention was especially drawn to the active and extinct volcanoes of the Mediterranean basin. As far back as 1776, he made an announcement that he had found in Portugal evidence of volcanoes older than certain mountains of limestone, a statement which he supplemented in 1784 with further evidence from Sicily proving the intercalation of ancient lavas among stratified deposits. Dolomule confirmed the igneous origin of basalt rock, regarding it as a variety of lava, for the most part associated with submarine eruptions. His name is perpetuated in the name of the Dolomites, given to the beautiful district in South Tyrol, south of the Puster Valley. Elie de Beaumont was another scientific Frenchman who interested himself in mountains. He was one of the most enthusiastic adherents of the volcanist doctrines. Toward the end of an article on mountains, which appeared in the Annals of the French Academy, are a few remarks on mountain structure. Brief although they are, the remarks on the influence of the slow cooling of the earth on surface conformation and the origin of furrows and fissures are at once recognized by a reader of the present day as the starting point of the modern view on mountain structure. Later appeared his 3-volume treatise on mountain systems. He points out that in virtue of the continued cooling of the planet, the radius is shortened and the crust is affected by a general centripetal movement. That is, the volume of the globe becoming less. The crust is drawn in toward the center of gravity. Delisle, meanwhile, had calculated 1,340 meters as the amount by which the Earth's radius had already been shortened. In other words, the Earth's crust in the course of the geological epochs had approached the Earth's center by a distance about equal to the height of Chimborazo or the Himalayas above sea level. William Smith, 1769 to 1839, an English engineer, was the first to recognize the importance of fossils in their full significance as a means of determining the relative age of strata. Born in a country that was unusually rich in fossil remains, he had in his boyhood abundant opportunity of observing and collecting. For 25 years he continued his investigation of all parts of England, entering his observations in colored geographical maps and compiled them from time to time in the form of tables or as explanatory notes to his maps. About 1800, he began the preparation of a geographical map of England and Wales on the scale of 5 miles to 1 inch, which occupied nearly 15 years of his life, and which was supplemented by separate maps of the counties, published in color on 21 sheets. Smith's map is the first attempt to represent on a large scale the geographical relations of any extensive tract of ground in Europe. It was a magnificent achievement and was the model of all subsequent geological maps. For English geography, the publication of the map was the starting point of a new regime. The Geological Society of London conferred upon him the Wollaston Medal, and he well deserves to be called the father of English geology. There is yet another name that deserves to be remembered in any review of the early efforts to group the secondary formations, that of Thomas Webster, 1773 to 1844. As far back as 1811, this clever artist and keen-eyed geologist began a series of investigations of the coast sections of the Isle of Wight and of Dorset, and continued them for 3 years. He clearly defined each of the leading subdivisions of the Cretaceous series and prepared the way for the admirable later and more detailed work of William Henry Fitton, 1780 to 1861, to whom geology is indebted for the first detailed and accurate determination of the succession of strata and their distinctive fossils, from the base of the chalk down into the oolites in the south of England and the neighboring region in France. More particularly, he showed the relations and importance of the greensand formations, his memoirs on which are now among the classics of English geology. The early progress of stratigraphical geology in Britain includes the important influence exerted by the Geological Society of London, which was founded in 1807 to investigate the mineral structure of the Earth. At the time, the warfare between the Neptunists and the Plutonists still continued, but there were many men interested in the study of geological subjects who were weary of the conflict of hypothesis and who would fain devote their time and energy to the accumulation of facts regarding the ancient history of the globe, rather than to the elaboration of theories to explain them. A few such inquirers formed themselves into the Geological Society and soon attracted others around them until, in a few years, they had established an active institution which became a center for geological research and discussion, published the contributions of its members in 4 volumes, and eventually was incorporated by royal charter as one of the leading scientific bodies of the country. This society, which has been the parent of others in different countries, continues to flourish, and its publications, extending over nearly a century, contain a record of the original researches which have powerfully helped the progress of all branches of geology. Besides their papers issued by the Society, some of the early members published separate works, which greatly advanced the cause of their favorite science. Among these early independent treatises, perhaps the most important was the Outlines of the Geology of England and Wales by W. D. Conybeare, 1787 to 1857, and W. Phillips, 1775 to 1828, which appeared in 1822. In this volume, all that was then known regarding the rocks of the country, from the youngest formations down to the old red sandstone, was summarized in clear and methodical a manner as to give a definite impulse to the cultivation of geology in England. The amount of ascertained fact regarding the structure and history of the earth was every year increasing at so rapid a rate that it became necessary to prepare digests of it for the use of those who wished to be informed on these subjects or to keep pace with the advance of knowledge. Hence arose in different countries textbooks, manuals, and other general treatises. Herein an account was given of the facts and principles of geological science. But of all the English writers of general treatises on geology, the first place must undoubtedly be assigned to Charles Lyell, 1797 to 1875, who exercised a profound influence on the geology of his time in all English-speaking countries, adopting the principles of the Hutton theory, says Sir Archibald Geikie in his Founders of Geology. He developed them until the original enunciator of them was nearly lost sight of. Quote, "With unwearied industry he marshaled in admirable order all the observations that he could collect in support of the doctrine that the present is the key to the past. With inimitable lucidity he traced the operation of existing causes and held them up as a measure of those which had acted in bygone time. He carried Hutton's doctrine to its logical conclusion, for not only did he refuse to allow the introduction of any process which could not be shown to be part of the present system of nature, he would not even admit that there were any reasons to support the degree of activity of geological agents to have ever seriously differed from what it has been within human experience. He became the great high priest of uniformitarianism, the creed which grew to be almost universal in England during his life, but which never made much way in the rest of Europe, and which, to its extreme form, is probably now held by few geologists in the country." End quote. Lyell's Principles of Geology will, however, always rank as one of the classics of geology, and must form an early part of the reading of every man who would wish to make himself an accomplished geologist. The last part of his work was ultimately published as a separate volume, with the title Elements of Geology, in which a large space was devoted to an account of the stratified fossiliferous formations. This treatise, diligently kept up to date by its author, continued during his lifetime to be the chief English exposition of its subject and the handbook of every English geologist.
Lyell's function was mainly that of a critic and exponent of the researches of his contemporaries, and of a philosophical writer thereon, with a rare faculty of perceiving the connection of scattered facts with each other and with the general principles of science. As Ramsay once remarked, "We collect the data, and Lyell teaches us to comprehend the meaning of them." But Lyell, though he did not, like Sedgwick and Murchison, add new chapters to geological history, nevertheless left his mark upon the nomenclature and classification of the geological record. Conceiving, as far back as 1828, the idea of arranging the whole series of tertiary formations in 4 groups, according to their affinity to the living fauna, he established, in conjunction with the Shays, who had independently formed a similar opinion, the well-known classification into Eocene, Miocene, and Pliocene. The scheme was a somewhat artificial one, and the original percentages have had to be modified from time to time, but the terms have kept their place, and are now firmly planted in the geological language of all corners of the globe. So far, no complete subdivision of the immense complex of strata between the crystalline schists and the coal measures had been attempted, and it was this gigantic task that the two British geologists, Adam Sedgwick, 1785 to 1873, and Roderick Murchison, 1792 to 1871, set themselves to accomplish in the British area. Unfortunately, the scarcity of fossils made it still impossible for Sedgwick to establish paleontological subdivisions. Murchison was more fortunate. While his colleague was engaged in the examination of the oldest group of the transitional series, Murchison began his investigation of the series in descending order from the upper members to the lower. He examined the exposures of old red sandstone and the rocks immediately below it, which occur on the eastern and southern borders of Wales. Murchison found fossils in abundance, and in a couple of years was able to lay before the Geological Society a complete paleontological sequence in the upper portion of the transitional formations. At first, Murchison had called these higher members examined by him an upper fossiliferous greywacke series. But in the year 1835, in compliance with the strongly expressed wish of Eli de Beaumont, he proposed the name Silurian system as a special designation for the upper members, and as the older members of the transitional series examined by Sedgwick in Cumberland and North Wales could not be identified with any of the members of the Silurian system of Murchison, the term of Cambrian series was proposed by Sedgwick in 1836 for these older members, and this term was accepted by Murchison. In the year 1839, Murchison published his great work, The Silurian System, wherein the results of his researches, extending over 6 years, were admirably elucidated. After a short statement regarding the younger geological formations, and a more detailed account of the English Carboniferous formation, the mountain limestone, and the old red sandstone, Murchison passes to the special description of the Silurian system in South Wales and the adjoining counties of England. With great accuracy he depicts the stratigraphical relations, the lithological characters of the rocks, the contents of fossils and minerals, and the occurrences of volcanic rocks. A special paleontological part with 27 quarto plates is devoted to the description of the characteristic fossils by L. Agassiz, Sowerby, and Lonsdale. Numerous colored sections help to demonstrate the tectonic relations of the district. Murchison distinguished 3 chief divisions in the Silurian system. Upper Silurian, comprising the Ludlow rocks and Wenlock limestone. Lower Silurian, comprising the Cotterrock sandstone and Llandeilo flags, and Cambrian. He found it impossible at the time to fix a definite paleontological horizon as the lower limit of the Silurian system, and Sedgwick also could not assign any paleontological or other feature which would determine the upper limit of the Cambrian series. Nevertheless, the recognition of the Silurian and Cambrian systems was one of the most important advances that had been made in stratigraphy. There still remained, however, a thick group of strata in the Wernian transitional series, which could not be allotted to either of the newly defined systems. Continued researches on the Paleozoic formations led Murchison to conclude that the Cambrian deposits examined by Sedgwick in North Wales contained no fossils different from those of the Lower Silurian, and that the Cambrian system was identical with the Lower Silurian. Murchison made known this opinion for the first time in a presidential address which he delivered at the Geological Society. Sedgwick was deeply hurt, and immediately began a new investigation of Wales, in which he was assisted by the paleontologist Salter, and in 1852 he upheld the independence of the Cambrian series. Murchison was not persuaded by Sedgwick's results, and demanded a paleontological formation for the Cambrian system. The members of the Geological Survey, to whom the investigation of Wales was entrusted, followed the views of Murchison. The Cambrian system disappeared from the official maps, and the color for Silurian rocks was carried over the whole of the area previously allotted to the Cambrian system. Sedgwick, embittered by the want of recognition for his Cambrian system, published, 1851 to 1855, a large work on the divisions and the fossils of the British Paleozoic deposits, and protested, in strong terms, against the views held by his former friend and fellow worker Murchison. While this dispute was in progress in Britain, a remarkable series of investigations by Johann Brande, 1799 to 1883, had made known the extraordinary abundance and variety of Silurian fossils in Bohemia. The The distinguished observer not only recognized the equivalence of Murchison's Upper and Lower Silurian series, but found below that series a still older group of strata, characterized by a different assemblage of fossils, which he termed the first or primordial fauna. It was ascertained that representatives of this fauna occur in Wales among some of the divisions of Sedgwick's Cambrian system, far below the Landilio group which formed the original base of the Silurian series. Eventually, therefore, since the death of the two great disputants, there has been a general consensus of opinion that the top of the Cambrian system should be drawn at the upper limit of the primordial fauna. The vast and varied series of rocks which have now been ascertained to underlie the oldest Cambrian strata have undergone much scrutiny during the last half-century, and their true nature and sequence are beginning to be understood. The first memorable onward step in this investigation was taken in North America by William Edmund Logan, 1798 to 1875. He recognized the existence of at least 3 vast systems older than the oldest fossiliferous formations. He may be said to have inaugurated the detailed study of Precambrian rocks. Subsequent investigation has shown the structure of the regions which he explored to be even more complicated and difficult than he believed it to be, and various important modifications have been proposed in his work and terminology by the able geologists of Canada and the United States who have continued his labors. But he will ever stand forward as one of the pioneers of geology, who, in the face of incredible difficulties, first opened the way towards a comprehension of the oldest rocks of the crust of the earth. Charles Darwin, 1809 to 1882, contributed several valuable works to the literature of geology. The 2 geological chapters in his Origin of Species produced a great revolution in geological thought. To most of the geologists of his day, Darwin's contention for the imperfection of the geological record and his demonstration of it came as a kind of surprise and awakening. They had never realized that the history revealed by the long succession of fossiliferous formations, which they had imagined to be so full, was in reality so fragmentary. And yet, when Darwin pointed out this fact to them, they were compelled, sometimes rather reluctantly, to admit that he was right. Lord Kelvin, Sir William Thomson, 1824 to 1907, attributed great importance to the enormous pressure existing in the interior of the earth and the consolidation of the nucleus from this cause. He ascribed to the body of the earth a degree of rigidity intermediate between that of steel and of glass. Starting from the nebular theory, Lord Kelvin supposed that the cooled and thereby heavier masses sank inward and formed an initial central nucleus, which always extended toward the periphery as the earth's mass continued to cool, until finally almost the whole earth became rigid. Sir Andrew Crombie Ramsay, 1814 to 1891, the noted Scotch geologist, devoted his attention to the physical side of geology. His dislike for paleontology and petrology sometimes led him into serious theoretical errors, thereby impairing the value of his work. His book on The Glacial Origin of Certain Lakes in Switzerland set forth the theory that certain lake basins had been scooped out by glaciers, now melted away. This book aroused considerable interest and controversy. This hypothesis has not yet been disproved, but it has failed to gather its most ardent supporters from the ranks of those who have an intimate personal knowledge of the Alps. In Austria and Switzerland, Suess, Hochstetter, Neumer, Studer, Agassiz, and others were making themselves famous. Suess's contributions to geology have opened up a new path in geological inquiry, and led the formation for what is now frequently termed the New Geology, dealing with the construction and relations of continents and mountain ranges, the dynamics of volcanoes and earthquakes, and the general movement of the Earth's crust. In 1885, he began his Antlitz der Erde, which is a masterful exposition of the relations of the dominant features of the Earth's surface, and the first luminous effort to correlate their multiform aspects and to give to them their true geological expression. He is one of the recognized authorities on earthquakes and volcanoes. Jean-Louis Rudolph Agassiz, 1807 to 1873, was born in Switzerland, and rose to distinction by his scientific work in Europe, but he went to the United States when he was still only 42 years of age, and spent the last 27 years of his life as an energetic and successful leader of science in his adopted home. His fame is thus both European and American, and the geologists of New England, not less than those of Switzerland, may claim him as one of their most distinguished worthies. His fame as a geologist is due to the important part he took in founding the modern school of glacial geology. Tracing the distribution of the erratic blocks above the present level of the glaciers, and far beyond their existing limits, he connected these transported masses with the polished and striated rock surfaces which were known to extend even to the summits of the southern slopes of the Jura. He was led to conclude that the alpine ice, now restricted to the higher valleys, once extended into the central plain, crossed it, and even mounted to the southern summits of the Jura chain. Before Agassiz took up the question, there were two prevalent opinions regarding the transport of the erratics. One of these called in the action of powerful floods of water. The other invoked the assistance of flowing ice. Agassiz combated these views with great skill. His reasoning ought to have convinced his contemporaries that his explanation was the true one. But the conclusions at which he arrived seemed to most men of the day extravagant and incredible. Even a cautious thinker like Lyell saw less difficulty in sinking the whole of Central Europe under the sea, and covering the waters with floating icebergs, than in conceiving that the Swiss glaciers were once large enough to reach to the Jura. Men shut their eyes to the meaning of the unquestionable fact that, while there was absolutely no evidence for a marine submergence, the former track of the glaciers could be followed mile after mile by the rocks they had scored and the blocks they had dropped, all the way from their present ends to the far distant crests of the Jura. He, moreover, demonstrated the identity of the phenomena in Britain with those in Switzerland, and claimed that not only glaciers once existed in the British Islands, but that large sheets of ice covered all the surface. These, and the subsequent researches and glacial monographs of the great Swiss naturalist, started the study of ancient glaciation. At first, his conclusions had been regarded as rank heresy by the older and more conservative geologists of the day. Von Buch could hardly contain his indignation, mingled with contempt, for what seemed to him the view of a youthful and inexperienced observer. A. von Humboldt also threw cold water upon the ardor of his young friend. But by degrees the opposition waned, and Agassiz had the satisfaction of seeing his most doughty opponents come over one by one to his side. William Nicol was a lecturer on natural philosophy at Edinburgh in the early part of the last century. Among his inventions was the famous prism of Iceland spar that bears his name. Every petrographer will acknowledge how indispensable this little piece of apparatus is in his microscopic investigations. He may not be aware, however, that it was the same skillful hands that devised the process of making thin slices of minerals and rocks, whereby the microscopic examination of these substances becomes possible. Yet for a quarter of a century, geologists took no notice of the opportunities put in their way by William Nicol. When Nicol died, his instruments and preparations passed into the hands of the late Mr. Alexander Bryson of Edinburgh, who, having considerable dexterity as a manipulator, and being much interested in the process, made many additions to the collections which he had acquired. At last, Henry Clifton Sorby came to Edinburgh, and had an opportunity of looking over the Bryson collection. He soon began to put the method of preparing thin slices into practice, made sections of mica schist, and found so much that was new and important, with a promise of such a further rich harvest of results, that he threw his whole energy into the investigation for several years, and produced at last, in 1858, the well-known memoir on the microscopical structure of crystals, which marks one of the most prominent epochs of modern geology. Sorby, for the first time, showed how, by means of the microscope, it was possible to discover the minute structure and composition of rocks, and to learn much regarding their mode of origin. In recent years, some excellent work has been, and is constantly being done, along the line of geological investigation. Geological surveys are being conducted under the supervision of the governments of the United States, the individual states, and the countries of Europe, and prominent present-day geologists are writing invaluable books on geological subjects. Important contributions to the history of geology have been made by the fluent pens of Sir Archibald Geikie and Karl von Ziettel, to whose works much of the value of the foregoing may be ascribed, and each department of geology now is in the hands of able specialists. Geology and paleontology give great promise for the 20th century. In another 100 years the whole surface of the earth will perhaps be so well known that works on comparative topographical geology will be fully accomplished along the lines which Edward Suess has so ably initiated in his Antlitz der Erde. If, at the same time, the structural and physical problems of the solid earth crust continue to be accurately investigated in all parts of the earth, it may be possible to determine the actual physical sequence of events in the origin and development of this planet.
A discussion of the geological changes which this planet has undergone ought to be preceded by a study of the materials which enter into its composition. This branch of geology is technically termed geognosy. The Earth may be considered as a globe, which has cooled sufficiently to have a solid crust, enclosed in two envelopes or shells, the inner one of water covering about 3/4 of the globe, and the outer one of gas completely enveloping the whole. This outer envelope of gas is known as the atmosphere. The water is called the hydrosphere, and the solid globe is the lithosphere, or rock sphere. There is every reason to believe that the present gaseous and liquid envelopes of the planet are only a portion of the original mass of gas and water with which the globe was invested. As Sir Archibald Geikie says in his textbook of geology, fully a half of the outer shell or crust of the Earth consists of oxygen, which probably once existed in the primeval atmosphere. The extent, likewise, to which water has been abstracted by materials is almost incredible. It has been estimated that already 1/3 of the whole mass of the ocean has been thus absorbed. Eventually, the condition of the planet will probably resemble that of the Moon, a globe without air, or water, or life of any kind. The gaseous envelope to which the name of atmosphere is given extends from the Earth's surface to a distance which has been variously estimated according to the methods of observation employed. From the phenomena of twilight, it may be inferred that the atmosphere must be at least 45 miles thick. The aurora indicates a sensible atmosphere at 100 miles, and clouds have been detected at heights of nearly 100 miles. Meteorites, which become incandescent by friction against our atmosphere, sometimes appear at heights of 150 miles. We may therefore infer that the atmosphere stretches for at least that distance from the Earth's surface, and probably in a state of extreme tenuity much farther. At sea level, the mean pressure of the atmosphere is about 14¾ pounds per square inch. Many speculations have been made regarding the chemical composition of the atmosphere during former geological periods. There can indeed be no doubt that it must originally have differed very greatly from its present condition. It has been contended, for instance, that originally there was little or no free oxygen in the atmosphere, which may have consisted mainly of nitrogen, carbonic acid, and aqueous vapor. Besides the abstraction of the oxygen, which now forms fully a half of the outer crust of the Earth, the vast beds of coal found all over the world in geological formations of many different ages doubtless represent so much carbon dioxide, carbonic acid, once present in the air. As now existing, the atmosphere is considered to be normally a mechanical mixture of nearly 4 volumes of nitrogen and 1 of oxygen, with minute proportions of carbon dioxide and water vapor and still smaller quantities of ammonia and the powerful oxidizing agent, ozone. The mean proportion of carbon dioxide is about 3.5 parts in every 10,000 of air. The other substances in the air are gases, vapors, and solid particles. Of these, by much of the most important is the vapor of water, which is always present, but in very variable amount according to temperature. It is by this vapor, together with carbon dioxide and suspended dust particles, that the radiant heat in the atmosphere is absorbed. The water vapor condenses into dew, rain, hail, and snow, and is thus of paramount importance in the great series of surface agencies which play so large a part in the geological changes of the Earth. In analyzing the air carried down in solution in rainwater, the atmospheric gases, together with ammonia, nitric, sulfurous and sulfuric acids, chlorides, various salts, solid carbon, inorganic dust, and organic matter have been detected. The fine microscopic dust so abundant in the air is no doubt for the most part due to the action of wind in lifting up the finer particles of disintegrated rock on the surface of the land. As a geological agent, the atmosphere affects changes by the chemical reactions of its constituent gases and vapors, by its varying temperature, and by its motions. Rather less than 3/4 of the surface of the globe, or about 144,712,000 square miles, are covered by the irregular sheet of water known as the sea. Within the last few decades, much new light has been thrown upon the depths, temperatures, and biological conditions of the ocean basins, more particularly by the Lightning, Porcupine, Challenger, Tuscarora, Blake, Gazelle, and other expeditions fitted out by the British, American, German, Norwegian, and Swedish governments. The water of the ocean is distinguished from ordinary terrestrial waters by a higher specific gravity, and the presence of so large a population of saline ingredients as to impart a strongly salt taste. The average density of seawater is about 1.026, but it varies slightly in different parts even of the same ocean. The greater density of seawater depends, of course, upon the salts which it contains in solution. At an early period in the Earth's history, the water now forming the ocean, together with the rivers, lakes, and snowfields of the land, existed as vapor, in which were mingled many other gases and vapors, the whole forming a vast atmosphere surrounding the still intensely hot globe. Under the enormous pressure of the primeval atmosphere, the first condensed water might have had a temperature little below the critical one. In condensing, it would carry down with it many substances in solution. The salts now present in the seawater are to be regarded as particularly derived from the primeval constitution of the sea, and thus it may be inferred that the sea has always been more or less saline. But it is manifest that, whatever may have been the original composition of the oceans, they have for a vast section of geological time been constantly receiving mineral matter in solution from the land. Every spring, brook, and river removes various salts from the rocks over which it moves, and these substances, thus dissolved, eventually find their way into the sea. Consequently, seawater ought to contain more or less traceable proportions of every substance which the terrestrial waters can remove from the land. In short, of probably every element present in the outer shell of the globe, for there seems to be no constituent of the earth which may not, under certain circumstances, be held in solution in water. The average proportion of saline constituents in the water of the great oceans far from land is about 3.5 parts in every 100 of water, and the proportions of the different chemical elements in the composition of the waters of the ocean as a whole are much as follows. Oxygen, 85.79. Hydrogen, 10.67. Chlorine, 2.67. Sodium, 1.14. Magnesium, 0.14. Calcium, 0.05. Potassium, 0.04. Sulfur, 0.09. Bromine, 0.008. And carbon, 0.002. Within the atmospheric and oceanic envelopes lies the inner solid globe, the only portion of it which, rising above the sea, is visible to man, and forms what is termed land, occupies rather more than 1/4 of the total superficies of the globe, or about 55 million square miles. It was formerly the prevalent belief that the exterior and interior of the globe differ from each other to such an extent that, while the outer parts are cool and solid, the vastly more enormous inner intensely hot part is more or less completely liquid. Hence, the term crust is applied to the external rind in the usual sense of that word. This crust was variously computed to be 10, 15, 20, or more miles in thickness. The Earth's crust is composed of mineral matter in various aggregates included under the general term rock. A rock may be defined as a mass of matter composed of one or more simple minerals, having usually a variable chemical composition, with no necessarily symmetrical external form, and ranging in cohesion from mere loose debris up to the most compact stone. Granite, lava, sandstone, limestone, gravel, sand, mud, soil, marl, and peat are all recognized in a geological sense as rocks. Direct acquaintance with the chemical constitution of the globe must obviously be limited to that of the crust, though by inference it may be possible eventually to reach highly probable conclusions regarding the constitution of the interior. Chemical research has discovered that some 75 simple or as yet undecomposable bodies, called elements, in various proportions and compounds, constitute the accessible part of the crust. Of these, however, the great majority are comparatively of rare occurrence. The crust is mainly built up of about 20 elements, which may be arranged in two groups, metalloids and metals. Of the metalloids, oxygen and silicon represent 75% of the matter in the world, hydrogen, carbon, phosphorus, sulfur, chlorine, fluorine, and nitrogen being less than 1.5% altogether. While among the metals, aluminum is 7.45%, iron 4.2%, calcium 3.25%, magnesium 2.35%, potassium 2.35%, sodium 2.40%, and titanium, manganese, beryllium, barium, strontium, chromium, nickel, and lithium together are less than 1/2%. Of the other elements, upwards of 50 in number, the proportions are so small that probably not one of them equals as much as 1/100% of the whole crust. Yet they include gold, silver, copper, tin, lead, and the other useful metals, iron excepted. It will be observed that of the accessible part of the globe, over 3/4 consist of metalloids and less than 1/4 of metals. It is also interesting to note that 97% of the crust is made up of the 10 most abundant elements, that is, of the 3 first metalloids and the 7 first metals. Silicon is never found free, but always combined with oxygen. Comparatively, few of the elements occur free, but occur in more or less complex compounds with one or more others. The combinations which enter most largely into the composition of the Earth's crust can be determined from the collation of a sufficiently large number of chemical analyses of the more representative rocks of the Earth's crust. Such a determination has been made by Mr. F. W. Clark from the mean of 830 analyses of typical samples from the older or primitive part of the crust, and is expressed. The following are the chief: silica 59.71%, alumina 15.41%, ferric oxide 2.63%, ferrous oxide 3.52%, lime 4.90%, magnesia 4.36%, potash 2.80%, soda 3.55%, water 1.52%, titanic acid 0.60%, and phosphoric acid 0.22. In a broad view of the arrangement of the chemical elements in the external crust, the speculation of Durocher may be noticed here. He regarded all rocks as referable to two layers or magmas coexisting in the Earth's crust, the one beneath the other, according to their specific gravities. The upper or outer shell, which he termed the acid or siliceous magma, contains an excess of silica and has a mean density of 2.65. The lower or inner shell, which he called the basic magma, has from 6 to 8 times more of the earthly bases and iron oxides, with a mean density of 2.96. To the former, he assigned the early plutonic rocks, granite, felsite, etc., with the more recent trachytes. To the latter, he relegated all the heavy lavas, basalts, and diorites. The rocks of the Earth's crust are made up of compounds of the elements which have just been mentioned. These compounds geologists call minerals. Scott, in his Introduction to Geology, defines a mineral as a natural, inorganic substance which has a homogeneous structure, definite chemical composition and physical properties, and usually a definite crystal form. The number of known minerals is large and constantly increasing, but only a few enter in any important way into the constitution of the Earth's crust. Having considered the composition of the atmosphere, sea, and solid crust, the general features of the Earth's surface require attention. The late Professor Dana of Yale briefly summarizes the important physical features of the Earth in his textbook of Geology, wherein he says, "The Earth has a circumference of 24,899 miles. Its form is that of a sphere flattened at the poles, the equatorial diameter, 7,926 miles, being about 26 2/3 miles greater than the polar diameter. About 8/11ths of the Earth's surface, or 144 million square miles, is depressed below the rest and occupied by the sea. This sunken part of the crust is called the oceanic basin, and the large areas of land are called the continents or continental plateaus. The area of dry land is about 52,745,000 square miles. Nearly 3/4 of the land is situated in the northern hemisphere, and very nearly 3/5 of the oceanic basin is in the southern hemisphere. The dry land may be said to be grouped about the North Pole, and to stretch southward in two masses, an oriental, including Europe, Asia, Africa, and Australasia, and an occidental, including North and South America. The ocean is gathered in a similar manner about the South Pole, and extends northward in two broad areas separating the Occident and Orient, namely the Atlantic and Pacific Oceans, and also in a third, the Indian Ocean, separating the southern prolongations of the Orient, namely Africa and Australasia. The Orient is made, by this arrangement, to have two southern prolongations, while the Occident, or America, has but one. This double feature of the Orient accords with its great breadth, for it averages 6,000 miles from east to west, which is far more than twice the mean breadth of the Occident, 2,200 miles. The inequality of the two continental masses has its parallel in the inequality of the Pacific and Atlantic Oceans, for the former, 6,000 miles broad, is more than double the average breadth of the latter, 2,800 miles. The northern portion of the Orient, or Europe and Asia combined, make one continental area, Eurasia. Its general course is east and west. The northern portion of the Occident, North America, is elongated from north to south. The mean depth of the oceanic depression is about 14,000 feet, and the mean height of the land, according to Murray, 2,252 feet. The greatest depth reached by soundings south of the Friendly Islands is 30,930 feet. The greatest height on the land, Mount Everest of the Himalayas, is 29,000 feet. Hence, the interval between the extremes of altitude and depression is over 11 miles. If the continental plateaus and the floor of the ocean were graded to a common level, the ocean would still have a depth of about 10,000 feet. The mean height of Europe is 939 feet, Asia 3,189 feet, Africa 2,021 feet, Australia 805 feet, North America 1,888 feet, South America 2,078 feet. The mean depth of the great oceans are of the North Atlantic 15,000 feet, North Pacific 16,000 feet, South Atlantic and South Pacific, and probably the Indian Ocean about 13,000 feet. The form of the ocean's bed has been fairly accurately determined. From north to south, along the middle of the Atlantic, there is a wide zigzag ridge or plateau, conforming nearly in trend to the American coast. It lies at a depth of 6,000 to 12,000 feet, while on either side the bottom slopes away to depths mostly between 15,000 and 20,000 feet. In the area of 4,000 fathoms and over, situated north of the island of Puerto Rico, the United States Coast Survey steamer Blake found in 1883 a depth of 27,366 feet. This greatest depth and large areas of deep water exist in the western part of the ocean. In the Pacific Ocean, a shallow area extends with little interruption from the Malay Archipelago southeastward, beyond the Paumotu Islands, and thence northeastward to the Isthmus of Panama, southeastward to Patagonia, and southward to the Antarctic. The deepest parts of this ocean also are in its western half. One deep area is east of Japan, another south of the Ladrones, others near the Friendly Islands. Northward in the northern hemisphere, the ocean shallows rapidly. The depth in the Bering Strait is not over 150 feet, and between Great Britain and Iceland, it does not exceed 6,000 feet and is mostly under 3,000 feet. The ocean's bottom has no steep ridges like those of ordinary mountain scenery, but broad elevations exist in some parts, as found in the surroundings of the Tuscarora between the Hawaiian Islands and Japan. Besides these, there are many mountain ranges rising somewhat abruptly from the depths, having the islands of the ocean as their summits, which rival in length those of the continents. The Hawaiian range, if the coral islands in the line of the volcanic islands are included, has a length of 2,000 miles, and it rises steeply from depths of 15,000 to 18,000 feet. The mountains of Hawaii have a height above the ocean of nearly 14,000 feet, and a depth of 17,000 feet was found but 50 miles south of the island, thus making the whole height nearly 31,000 feet. The islands of the tropical Pacific have together an island chain about 5,000 miles long, and they are the tops of a mountain chain of this great length. Along the oceanic borders, the sea is often, for a long distance out, quite shallow, because the continents continue on underwater with a nearly level surface. Then comes, usually at a depth of about 100 fathoms or 600 feet, a rather sudden slope to the deep bed of the ocean. This is a case off the eastern coast of the United States, east and south of New England. Off New Jersey, the deep water begins along a line about 80 miles from the shore. Off Virginia, this line is 50 to 60 miles at sea, and thus it gradually approaches the coast to the southward, while to the northward it continues 80 to 100 miles off from the New England coast, and passes far outside of Nova Scotia and Newfoundland. The slope of the bottom for the 80 miles off New Jersey is only 1 foot in 700 feet. The true boundary between the continental plateau and the oceanic depression is the commencement of the abrupt slope. The same abrupt slope near the 100-fathom line exists in the Gulf of Mexico. The British Islands are situated on a submerged portion of the European continent and are essentially a part of that continent, the limit of the oceanic basin, the 100-fathom line, being 50 to 100 miles outside of Scotland and Ireland and extending south around the Bay of Biscay. West of the English Channel, the depth increases, in a distance of only 10 miles, from 100 fathoms to 2,000. New Guinea, in a similar way, is proved to be a part of Australia. Such facts occur on most coasts, and they teach that the oceanic depression is generally separated from the continental plateaus by a well-defined outline. The surface of the continent comprises plains or lowlands, plateaus or tablelands, and mountain ridges. The mountain ridges may rise either from the lowlands or the plateaus. The plateaus are large areas of approximately level surface at an altitude of 1,000 feet or more above the sea. They are often part of the great mountain chains, lying between the ridges, or forming the mountain mass out of which the ridges rise. For example, the regions of northern and southern New York are plateaus, the former averaging 1,500 feet in height, the latter 2,000 feet, situated on the western borders of the Appalachian chain. And the same is true of the Cumberland tableland in Tennessee. Between the Sierra Nevada and the Wasatch, there is a plateau of vast extent called the Great Basin, having the Great Salt Lake in its northeastern portion. Its height above the sea averages 4,000 feet. The Humboldt Mountains and other ranges rise out of it. It continues northward into British America and southward into Mexico. The eastern part of New Mexico, with the western part of Texas, is a plateau of about the same elevation, called the Llano Estacado. The desert of Gobi, between the Altai and the Kunlun range, is a desert plateau about 4,000 feet high, while the plateau of Tibet, between the Kunlun range and the Himalayas, is 11,500 to 13,000 feet above the sea. Persia and Armenia constitute another plateau. These examples are sufficient to explain the use of the term. The continents are constructed on a common model. They have high borders and a low center, and are, accordingly, basin-shaped. North America has the Appalachians on the eastern border, the Cordillera on the west, and between these, the low Mississippi Basin. South America, in a similar manner, has the Andes on the west, the Brazilian Mountains on the east, and other heights along the north, with the low region of the Amazon and La Plata making up the larger part of the great interior. In the Orient, there are mountains on the Pacific side, others on the Atlantic, and, again, the Himalayas on the south face the Indian Ocean, and the Altai Mountains face the Arctic seas. Between the Himalayas, or rather the Kunlun Mountains, which are just north, and the Altai, lies the plateau of Gobi, which is low compared with the enclosing mountains, and farther west there are the lowlands of the Caspian and Aral, the Caspian lying even below the level of the ocean. The Urals divide the 6,000 miles of breadth into two parts, and so give Europe some little title to its designation as a separate continent. West of their meridian, there are again extensive lowlands over middle and southeastern European Russia. In Africa, there are mountains on the eastern border and on the western border south of Guinea. There are also the Atlas Mountains along the Mediterranean and the Kong Mountains along the Guinea coast, and the interior is relatively low, although mostly 1,000 to 2,000 feet in elevation. In Australia, also, there are highlands on the eastern and western borders, and the interior is low. All the continents are, therefore, constructed on the basin-like model. There is a second great truth with regard to the continental reliefs. The highest border faces the largest ocean. Each of the continents sustains the truth announced. North America has its great mountains, the Cordillera, on the side of the great ocean, the Pacific, and its small mountains, the Appalachians, on the side of the small ocean. South America also has its highest border on the west. The Orient has high ranges of mountains on the east, or the Pacific side, and the lower ranges, as those of Norway and other parts of Europe, on the west, and the Himalayas face the great Indian Ocean, while the smaller Altai range faces a small northern ocean. In Africa, the mountains on the side of the Indian Ocean are higher than those on that of the Atlantic. In Australia, the highest border is on the Pacific side, for the South Pacific fronting East Australia is greater than the Indian Ocean fronting West Australia. Hence, the basin-like shape before illustrated is that of a basin with one border much higher than the other, and with the highest border on the side of the largest ocean. The features described have a vast influence in adapting the continents for man. America has its highest borders in the far west, with all its great plains and great rivers inclined toward the Atlantic. For through the Gulf of Mexico, the whole interior, as well as the eastern border, has its natural outlet eastward. The Orient, instead of rising into the Himalayas on the Atlantic border, has its great heights in the remote east. And its vast plains, even those of Central Asia, have their natural outlet westward, over Europe and through the Mediterranean, or toward the same Atlantic Ocean. Thus, as Professor Guyot has said, the vast regions of the world, which are best fitted for man by their climate and productions, are combined into one great arena for the progress of civilization.
Dynamical geology investigates the process of change at present in progress upon the Earth, whereby modifications are made on the structure and composition of the crust, on the relations between the interior and the surface, as shown by volcanoes, earthquakes, and other terrestrial disturbances, on the distribution of land and sea, on the outlines of the land, on the form and depth of the sea bottom, on marine currents, and on climate. Bringing together the whole range of geological activities, it leads to precise notions regarding their relations to each other and the results which they achieve. In other words, the present order of things must be employed as a key by means of which to decipher the hieroglyphics of the past, and proceed from what may be directly observed to past changes which can only be inferred. We might assume, says Scott in his Introduction to Geology, that the present was so radically different from the far distant past that the one could throw no light upon the other. Such an assumption, however, would be most illogical, for there is nothing to support it. There is no reason to imagine that physical and chemical laws are different now from what they have always been, and the more we study the earth, the more clearly we perceive that its history is a continuous whole, determined by factors of the same sort as are now continuing to modify it. Some of these forces, however, act with greater efficiency at the present time than they did in the past, others with less. The dynamical agencies may primarily be divided into two classes. One, the subterranean agencies, which act, or at least originate, at considerable depths within the earth, and two, the surface or superficial agencies, whose action takes place at or near the surface of the earth. The former are due to the inherent energy of the earth, and their seat is primarily subterranean, though their effects are very frequently apparent at the surface. These agencies are also called igneous, from ignis, fire, which is a misnomer, but the term is nevertheless in common use. The surface agents, including the circulation of the winds and waters, the changes of temperature, and the activities of living beings, all depend upon the sun's energy, and were that withdrawn, only such changes as are brought about by the earth's internal heat could continue in operation. Some of the agencies that shall be considered may seem, at first sight, to be very trivial in their effects, but it must be remembered that they appear so only because of the short time during which they can be observed. For enormously long periods of time they have been steadily at work, and their cumulative effects must not be left out of account in estimating the forces which have made the earth what it is now. No human eye has ever witnessed the birth of a mountain range, or has seen the beds of solid rock folded and crumpled like so many sheets of paper, or observed the processes by which a rock is changed in all its essential characteristics, metamorphosed, as it is technically called. Yet these things are continually being accomplished in nature's workshop. All such problems, however, must be discussed in connection with structural geology. The logical order of treatment of these subjects is to begin with the subterranean agencies, because the most ancient rocks of the earth's crust were doubtless formed by these forces, and the circulation of matter upon and through the crust started originally from igneous rocks. These agencies fall naturally into two great groups: diastrophism, or movements of the earth's crust, and volcanism, or the phenomena of volcanoes, geysers, etc., while a third group, earthquakes, is intimately associated with each of the others, but on account of its great importance will require separate treatment. Crustal movements to be discussed here may be distinguished as 1. Warping, which is a broad, gentle curving of the surface, upward or downward. 2. Direct upheaval or depression, with fracturing and dislocation of the rocks, which may be accompanied by a tilting of the strata. Diastrophic movements of this class are almost, if not quite, invariably associated with earthquakes and can be most conveniently studied in connection with the latter. Permanent changes of level frequently accompany earthquakes, but these are sudden and appear to be nearly always the result of dislocation or faulting. By change of level, in the general sense, is meant the gradual elevation or subsidence of land, with reference to the sea, over considerable areas. Such movements are very slow, and hence are apt to escape observation, so that there is much dispute as to the facts and still more as to their interpretation. But there is an abundance of indisputable evidence showing that considerable changes in level have been effected even since the dawn of civilization. On certain coasts long inhabited by civilized man, ancient structures like quays and bridges, which were built in the water, may now be found high above it. Such changes have been noted in the Mediterranean lands, especially in southern Italy and the island of Crete. The so-called Serapeum at Pozzuoli near Naples is a famous and much discussed example of repeated oscillations upward and downward. This structure was built in Roman times and probably began to sink while still in use, as appears from the two ancient pavements, one above the other. 3 large monolithic columns of marble, about 40 feet high, are still standing erect, and on each of them is a belt about 10 feet above the ground and 9 feet wide, honeycombed by the boring mollusk Lithodomus, which still abounds in the neighboring bay, and many of the shells were actually found in the columns. Evidently, the building was once submerged to a depth of nearly 20 feet, and when underwater, the columns were attacked and perforated by the mollusk. Just when the re-elevation began is not definitely known, but it was probably completed in 1538, when a volcanic eruption in the neighborhood resulted in the formation of Monte Nuovo. For nearly a century past, a slow movement of subsidence has been going on. Raised beaches filled with the remains of marine animals are a decisive proof of a rise of the land or a fall in the sea, and evidence of a similar kind is given by raised coral reefs. The eastern coast of North America shows marks of relatively late elevation, increasing in amount northward. At the mouth of the Connecticut, the highest beach is 40 to 50 feet above sea level. At Boston, it is 75 to 100 feet. On the coast of Maine, it is 200, and on that of Labrador, 500 feet. On the eastern shore of Hudson's Bay, the marine terraces and beaches extend up to 700 feet above sea level. In the geological period Pleistocene immediately preceding the recent one, several immense lakes existed in the interior of North America, some around the basins of the present Great Lakes, others in Utah and Nevada. The ancient shorelines of these vanished lakes may still be seen, for the most part in admirable preservation. When first formed by the action of the waters, these beaches must have been level, but accurate surveys show that they are no longer so, but have undergone extensive warpings. As ancient structures on long inhabited coasts sometimes show elevation, they likewise sometimes show depression. On the north coast of Egypt, ancient rock-cut tombs are now visible beneath the waters of the Mediterranean. South of Stockholm in Sweden, the remains of an ancient hut were found in place, 65 feet below the surface, buried in marine deposits which contain shells of the same species now living in the Baltic. On the west coast of Greenland, the sinking is so rapid as to have attracted the attention of the natives. The sea bottom south of Long Island must once have been dry land, because a river flowing into the sea cannot excavate the sea bottom below the level of its mouth. The ancient channel of the Hudson has been treated by soundings out to the edge of the continental platform, more than 100 miles southeast of Sandy Hook. In the same manner, the channel of the St. Lawrence may be followed out through the Straits of Belle Isle, and that of the Congo extends out 70 miles from the west coast of Africa, with a depth of nearly 1,000 fathoms. What are known as earthquakes are caused by rapid vibrations of the Earth's crust due to some sudden shock in the Earth's interior. The displacements, that is, the amplitude of the vibrations, in the great majority of earthquakes is only a fraction of a millimeter. When it exceeds 4 or 5 millimeters, the quake is destructive. The greatest destruction is wrought in instances where the buildings are built upon loose foundations or upon made ground. Steel-framed structures founded upon bedrock do not fall easily, for they vibrate with the rock. Centuries ago, the Chinese devised an instrument that detected these vibrations of the Earth's crust, for the majority of them can only be detected by instruments. Their device, as have all successful subsequent ones, depended on the inertia of a suspended weight or pendulum. The delicately poised weight alone is unaffected by the vibrations. A paper under it moves with the tremblings of the crust, and a pen held by the pendulum records the movement. In the Chinese device, their pendulum merely displaced little bullets which were carefully supported. Modern instruments, called seismographs, do not only tell when an earthquake has occurred, but they record the tremors, different pendulums recording the various components, horizontal and vertical, of the movements. In the cases of a violent disturbance, communication of all kinds is often cut off, but there are now seismographs in all parts of the world, and by comparing the times at which various instruments recorded similar phases of the shock, the center of the disturbance can generally be accurately determined. The study of seismographic records has brought to light many highly significant facts, among others, that minute and insensible tremors of the earth are almost incessant, but some, at least, of these tremors are due to atmospheric changes, and it is not known how large a proportion of them are of subterranean origin. Another very important result of the seismographic observations is that when a very distant earthquake is registered, 3 series of waves are indicated, that is, the first and second phases of the preliminary tremors and the larger waves of the main shock. Those first to arrive, called the preliminary tremors, are believed to be transmitted through the mass of Earth along the chord of the arc included between the point of origin and the point of observation. The waves of the third series are longer and slower, that is, of greater amplitude and period, and constitute the main shock. They are believed to follow the curvature of the Earth. Sensible earthquakes are numerous, not less than 30,000 being the estimated number per annum. Of course, the great majority of these are very light. It would be just to say that the crust quivers constantly. While any part of the Earth's surface may be visited by earthquakes, there is a very great difference between different regions in regard to their seismicity, that is, the frequency and violence of the shocks which affect them. The main seismic regions, when platted upon a map, are found to be arranged in 2 great circle belts, one of which encloses the Pacific Ocean and the other girdles the whole Earth. The latter includes the Mediterranean region, the Azores, the bed of the Atlantic westward from the Azores to the West Indies, those islands themselves, Central America, Hawaii, Japan, China, India, Afghanistan, Persia, and Asia Minor. Although earthquakes are commonly perceptible upon the land, the most frequent seats of disturbance are in the bed of the sea. In the sea there are regions quite free from quakes and others of a high degree of seismicity, but quakes also occur in an isolated and scattered manner. Submarine cables are frequently interrupted at the same points. Thus, the cable from the Lipari Islands to Sicily has been broken 5 times at the same point. A great earthquake usually begins suddenly and without warning. A rumbling sound, quickly becoming a loud roar, accompanies or slightly precedes the movement of the ground, which is at first a trembling, then a shaking, and finally a rapid swaying, wriggling motion, describing a figure 8, which is extremely destructive and overthrows the buildings affected, and even in the open country it is impossible to keep one's feet. The surface of the ground has been repeatedly observed to rise in low, very swift-moving waves, somewhat like those on the surface of water, upon the crests of which the soil opens in cracks, closing again in the wave troughs. When the earth waves traverse a forested region, the trees sway violently from side to side, like a field of ripe grain in the breeze. In the details of movement, earthquakes differ greatly from one another. Sudden and extremely violent vertical shocks may come from below, or the surface may writhe and twist in every direction instead of rolling in waves. There may be only a single shock or many successive ones. Strictly speaking, the geological effects of earthquakes are of less importance than is usually supposed. The violent shaking of the surface often brings about great landslips in mountain regions, which precipitate enormous masses of earth and rock from the heights down into the valleys. In all of the more violent quakes, cracks and fissures of the ground are formed, which may close again or remain open, and may show a lineal, curved, zigzag, or radiating arrangement. Through these fissures, great quantities of water and sand are often forced up from below and form little sand craters or water-filled funnels on the surface. Frequently, the fissures assume the character of faults or dislocations, one side being raised, the other depressed, so that long scarps or low cliffs are left standing. In the San Francisco earthquake of 1906, two long lines of parallel faults were formed, with varying throw up to 20 feet. A very common result of earthquakes is a change in the circulation of underground waters. Wells and springs go dry, while other springs are formed in new places, or old ones may be increased in volume. The changes in the form of the land surface produce corresponding changes in surface drainage. Rivers are diverted into new channels or dammed into lakes, while streams intersected by fault scarps form new cascades. The recent earthquake, which occurred at the extremity of the Italian peninsula, was at first seismologically explained as the propagated effect of a fault slip. It was not the eruptive outburst of Etna, according to Sir Norman Lockyer, that set the earth quivering in the vicinity, but the prolonged tension of the crust, a sudden snap, an abrupt settlement, and then the waves of the quake. The celebrated geologist, Professor Edward Suess of Vienna, expresses himself very pessimistically regarding the outlook for the near future. According to his theory, the Calabrian and Sicilian shocks do not result from volcanic outbreaks anywhere, but were occasioned by a general sinking. Should this settling down continue, further catastrophes are likely to ensue. In studying the causes of earthquakes in general, they are usually divided into two classes, volcanic and tectonic, though it is often impossible to determine to which of the two classes a given earthquake should be referred. The volcanic earthquakes, which are closely associated in time and space with volcanic eruptions, are due to steam explosions and to the struggles of the rising lava within the earth to escape. Tectonic earthquakes are believed to be due to stresses in the interior of the earth, which, when suddenly yielded to by the rocks, cause the jar and shock which generates the earthquake. No entirely satisfactory hypothesis has been advanced to account for the origin of the stresses referred to above. The explanation usually accepted is that the Earth is slowly contracting on account of the loss of heat, and that the crust, which must follow the shrinking interior, is being crowded into a smaller space, with resultant ruptures and shocks. On the other hand, it is contended by some geologists that all earthquakes are essentially volcanic in origin. The stresses induced by the changing of the Earth's axis also has been put forward as an explanation. Many geologists attribute the recent earthquake at Messina to the explosion of steam, according to the theory just given prominence by Dr. T.J.J.C. of the Naval Observatory on Mare Island, to the effect that all great earthquakes are caused by the explosive force of steam generated by the percolation of seawater to the molten or red-hot rocks far below the Earth's surface. He asserts that the so-called waves following great earthquakes are not really tidal. They are produced by seismic disturbances of the sea bottom and should be called seismic sea waves. A seismic wave, explains Dr. C., is due to a sinking of the sea bottom at some distance from the shore. When this happens, the water, of course, flows in from all sides to fill the depression. Then, when the currents meet at the center and raise a ridge by their mutual impact, the ridge collapses under gravity and sends the first great wave ashore. Where the ridge of water once was, he says, a second depression in the sea level is thus developed. The water again flows as in the first case, and the process keeps on repeating itself. On June 15, 1896, the northern shores of Japan were visited by terrible earthquake shocks, which were recorded on seismographs in Europe. The disturbance originated beneath the Tuscarora Deep. This oceanic abyss, which reaches a depth of 4,600 fathoms or more than 27,000 feet, is known as the worst earthquake region in the world. On the Japanese coast, as on that of South America, the water first withdrew from the shore and later returned in a great wave. Along a region 70 miles in length, the coast villages were washed away and 30,000 people perished from the earthquake and the inundation. In other instances, the water rises suddenly, overflows the coast, and washes ships inland without any previous withdrawal from the shore. For instance, on December 29, 1854, the city of Shimoda in Japan was overwhelmed by a sudden inrush of the sea about an hour after a violent earthquake. Seismic waves of this class are produced by an upheaval of the sea bottom, which lifts the overlying water bodily upward, causing it to rush in upon the shore. In summing up, Dr. C says that the so-called tidal waves that follow violent earthquake shocks are due either to the sinking or to the elevation of the sea bottom, and that earthquakes themselves are due to the secular leakage of the ocean bottoms. The great depth and the enormous pressure of the seawater, with the aid of capillary forces, drive it through the rocky crust of the earth till it comes to the intensely hot strata some 20 miles below the surface. The earth in many places is at a high temperature inside, and steam develops under the crust. When the pressure of the steam accumulates, it finally shakes the solid crust until it gets relief through some opening. Practical people, notably insurance companies, are asking the scientists whether seismic disturbances have not a common and determinable origin, and if their cause can be ascertained, if they will ever be able to foretell their occurrence. They are questions which are being carefully considered, notably by Professor H. H. Turner, who in a recent paper on the times and places of earthquakes is somewhat pessimistic. It has been noted that some 30,000 shocks are detected annually by the recording instruments. Of all these, only 60 are world-shaking and observable from a distance. The two rings which the earthquake districts make when plotted on the globe also has been referred to. Professor Milne and others attach peculiar significance to this geographical distribution. Now, this is not merely a convenient geographical summary, but a physical fact of virtual importance, according to recent researches by Professor Jeans. In a remarkable paper read before the Royal Society, he gave reasons for believing that the Earth is not so absolutely a sphere or spheroid, but is slightly of pear shape. Under gravitational stress, it is continually approaching the spheroidal form. The pear is being crushed into a sphere by its own attraction, and the result is a series of earthquakes which will naturally occur in the weakest places. The speculation, for it is little more as yet, possesses no small degree of interest. Also, Professor Turner, dealing with the distribution of earthquakes in time, suspects that there must be a direct connection between polar movement and the strain on the crust of the Earth. For many years it has been observed that there are slight but irregular changes in latitude, or, in other words, the axis of the Earth does not always point in the same direction. The world top is not spinning truly, but it wobbles slightly. When the change in direction of its axis is sharp, large earthquakes have been frequent. If a swiftly moving body is, so to speak, compelled to turn a corner, that it should be subjected to strains which might result in yielding is easily conceivable. A shifting of the Earth's axis, even to the slightest degree, would impose a great strain upon some parts of the Earth's crust, and this might explain earthquakes and in turn lead to appreciable results in foretelling them. But, to use the words of Professor Simon Newcomb, earthquakes are due to a shifting of the Earth's strata, but what causes that shifting is not positively known. The general theory hitherto has been that the shifting is due to the gradual lessening of the Earth's surface. That may be a fallacy, but Professor Milne has yet to establish his hypothesis. Nevertheless, the great prestige of Sir Norman Lockyer's name has been given to the Milne theory, that is, that the earthquake is a natural phenomenon resulting from the failure of the Earth to swing true upon its axis. The great seismic disturbances of the past few years tend, this expert thinks, to support the theory advanced by Professor Milne. This would yield the inference that it is possible to calculate the frequency of earthquakes in the light of their suspected cause. However much announcements of this nature may appeal to the scientific mind, says Professor Milne, the layman requires something more definite. If not to the minute, he would at least like to know the day on which an earthquake is to occur. The science of seismology may never become so precise as all that, but when the factor of causation is given, when it is known for certain whether or not the sun spots or the shrinkage of the globe or the alteration of the direction of the Earth's axis must be given credit for the earthquake, the chief problem of the seismological prophet will have been practically solved.
A volcano is usually a conical mountain or hill with an opening or crater through which various solid, molten, or gaseous materials are ejected. The essential part of the volcano is the opening or vent, and some volcanoes consist of almost nothing else. It is known that at least a part of the interior of the Earth at a certain depth is hot, and a great part of it is actually or potentially molten. Thus, a volcano might be considered as a connection between the interior and the surface, or as a chimney over an especially active part of the interior. The number of volcanoes now active may be estimated at about 328, of which rather more than one-third are situated in the continents and the remainder on islands. The active volcanoes are not scattered haphazard over the surface of the globe, but are arranged in belts or lines, which bear a definite relation to the great topographical features of the Earth, as well as to the seismic belts. Two of these belts together encircle the Pacific Ocean. A third band occupies a ridge in the eastern bed of the Atlantic, from Iceland to beyond St. Helena, from which arise numerous volcanic islands and submarine vents. The phenomena displayed by different volcanoes, or even by the same volcano at different times, vary greatly. It often seems difficult to believe that similar forces are involved, and that the divergences are due merely to different circumstances attending the outbreak. A careful comparison, however, of the varying phenomena brings to light a fundamental likeness in them all. Some vents, like Stromboli in the Mediterranean, are in an almost continual state of eruption of a quiet kind. Others, like Vesuvius, have long periods of dormancy, broken by eruptions of terrible violence. The first recorded eruption of Vesuvius, which occurred in 79 AD and is described in two letters written to Tacitus by the younger Pliny, was of the explosive type. In this frightful paroxysm little or no molten lava was ejected, but so enormous was the quantity of ashes that at Misenum, across the Bay of Naples, the sun was darkened, as Pliny reports, not as on a moonless, cloudy night, but as when the light is extinguished in a closed room. In order not to be covered by the falling ashes and crushed by their weight, it was necessary to rise often and shake them off. The explosive type of eruption is exhibited in its extreme form by several of the East Indian volcanoes, and preeminently by Krakatoa, the eruption of which in 1883 was the most frightful ever recorded. This volcanic island, situated in the Strait of Sunda, was little known, except that it had been in eruption in 1680. The catastrophe occurred in August, when, besides the fearful devastation caused by the disturbances of the sea on the coasts of Sumatra and Java, the island itself was almost annihilated. The force of the explosion produced waves in the atmosphere which were propagated around the whole earth, and the first one was observed in Berlin 10 hours after the explosion. The ejected materials were all fragmentary and of an incredible volume. Ashes were distributed over an area of 300,000 square miles, the greater part falling within a radius of 8 miles around the island. Stretches of water that had an average depth of 117 feet were so filled up as to be no longer navigable. Enormous masses of pumice floated upon the sea and stopped navigation except for powerful steamers. The flaming red sunsets which characterized the autumn and winter of 1883 to 1884 have been very generally ascribed to the refractive effects of the impalpably fine Krakatoa dust. The islands of St. Vincent and Martinique in the Lesser Antilles were devastated by a series of fearful and nearly simultaneous explosions, which in certain important respects differ from those of any other known volcanoes. The volcano of St. Vincent, known as La Soufrière, began breaking out on May 6, 1902, in a series of tremendous steam explosions. May 7, the eruption became continuous, and on the same day occurred the dreadful descending hot blast, a cloud of superheated steam and other gases, mingled with red-hot particles of ash, which rushed down the mountain and destroyed 1,400 human lives. The eruptions, which were repeated at varying intervals and with different degrees of violence for considerably more than a year, were characterized by the absence of lava and by the vast quantity of finely divided ash ejected by the explosions. The eruptions of Mont Pelée in Martinique were actually less violent, but far more destructive to life than those of St. Vincent. On May 2 the ejections of ash became frequent, increasing until the 8th, when a descending cloud of hot vapors and glowing ash swept with terrible velocity down the ravine of the Rivière Blanche upon the city of Saint-Pierre, which, together with its 30,000 inhabitants, was instantly annihilated. The velocity of the air set in motion by the descending cloud was sufficiently great to hurl from its pedestal the great iron statue of Notre-Dame de la Garde, weighing several tons, to a distance of more than 40 feet. It is the descending clouds which lend such an exceptional character to the eruptions of St. Vincent and Martinique, but Mont Pelée also displayed certain other peculiar phenomena. While no lava streams were produced, very stiff and viscous lava appeared at the summit, filling up the old crater and forming a steep cone, through which protruded a lofty obelisk or spine, which, thrust up from below, grew irregularly in height, as it continually lost material by scaling off the top and sides. Eventually it fell altogether. In all eruptions of the explosive kind, a few typical examples of which are described above, the active agency is obviously exploding masses of intensely heated and compressed steam, and all such eruptions are accompanied by gigantic steam clouds, which, condensing in the atmosphere, fall in rains of torrential volume and violence. The hot water thus produced mingles with the volcanic ash in the air and on the ground, forming streams of hot mud, which are often more destructive than the lava flows themselves. When cold, the mud sets into quite a firm rock, called tuff. The opposite extreme of volcanic activity from the explosive type is to be found in the volcanoes of the Sandwich Islands, such as Mauna Loa and Kilauea. Here the eruptions are usually not heralded by earthquakes. The lava is remarkably fluid and simply wells up over the sides of the crater, pouring down the sides of the mountain in streams which flow for many miles. More commonly, the walls of the crater are unable to withstand the enormous pressure of the lava column, and the molten mass breaks through at some level below the crater, rising through the fissure in giant fountains, sometimes 1,000 feet high. Even in the ordinary activity of Kilauea, jets of 30 and 40 feet in height are thrown up. hardly any ashes or other fragmental products are formed. And though the clouds of steam, the invariable accompaniments of volcanic outbursts, are present, yet the quantity of steam is relatively less than in those volcanoes in which explosions occur. Between such extremes as the Hawaiian volcanoes on the one hand and the explosive East Indian type, Krakatoa, on the other, may be found every intermediate gradation. Thus, though occasionally breaking out with violence, Stromboli has been in a state of almost continuous activity for more than 2,000 years, and is for long periods in such exact equilibrium that barometric changes have a marked effect upon its activity, and the Mediterranean sailors make use of it as a weather signal. Evidently, one active agent in these phenomena is imprisoned steam in its struggles to escape. Different as are the manifestations at various volcanoes, steam is an important cause of the eruption in all cases, though the conditions under which it acts vary widely. In the modern eruptions of Vesuvius, essentially the same phenomena may be observed, but on a far grander and more terrible scale. Earthquakes usually announce the coming eruption, increasing in force until the outbreak occurs. Terrific explosions blow out fragments of all sizes, from great blocks to the finest and most impalpable dust. Inconceivable quantities of steam are given off with a loud roar, which is awe-inspiring in its great and steady volume. A volcano, as its activity wanes, may pass into the solfataric stage, when only volatile emanations are discharged. The well-known Solfatara near Naples, since its last eruption in 1198, has constantly discharged steam and sulphurous vapors. The island of Volcano has now passed also into this phase, though giving vent to occasional explosions. As the result of solfataric action, masses of rock are decomposed below the surface and new deposits of alum, sulfur, sulfides of iron and copper, and layers of silica, etc., are formed above them. The lagoons of Tuscany are basins into which the waters from Soffione are discharged, and where a precipitation of the dissolved salts takes place. Among the substances thus deposited are gypsum, sulfur, silica, and various alkaline salts, but the most important is boracic acid, the extraction of which constitutes a thriving industry. Another class of gaseous emanations betokens a condition of volcanic activity further advanced toward final extinction. In these the gas is carbon dioxide, either issuing directly from the rock or bubbling up with water which is often quite cold. The famous Valley of Death in Java contains one of the most remarkable gas springs in the world. It is a deep, bosky hollow, from one small space on the bottom of which carbon dioxide issues so copiously as to form the lower stratum of the atmosphere. Tigers, deer, and wild boar, enticed by the shelter of the spot, descend and are speedily suffocated. Many skeletons, including those of man himself, have been observed. Death Gulch is the significant name to another example of the accumulation of carbonic acid in Western America. Eruptive fountains of hot water and steam, to which the general name of geysers, i.e. gushers, is given, from the examples in Iceland, which were the first to be seen and described, mark a declining phase of volcanic activity. Iceland has long been famous for its geysers, and a very beautiful series in New Zealand was destroyed by the volcanic eruption in 1886. But probably the most striking and numerous assemblage is that which has been brought to light in the Yellowstone National Park. In this singular region, the ground in certain tracts is honeycombed with passages which communicate with the surface by hundreds of openings, whence boiling water and steam are emitted. In most cases the water remains clear, tranquil, and of a deep green-blue tint, though many of the otherwise quiet pools are marked by patches of rapid ebullition. These pools lie on mounds or sheets of sinter, and are usually edged round with a raised rim of the same substance, often beautifully fretted and streaked with brilliant colors. The eruptive openings usually appear on small, low, conical elevations of sinter, from each of which one or more tubular projections rise. It is from these irregular tube-like excrescences that the eruptions take place. The term geyser is restricted to active openings whence columns of hot water and steam are from time to time ejected. The non-eruptive pools are only hot springs. In the upper firehole basin of the Yellowstone Park, one of the geysers, named Old Faithful, ever since the discovery of the region, has sent out a column of mingled water and steam every 63 minutes or thereabouts. The column rushes up with a loud roar to a height of more than 100 feet, the whole eruption not occupying more than about 5 or 6 minutes. The other geysers of the same district are more capricious in their movements, and some of them more stupendous in the volume of their discharge. The eruptions of the Castle, Giant, and Beehive vents are marvelously impressive. The action of geysers is due to the conditions that subterranean waters have access to hot rocks, as the interior of great lava sheets, retaining a high temperature on account of the poor conductivity of the material, and that the conduit communicating with the surface is so narrow that convection currents cannot be freely established. The heat accordingly increases in the deeper part of the column of water until steam is formed, by whose expansion the cooler waters above are explosively ejected. After an eruption, the water flows back into the underground passages and gradually becomes heated up for another explosion. Heated waters act on the rocks with which they are in contact and decompose them, and, as most rocks, especially volcanic rocks, contain some kind of feldspar, the waters become slightly alkaline through the alkali of the feldspar, and so are enabled to take up silica and make siliceous solutions. The silica taken into solution is deposited again around the geyser in many beautiful forms and makes the bowl or crater from which the waters are thrown out. From a geological point of view, the products of volcanic action form a most important part of the subject, because they contribute largely to the permanent materials of the Earth's crust. Volcanic products are of 3 kinds. 1. Lava, or molten rock. 2. Fragmental material, including blocks, lapilli, bombs, the so-called volcanic ashes, cinders, and the like. And 3. Gases and vapors. A lava is a more or less completely melted rock. The degree of fluidity varies greatly in different lavas, but is rarely, if ever, perfect. The degree of fluidity depends upon several factors, the most obvious of which is temperature. The more highly heated the mass is, the more perfectly will it be melted. The quantity of imprisoned gases and vapors present has also an important effect, and some lavas appear to owe nearly all their mobility to these vapors. A third and most significant factor is the chemical composition. Those lavas which contain high percentages of silica, the acid lavas, are much less readily fusible than the basic lavas, in which the percentage of silica is lower. When a lava stream reaches the surface of the ground, the imprisoned vapors immediately begin to escape and the surface of the molten mass to cool and harden. The surface layers are blown by the steam bubbles into a light, frothy, or slaggy consistency, forming scoriae, or cindery masses. The motion of the lava breaks up this thin crust into loose slabs and blocks, and on the advancing front of the stream these loose masses rattle down over one another in the wildest confusion. The front of a lava stream advances not by gliding over the ground, but by rolling, the bottom being retarded by the friction of the ground and the top moving faster, so that it is constantly rolling down at the curved front end and forming the bottom. Ordinarily, the motion soon becomes very slow, though thoroughly melted masses pouring down steep slopes may, for a short time, move very swiftly. One of the lava floods from Mauna Loa moved 15 miles in 2 hours, and for shorter distances much higher rates of speed have been observed, but this is very exceptional. When lava cools rapidly, it solidifies as a glass, obsidian, or tachylite. When it cools slowly, it forms a truly crystalline rock. Between the extremes are various gradations. If the swiftly cooling portions have been much disturbed by the bubbles of steam and vapors, they are made light and frothy. In some cases, as in pumice, they will float upon water. The lavas which contain large crystals embedded in a finy stone or glassy base are said to be of porphyritic texture. A mass of lava, when it cools and solidifies, necessarily contracts, and since the cohesion of the mass is insufficient to allow it to contract as a whole, it must crack into blocks, separated by fine crevices, which are called joints. Not all the lava produced in and around a volcanic vent can reach the surface. Some of it may be forced horizontally between beds of the surrounding rocks, thus forming intrusive sheets, which, when exposed in sections, may be readily distinguished from surface flows by the fact that they have consolidated under pressure, and hence have no slag or scoriae associated with them. Other portions of the lava will fill up vertical fissures in the volcanic cone or in the underlying rocks, and, solidifying in these fissures, form dikes. Such a fissure, 12 miles in length and filled with molten lava, was observed by Sir Charles Lyell in the neighborhood of Etna.
The division of fragmental products includes all the materials which are ejected from the volcano in a solid state. These are of all sizes and shapes, from huge blocks weighing many tons, down to the most impalpable dust, which the wind will carry for thousands of miles. The more violently explosive the eruption, the greater the proportion of the lava that will be blown into fragments. In such eruptions as that of Krakatoa, all of it is thus dispersed and none remains to form lava flows. Cindiary fragments thrown out of the vent are called scoria, while portions of still liquid lava thus ejected will, on account of their rapid rotation, take on a spheroidal form and are called volcanic bombs. Lapilli are smaller, rounded fragments, and volcanic ash and dust are very fine particles, though with a wide range of variation in size. The term ash is so far unfortunate that it implies combustion, but nevertheless it accurately describes the appearance of these masses. In the immediate neighborhood of the vent, fragments of all sizes accumulate, but the farther from the volcano, the smaller do the fragments become. The coarser masses around the vent form a volcanic agglomerate, in which the fragments are of all shapes and sizes, heaped together without any arrangement. More regular sheets of large angular fragments form volcanic breccia, and these may be seen on a grand scale in the Yellowstone National Park and in many other parts of the Rocky Mountain region. The finer accumulations of ash, formed at a greater distance from the vent, are roughly sorted by the air and often quite distinctly divided into layers, while, as already explained, the muds on drying set into quite a firm rock, called tuff or tufa. It is important to emphasize the vast quantity of material which, in many volcanic eruptions, is brought from the interior of the earth and deposited on the surface. Thus the eruption of Skraptar Jökull in Iceland in 1783 produced an amount of lava which is calculated as exceeding 6 cubic miles in volume. The fragmental materials derived from the great explosion of Krakatoa in 1883 are estimated at 4.3 cubic miles, while for that of Tamboro in 1815, Verbeek gives the almost incredible figures of 28.6 cubic miles. As the ejections flow off or fall more or less symmetrically around the vent, the form of a volcanic peak necessarily tends to become conical. The cone of Vesuvius consists mostly of cinders, and is accordingly steep, nearly 40 degrees. Etna, about 10,000 feet high, and Mauna Loa in Hawaii, nearly 14,000 feet, consisting of lava streams, have an average slope of less than 10 degrees. A tufa cone is midway between these two extremes. From the days when Werner and his followers declared volcanic action to be caused by subterranean beds of inflammable material taking fire, speculation has been constant as to the underlying reasons that promote the heat expressed by volcanoes. The contraction of the earth in consequence of its secular cooling was the conception that met with the greatest favor, especially since Cordier calculated that were the earth to contract 1 millimeter, or 1/25th of an inch, it would suffice to cause 500 eruptions, each ejecting 1,300,000,000 cubic yards of lava. By common consent, geologists have recognized that the source of volcanic energy must be sought in the high temperature of the interior of the globe. They agree that the main proximate cause of the ordinary phase of eruptivity, marked by the copious evolution of steam and the abundant production of dust, slags, and cinders from one or more local vents, is obviously the expansive force exerted by vapors dissolved in the molten magma from which lavas proceed. Whether and to what extent these vapors are parts of the aboriginal constitution of the Earth's interior, or are derived by descent from the surface, is, however, a question on which opinions differ. Professor Skurmak and others have been led to conclude that the gaseous ejections are essentially portions of the original constitution of the magma of the globe, and that to their escape the activity of volcanic vents is due. On the other hand, since so large a portion of the vapor of active volcanoes consists of steam, many geologists have urged that this steam has in great measure been supplied by the descent of water from above ground, as it percolates down cracks and joints and infiltrates through the very pores of the rocks. It appears to be probable that, somewhat like the reservoirs in which hot water and steam accumulate under geysers, the subterranean magma receives a constant influx of water from the surface, which cannot escape by other channels, but is absorbed by the internal magma at an enormously high temperature and under vast pressure. In the course of time, the materials filling up a volcanic chimney are unable to withstand the upward expansion of this imprisoned vapor or water substance, so that after some premonitory rumblings, the whole opposing mass is blown out and the vapor escapes in the well-known masses of cloud. Meanwhile, the removal of the underlying column relieves the pressure on the lava underneath, saturated with vapors or superheated water. This lava, therefore, begins to rise in the funnel until it forces its way through some weak part of the cone or pours over the top of the crater. An obvious objection to this explanation is the difficulty of conceiving that water should descend at all against the expansive force within. But Daubry's experiments have shown that, owing to capillarity, water may permeate rocks against a high counter pressure of steam on the further side, and that, so long as the water is supplied, whether by minute fissures or through pores of the rocks, it may, under pressure of its own superincumbent column, make its way into highly heated regions. The great physicist, Professor Arrhenius of Stockholm, has done much to clarify the views superincumbent upon modern investigation, pointing out the amazing potency of force possessed by water vapor at a temperature far above the critical point. He notes that the magma is charged with this and compares the explosive discharge of lava and viscous matter in volcanic vents to the ascent of water in a geyser. At a depth of 540 meters, the vapor in the magma must press upward through the molten mass in gas bubbles, and as it escapes, the column of liquid is forced upward, sometimes even with explosive violence. At the end of the eruption, all the water in the lava column must again be in equilibrium down to that depth, and if no other agency intervened, the molten rock would gradually cool and stiffen, so that no further discharge would take place in that funnel. But observation shows that eruptions may continue constant at the same spot for centuries, and, as at Stromboli, may be as frequent as those of geysers. The gaseous water above the critical temperature, in consequence of the enormous pressure, 1,000 atmospheres at 10,000 meters down, beneath the surface, may have the same density as liquid water, probably rather less, and will press into the magma. The investigations of recent years have shown, moreover, that superheated subterranean water possesses entirely different properties from those above ground. At about 300 degrees, it is estimated that water and silicic acid are about equally strong, but at 1,000 degrees, water is some 80 times, and at 2,000 degrees, about 300 times stronger than that acid. It is a common error to criticize the inability of geologists to explain these matters, and the inexpert reader is very apt to declare that all that is necessary to be known is the nature of the interior of the earth, and all the phenomena of volcanism will arrange themselves in due consequence. In this, the casual observer is right, but he forgets that a cognition of the interior of the earth in the present state of scientific investigation is so far impossible. The deepest boring ever made is less than 1/300th part of the earth's radius, and this was in the form of a hole a few inches in diameter. To give an illustration which may show the cause of the little knowledge of the earth's interior. Suppose the smallest insect visible to the human eye to be resting on the surface of an orange, and suppose this tiny insect again to be possessed of a boring instrument like the mechanisms of man, only of course comparable to its own size, that is to say, microscopic to the eye of man. If this insect should force this tiny borer into the orange, it would not penetrate the outer orange-colored skin of the fruit, much less would it reach the white rind within, while the pulp beneath the rind would forever be distant from its mental grasp. If, however, some inner stress in the orange should cause a fissure, through which the juice within should ooze out, in what manner could the insect, supposing it possessed of equivalent mental powers with man, explain the emission of the juice from its knowledge of the orange-colored cuticle of the fruit? In similar wise, the geologist of today is in no position to declare the nature of the interior of the earth from the slight scratchings that have been made upon the surface of the earth by such means as mines, wells, and so-called deep borings. He has not even reached the rind, much less the pulp within. From observations with the pendulum and plumb line, it is calculated that the specific gravity of the earth as a whole is 5.6, while the average specific gravity of the rocks, which form the accessible parts of the crust, is only 2.6. It follows that the interior of the globe is composed of much denser materials than the superficial portion, and this fact, together with the phenomena of terrestrial magnetism, has led many to the belief that the earth is substantially a globe of some dense substance, such as iron. Volcanoes, which eject molten and white-hot lavas, and thermal springs, which pour out floods of hot and even boiling water, indicate that the interior of the earth is highly heated, at least along certain lines. But this only reveals a strata of intense heat and does not prove the heat of the entire interior. It has long been known that, after passing through a zone of variable temperature, the heat increases with the depth below the surface. In New York, the rate is 1 degree Fahrenheit for every 50 feet, and in Prussia, where the deepest borings have been made, it is 1 degree Fahrenheit for every 60 feet of descent. Should this rate be continued regularly, it would reach, at the depth of 35 miles, a heat sufficient to melt almost any known rock at atmospheric pressure. Yet a depth of 35 miles, in comparison with the diameter of the earth, is almost a negligible quantity. Opinions concerning the internal constitution of the earth differ very radically, and only within the last few years has evidence begun to accumulate, which permits the drawing of certain inferences with a considerable degree of probability. Many hypotheses as to the condition of the earth's interior have been proposed, to which the following are the most important. 1. That the earth is a molten globe, covered only by a relatively thin crust. 2. That it is substantially a solid body. 3. That the interior passes gradually from a solid crust to a gaseous core, heated beyond the critical temperature, and yet under such enormous pressure that the core is as rigid as a solid body, but still a gas in molecular condition. According to this theory, the temperature of the earth at the center is about 180,000 degrees Fahrenheit, and the pressure 3 million atmospheres. 4. That it has a very large solid nucleus surrounded by a layer of fused material, upon which the crust floats in equilibrium. William B. Scott deals with these hypotheses as follows. 1. The first, or thin crust hypothesis, is now almost entirely abandoned, for there is really no evidence in its favor and very much against it. The velocity and character of the earthquake waves and the astronomical relations of the earth as a planet especially the tidal phenomena, are strongly opposed to this view. 2. The Earth is substantially a solid body is the opinion held at present by many geologists and astronomers. In support of it may be cited the astronomical evidence just mentioned, and the earthquake waves, the speed of which requires a medium more rigid than steel, while the very transmission of the transverse or distortional waves would seem to require a solid medium. 3. Between the second and the third hypotheses, the distinction is one not easy to explain in an elementary manner, and there are many modifications of the latter. According to Arrhenius, the rigidity of the earth is greater than less than that of steel, but the interior forms an extremely viscous mass, with qualities somewhat like those of asphalt at a low temperature, of pitch, sealing wax, and glass. These bodies behave under forces of deformation, which act quickly or with constantly changing direction, like solids, but under slow, continuing pressures, acting in a constant direction, they behave like fluids. Observations and records of very distant earthquakes show that when the path of the mass waves penetrates to a depth of more than 3/5 of the Earth's radius, the transverse waves of distortion are either extinguished or greatly retarded. This points to a change in the character of the medium and decidedly supports the notion of a gaseous core postulated by this hypothesis. 4. The fourth hypothesis, which assumes the presence of a fused layer between the crust and the solid nucleus, with gradual transitions from one to the other, is believed to avoid the astronomical objections to a molten globe, as well as certain geological difficulties in accepting the hypothesis of an entirely solid Earth. The earthquake observations, so frequently cited, are decidedly opposed to the belief that a layer of actually fused matter can exist at a moderate depth below the surface. It is thus probable that below the superficial crust, only a few miles in thickness, the great mass of the Earth is composed of very dense material, which transmits elastic waves like a very perfectly elastic solid, and yet is so highly heated and under such enormous pressure that it is potentially fused and liquefies under sufficient release of pressure and yields plastically to slow, long-continued stresses which act in a constant direction. Furthermore, there is evidence that a core, 2/5 of the Earth's diameter, and composed of matter in a different state of aggregation, which may be gaseous, occupies the center. The important theory of isostasy is to be considered with care. It has been defined by Titman and Hayford thus: the Earth is composed of heterogeneous material, which varies considerably in density. If this heterogeneous material were so arranged that its density at any point depended simply upon the depth of that point below the surface, a state of equilibrium would exist, and there would be no tendency toward a rearrangement of masses. If the heterogeneous material composing the Earth were not arranged in this manner at the outset, the stresses produced by gravity would tend to bring about such an arrangement, but as the material is not a perfect fluid, the arrangement will be imperfect. The excess of material represented by that portion of the continent which is above sea level will be compensated by a defect of density in the underlying material. The continents will be floated, so to speak, because they are composed of relatively light material, and similarly the floor of the ocean will, on this supposed Earth, be depressed, because it is composed of unusually dense material. This particular condition of approximate equilibrium has been given the name isostasy. The recent very extensive and exact operations of the United States Coast Survey have brought strong confirmation of the theory of isostasy. The United States is not maintained in its position above sea level by the rigidity of the Earth, but is in the main buoyed up, floated, by material of deficient density.
All superficial agents are manifestations of solar energy, as indeed is circulating water which penetrates a certain distance below the surface. These are usually termed destructive and reconstructive processes, words which describe the work rather than define them. It can scarcely be said that the matter of the Earth is destroyed or that it is reconstructed, but it may perhaps be said that it is destroyed as one form of rock and built up again as another. Thus, for example, a granite cliff, against which the sea dashes, will little by little be borne away. The particles thus worn away are sand, and this sand, under suitable pressure and heat, will become sandstone, a very different material from granite. Thus it is possible to say that the granite has been destroyed and the sandstone constructed, but it must not be forgotten that the particles of matter themselves have simply changed their order of arrangement. These two processes are complementary, for, since matter is indestructible and can have only its position and physical and chemical relations changed, it is obvious that what is removed in one place must be laid down in another. In studying the work of the surface agents, the logical order of treatment requires that the destructive operations be considered first. The agencies to be examined are 1. The atmosphere, 2. Running water, 3. Ice, 4. Lakes, 5. The sea, 6. Animals and plants. Of these various agents, the work is principally mechanical, but water, in its various forms, is a slow but extremely efficient agent of chemical changes. The atmospheric agencies are by far the most important of the destructive or denuding agents, because no part of the land surface is altogether exempt from their activity. Their work is described by the general term weathering, and is shown at once by the different appearance of freshly quarried stone from that which has been long exposed in the face of a cliff, or even ancient buildings. While such agents as rivers and the sea do work that is much more apparent and striking than that of the atmosphere, yet they are more locally confined, and even in their operations the atmosphere renders important aid. There are, in the first place, the great differences of climate to be considered, differences in the amount and distribution of the rainfall, of temperature and of the winds, and, in the second place, the resistance offered by the various kinds of rocks to the disintegrating processes. The outcome of these varying factors is to produce very irregular land surfaces. While the tendency of the atmospheric agencies is gradually to wear down the land to the level of the sea, yet in that process some parts are cut away much more rapidly than others, and hence the first effect of denudation is an increasingly irregular surface. The atmospheric agents may be conveniently divided into 1. Rain, 2. Frost, 3. Changes of temperature, 4. Wind. The work of the rain, which is both chemical and mechanical, varies greatly in accordance with climatic factors. Amount, frequency, and violence of the precipitation, together with its temperature and regularity, all modify the effect. Perfectly pure water would act upon rocks with extreme slowness, but such water is not known to occur in nature. The raindrops, formed by the condensation of the watery vapor of the atmosphere, absorb certain gases, chiefly oxygen and carbon dioxide, which very materially increase the solvent power of the water. One of the first and simplest effects of atmospheric moisture consists in the hydration of the minerals exposed to it. Hydration, the taking up of water into chemical union, is an important agent of decay, since it causes an increase of volume and thus greatly increases the pressure in the lower parts of the rock masses, causing them to keep breaking into smaller and smaller blocks. Oxidation affects especially the iron minerals, and thus brings about conspicuous color changes, for iron compounds form the principal coloring matter of rocks and soils. An especially important and widespread change is carbonation, due to the carbon dioxide which all natural waters contain in greater or less quantity. Finally, solution plays a highly important role in the destructive work of the rain. All rocks contain some soluble material, and when the soluble material is removed, the rock crumbles into a friable mass, which, on complete disintegration, forms soil. This may be illustrated by a block of frozen earth, which is as hard as many rocks, being cemented by the ice crystals which bind the particles of soil together. When the ice is melted, the mass immediately becomes incoherent. So, in the rocks, the removal of even a small quantity of soluble material often causes the whole to crumble. Most igneous rocks are made up of crystals of some kind of feldspar associated with such minerals as augite, hornblende, and quartz. In granite, for example, rainwater slowly attacks the orthoclase by dissolving out the potash, probably as carbonate, and also a considerable proportion of the combined silica, and the decompensation finally results in the formation of clay, through which are scattered flakes of mica, if mica were originally present, and unaltered grains of quartz. Rocks which are themselves composed of substances derived from the decay of older rocks are attacked in their turn and yield material for new formulations. These derivative rocks, such as sandstones, slates, and limestones, are affected in characteristic ways by the rain. In a sandstone with siliceous cement, the action is excessively slow, atmospheric waters having very little effect upon silica, but underground it is slowly attacked. The uppermost layers of red sandstone are completely disintegrated into loose sand, bleached by the removal of the iron which gave it its color. In sandstones and slates, it is the cementing substance which is removed, leaving the grains of sand or particles of clay unchanged, and with calcareous cement disintegration is rapid. Slates and shales, by removal of their soluble constituents, crumble down into clay. Limestones, chiefly or entirely carbonate of lime, are attacked by rainwater, dissolved and carried away in solution, while the insoluble impurities contained in the rock remain to form soil. The gradual formation of soil by the disintegration of rock may be easily observed in excavations, even shallow ones, such as cellars, wells, railroad cuttings, and the like. At the surface is the true soil, which is usually dark-colored. Next follows the subsoil, which, owing to the absence of vegetable matter and the less complete oxidation and hydration, is of a lighter color. By imperceptible gradations, the subsoil shades into what looks like unaltered rock, but is friable and crumbles in the fingers. This is rotten rock. From this to the firm, unchanged rock, the passage is equally gradual. The mechanical effect of rain is less extensive, perhaps, than its chemical work of disintegration, but it is very important nevertheless. Under ordinary conditions, this mechanical work consists in the washing of soil from higher to lower levels. How considerable is the movement of soil that has been thus brought about may be imagined when one sees, after a heavy rain, the rills which run over the slopes, muddy and charged with sediments, and how turbid the streams become with the soil which the rain washes into them. The mechanical action of rain is greatly increased by extreme violence and volume of precipitation. A single cloudburst will do far more damage than the same quantity of rain falling in gentle showers. One of the most remarkable monuments of rain erosion is exhibited by the curious districts in the far western states known as the Badlands, which cover many thousands of square miles in the Dakotas, Nebraska, Wyoming, Utah, etc. The Badland rocks are mostly rather soft sandstones and clays, with prevailing calcareous cements, and formed in nearly horizontal beds or layers. The rainfall is light, the torrential showers sometimes occur, but the absence of vegetation is favorable to its efficiency, and the present aridity of the climate is not of very long standing from a geological point of view. The chemical action of the rain has disintegrated the rocks by dissolving out the calcareous cement, and then the debris so formed has been mechanically washed away. Differential weathering, or irregular disintegration, has resulted in that remarkable variety and grotesqueness of form resembling the ruins of gigantic towers and castles, for which the Badland scenery is famous. The removal of the protecting vegetation is often speedily followed by disastrous results, and especially the reckless and wanton destruction of the forests, which has gone on in this country ever since its settlement by Europeans, has been followed by the loss of valuable soil on a vast scale. The term frost, as a surface agent in dynamical geology, is restricted to the freezing of water. Water is one of the comparatively few substances which expand considerably on solidifying. This expansion amounts to about 1/11th of the original bulk of the water, and, exerting a pressure of somewhat more than 2,000 pounds per square inch, it takes place with irresistible power, bursting thick iron vessels like eggshells. All rocks are divided into blocks by joints and are traversed by minute crevices, rifts, and pores, all of which openings take up and retain quantities of water, as may be readily seen by examining freshly quarried stone. The water freezes and forces out the large blocks and shatters them into pieces of smaller and smaller size. The fragments thus formed are called talus, and great accumulations of such blocks are formed at the foot of cliffs in all regions where the winters are at all severe. Alternate freezings and thawings not only break up rocks, but cause the broken fragments and soil to work their way down slopes. Each freezing causes the fragments to rise slightly at right angles to the inclined surface, and each thawing produces a reverse movement, hence the slow creep down the slope. Immense accumulations of frost-made talus are to be found in such places as the foot of the Palisades of the Hudson, and at Sherman, where the Union Pacific Railroad crosses the Continental Divide, the ground is covered for miles with small, angular fragments of granite broken by the frost. Sudden changes of temperature form another of the processes by which rocks are broken. Their influence is greatest where the changes are most extreme, as in arid regions, especially high mountains and plateaus. The exposure of a naked rock to the burning rays of the sun, followed by the rapid radiation in thin air, causes extreme expansion and contraction. As, however, the heat has penetrated some distance into the interior of the rock, and the surface cools first, the cause is that of a cooling exterior trying to contract upon a heated, expanded interior. The rock not being susceptible of sudden elasticity, the interior refuses to contract in obedience to the demands of the exterior, and when the latter endeavors to contract, the passive resistance of the expanded interior causes the surface to crack and break. Certain rocks, notably granites, exfoliate under extreme temperature changes, that is, the surface portions split off in large sheets, which may be of almost any thickness and are either flat or, more commonly, are curved. The effect is frequently the disintegration of rocks into minute fragments. This is especially noteworthy in those igneous rocks which are coarsely crystalline. The force of the wind bearing particles of sand acts like emery and becomes a disintegrating agent of importance. This agency is of small efficiency in regions of ordinary rainfall, because in these the soil is protected and held together by its covering of vegetation. But on sandy coasts the force is intense. In a Cape Cod lighthouse, a single heavy gale so ground a plate glass window as to render it opaque and useless. Glass is far harder than many rocks, so that the latter are quite rapidly abraded and cut down by the drifting sand. The softer parts are cut away first, leaving the harder layers, streaks or patches standing in relief. In this way, very fantastic forms of rocks are frequently shaped out, potholes and caverns are excavated by the eddying drift, and archways cut through projecting masses. Isolated blocks are sometimes so symmetrically cut away on the underside that they come to rest upon a very small area and form rocking stones, which, in spite of their size and weight, may be swung by the hand. Slowly as they work, the wind and temperature changes prevent any complete stagnation in the circulation of material, and thanks to them, the processes of disintegration of rock and transportation of soil are kept up even in the driest deserts. The source of all running water, says Scott, whether surface or underground, is atmospheric precipitation. The rainwater which falls upon the land is disposed of in three ways. One part is returned to the atmosphere by evaporation. Another part flows over the surface to the nearest watercourse. The remainder sinks into the soil to a greater or less depth, and though some of it is returned to the surface in springs, yet a great part must reach the sea by subterranean channels. The relative proportions of these three parts of the total precipitation vary much in accordance with the climate and with the topography of the land surface. At a depth below the surface, which varies greatly at different times and places, the soil and rocks are saturated with water, which is called the groundwater. Near bodies of surface water it may be very little below the surface of the ground, while in arid regions with irregular topography it may sink to great depths. In the eastern United States, the groundwater is encountered at depths of 1 to 100 feet, as is shown by the countless wells which are supplied by it. In the plateau of the Colorado River, which is dissected by profound, deep canyons, the groundwater is, in places, nearly 3,500 feet from the surface. The level fluctuates with the rainfall, rising in wet seasons and sinking in dry. It is usual to regard the groundwater as everywhere penetrating to great depths, but as Spur briefly says, it is probable that the universal presence of groundwater is characteristic of a comparatively shallow surface belt, below which the water, which has not again been drawn off at the surface, at a lower level, or has not been used up in hydration processes, is concentrated into the larger fissures. The factors which determine flow are the inclination of the stratified rocks, the alternation of porous and impervious beds, and the character of the joints and fissures, and not surface topography. The water, seeping downward through the joints and bedding planes, exerts its solvent and decomposing action upon the walls of these crevices in the manner already described in connection with the work of rain. Down to the level of the groundwater, or in the shell of weathering, percolating waters are the great agent of decomposition, and therefore always contain more or less mineral matter in solution, the nature and quantity of which depend upon the character of the rocks traversed. Below the groundwater level in the shell of cementation, the effects are more reconstructive than destructive, though solution and alteration of minerals continue at these lower levels. In passing through limestone, percolating waters dissolve channels which sometimes enlarge into caverns. The Mammoth Cave in Kentucky covers several square miles, and Professor Shaler estimated the length of the passages at 10,000 miles. When underground waters become highly heated, through contact with hot volcanic masses, their solvent efficiency is greatly increased. Rocks penetrated by such thermal waters are profoundly altered in character and composition. Except in caverns, underground waters flow too slowly to accomplish direct mechanical erosion, but indirectly they may bring about important mechanical changes. Masses of soil or talus lying on steep slopes, saturated by long-continued heavy rains, may have their weight so increased and their friction so reduced as to cause landslides. Rock slides occur in a similar manner. In 1903, at Frank, Alberta, in Canada, the entire face of Turtle Mountain fell and rushed across the valley in a huge avalanche of broken rock, estimated at 40 million cubic yards. The effect of this seepage appears wonderfully in springs, which are merely the openings of the groundwater upon the surface, due to the force of gravity, in that the source of a spring is always higher than its mouth. A spring usually is formed when a relatively impervious bed of rock, usually clay in some form, overlaid by porous rock, crops out on a hillside. The groundwater saturates the lower layers of the porous beds until its descent is arrested by the impervious bed, and then the water follows the upper surface of the latter. When, by some irregularity of the ground, the impervious bed comes to the surface, the water will issue as a spring or a line of springs. Other springs rise through a crack or fissure in the rocks. Inclined porous beds, enclosed between more impervious ones, allow the water to follow them downward. On reaching a fissure opening upward, the water will rise through it and, if it is under sufficient pressure, will reach the surface. An artesian well is an artificial fissure spring. It is a boring which taps a sheet or stream of the groundwater, when the water is under sufficient pressure, to rise it to the surface, or even spout high above it. The underground streams, of which springs are the outlets, often have effected much in their way of dissolving rock material, and hence spring water always contains dissolved minerals, principally the carbonates and sulfates of lime and magnesia, and the chlorides of magnesium and sodium. In mineral springs, the quantity of dissolved minerals is larger and perceptible to the taste. The narrow bed of a river has the effect of making its destructiveness more apparent, but as a whole rivers are less potent than the atmospheric agencies. A certain amount of solution and decomposition is performed by rivers upon the rocks of the bed, and in limestones this may be considerable, especially if the water be charged with organic acids from a swamp or peat bog. As in the case of the wind, the stream merely supplies the power. The implement with which the cutting is performed is the sand, pebbles, and other hard particles which the water sets in motion. These abrade the rocks against which they are cast, just as the wind-driven sand does, but more effectively, because of the ceaseless activity of the stream, and because many rocks are rendered softer and more yielding by being wet. The mechanical work is dependent upon the velocity of the current varying directly as the square of that velocity. Angular blocks are speedily worn into cobblestones, and these into pebbles of spheroidal or flat, discoidal form. A process of selection goes on, by which the softer materials are ground into mud, the harder remaining as pebbles and sand. Sudden fluctuations of volume in a river, so that it is now a rushing torrent, and again almost dry, is a much more efficient agent, both of erosion and of transportation, than is one which carries nearly the same quantity of water at all times, or which fluctuates only slowly. In eddies and at the foot of cascades, the water acquires a rotary motion, which is transmitted to stones lying on the bottom. In a rocky bed, these revolving stones excavate cylindrical holes, often of remarkable regularity, called potholes or giant kettles. Unassisted by other agencies, a river cuts a narrow, steep-sided trench or gorge. As soon as the gorge begins to form, its sides are attacked by the atmospheric destructive forces, and a process of widening is begun. But this is very slow, and to widen out the gorge or canyon into a broad valley with gentle slopes requires a long period of time, determined by the activity of the climate and the resistant power of the rocks. Rarely is a river valley straight for any considerable distance, but takes a sinuous course, with rocky spurs projecting alternately from opposite sides of the stream. This is true of even swift streams flowing through hard rocks, and the tendency is much exaggerated when the velocity of the current is diminished and the river bed is in soft materials, as in the lower Mississippi. Having learned the general character of river erosion, a few concrete examples will be interesting. A particularly valuable case is that of the little river Simeto in Sicily, since the history of its gorge is so well known. In 1603, a great lava flood from Etna was poured out across the course of the stream and, when cold, solidified into a barrier of the hardest rock. When Sir Charles Lyell visited the spot in 1828, he found that in a little more than 2 centuries the stream had cut a gorge through this barrier, of 40 to 50 feet deep, and varying in width from 50 to several hundred feet. The lava, which had thus been trenched, is not porous or slaggy, but homogeneous, dense, and very hard. In northern parts of the United States, the great ice sheet brought down with it vast quantities of drift that filled up the channels of many streams and quite revolutionized the drainage of certain districts. Since that time, the displaced streams have cut out new channels for themselves. Ausable Chasm, New York, is an example of these geologically modern river gorges, the atmosphere not having had time to widen it. The Niagara is an exceptional case, the gorge being cut not only by the direct abrasion of the running water, but also by the action of the spray and frost at the falls. In the ravine, the upper rock is a hard, massive limestone, which is underlaid by a soft clay shale. The latter is continually disintegrated by the spray of the cataract and by the severe winter frosts undermining the limestone, which, when no longer able to bear its own weight, breaks off in tabular masses. Thus the falls are steadily receding, leaving behind them a gorge, which is deepened by the river and especially by the plunging masses of water at the foot of the cataract. One of the most remarkable known examples of river erosion is seen in the canyons of the Colorado. The Grand Canyon is over 200 miles long and from 4,000 to 6,500 feet deep, with precipitous walls. It is extremely probable that the river has been rendered able to cut to such profound depths by the gradual uplifting of the whole region, which is now a lofty plateau, in places more than 8,000 feet above the sea. The scope of the transporting power of running water is dependent upon the velocity of the current. If the rapidity of a stream be doubled, it can carry 64 times as much as before, being as the 6th power. The destructiveness of sudden and violent floods is thus explained. In the terrible flood which overwhelmed Johnstown, Pennsylvania, in 1889, great locomotives and massive iron bridges were swept off. It is hardly an exaggeration to say, like straws, and huge boulders carried along like pebbles. The quantity of material which rivers are continually sweeping into the sea is enormously great. Each year the Mississippi carries into the Gulf of Mexico nearly 7,500,000,000 cubic feet of solid sediment, either in suspension or pushed along the bottom, an amount sufficient to cover 1 square mile to a depth of 268 feet. In addition to this is the quantity brought down in solution, which is estimated at 2,850,000,000 cubic feet annually. And yet, this astounding volume only represents a lowering of the surface of the entire drainage at the rate of 1 foot in 4,920 years, for it must be remembered that North America's great river drains 1,325,000 square miles. In addition to the destructive agencies of the atmosphere and of running water, the sea plays a large part. Upon the coastline, whether it be rock or beach, the waves dash interminably, not only possessing the force which has been imparted to them by the wind, but also from the tension of oceanic current and the tides. According to observations made for the Scotch Lighthouse Board, the average wave pressure on the coast of Scotland is for the 5 summer months 611 pounds per square foot, and for the 6 winter months 2,086 pounds. These are average figures, and are greatly exceeded in storms, when the force of the breakers often rises to many tons per square foot. The gentlest movements have some grinding action among the sands, while the heaviest may dislodge and move along, up the shores, rocks many tons in weight. Niagara wastes its power by falling into an abyss of waters, but in the case of the waves, the rocks are barred anew with each successive plunge. The waters are often loaded with gravel and sand when they strike, and thus carry on abrasion. Cliffs are undermined, rocks are worn to pebbles and sand, and, through mutual friction, sand is ground to the finest powder. Rocky headlands on windward coasts are especially exposed to wear, since they are open to the battering force from different directions. The coast of Yorkshire in England is washed away at an average rate of nearly 7 feet per annum. The island of Heligoland, near the German coast, has suffered great loss from the attacks of the sea within historic times. The small eastern island was cut off from the larger island, Heligoland proper, by a great storm in 1720. At Long Branch, New Jersey, the sandy bluffs must be artificially protected against the attacks of the sea, yet in spite of such protection, almost every severe gale does considerable damage. Sandy coasts which are low-lying and flat often suffer less from the inroads of the sea than rocky and precipitous ones, but even such coasts may, however, be rapidly cut back. Limestone coasts suffer from solution by sea water and are characterized by long caverns and tunnels, though sea caves are worn by the surf in all classes of rocks. Of far less influence are the lakes, which indeed are to be regarded as merely temporary bodies of water, and which, either by being filled up or by the gradual wearing away of a barrier which obstructs them, will disappear. In the Great Lakes, there are small tides and small breakers, which in all details follow the nature of marine destruction, but on a far smaller scale. It is otherwise, however, with snow and ice. Snow in the form of avalanches, which frequently bring down with them masses of earth, and ice in the form of glaciers. A glacier, says Scott, is a stream of ice which flows as if it were a very tough and viscous fluid, and does not merely glide down a slope, as snow glides from the roof of a house. Their contribution to the sum total of rock destruction and reconstruction is relatively small, but their former extension has a wide bearing upon some of the most far-reaching of cosmical problems. The height in the Alps of the snow line, or that below which the snow annually precipitated melts during the year, is about 8,400 feet on the north side of the Alps and about 8,800 feet on the south side, and the glacier may descend below this line 5,000 feet or more. Though starting where all is white and barren, it passes by regions of alpine flowers, and often continues down to a country of gardens and human dwellings before its course is ended. Thus the Glacier de Bois, an upper portion of which is called the Mer de Glace, rises in Mont Blanc and other neighboring peaks, and terminates, like several other glaciers, in the Vale of Chamonix. In a similar manner, 2 great glaciers descend from the heights of the Bernese Alps to the Grindelwald Valley, just south of Interlaken. Snow is made up of minute, hexagonal crystals of ice, which are intimately mixed with air and thus separated from one another. Ice is composed of the same kind of crystals as is snow, but they are in contact with one another, not separated by air. To convert snow into ice, it is only necessary to expel the air and bring the crystals into contact, for which pressure alone is not ordinarily sufficient. The first step in the transformation is the partial melting of the upper layers of snow. The water thus formed trickles down into the snow beneath, expelling much of the air. This underling snow still has a temperature much below the freezing point, and the percolating water is soon refrozen into little spherules of ice. This substance, midway between snow and ice, is called neva. The air, which is now in the form of discrete bubbles, is largely expelled by the increasing pressure of the overlaying snow masses, which are continually added to by renewed falls, and the neva is thus converted into ice. A glacier moves in much the same way as a river, but at a very much slower rate. The middle portion moves faster than the sides because the latter are retarded by the friction of the banks, and, for the same reason, the top moves faster than the bottom. While behaving like a plastic substance under pressure, ice yields readily to tension, and even a slight change in the slope of the bed will cause a great transverse crack or crevice to form. Marginal crevices are formed along the sides of the glacier and are due to the more swiftly moving middle pulling away from the retarded sides. The rate of glacier movement depends upon the snow supply, upon the slope of the ground, and the temperature of the season. The great stream of ice which enters Glacier Bay in Alaska has a summer velocity of 70 feet per day in the middle. Newly formed glaciers remove the soil, talus, and other loose material from the surface, and then the bare rocks are eroded by a double process. The joint blocks are torn away by the advancing ice, an operation which is much facilitated by the continual liquefaction and relegation of the ice at the bottom of the glacier, owing to changes of pressure, for it must be remembered that the melting point of ice varies with the pressure, and this is continually changing due to the motion of the glacier and inequalities of the bed, and in this manner the joint blocks of the bedrock are loosened. The bottom of the glacier is a mass of ice mingled with rocks, pebbles, boulders, sand, and debris of all sizes, and by their means the rock bed is worn down, smoothed, polished, and scored with parallel marks in a fashion which forms the unmistakable autograph of the glacier. In the lower part of a glacier, says Dana, the several moraines generally lose their distinctness through the melting of the ice and also by reason of the fact that the glacier is generally compressed in its lower part to a width very much less than the aggregate width of its tributaries. The surface of the glacier accordingly often becomes covered with earth and stones for the greater part of its breadth. The bluff of ice which forms at the foot of a glacier is often a dirty mass, scarcely revealing superficially its real nature. Besides the superficial moraines, a glacier also gathers rock material from the bottom over which it moves. The disintegrated and decomposed rock is mostly scraped from the surface, masses of rock are torn off from jointed ledges, and soft rocks in the path of the glacier are deeply abraded. The final melting leaves all the earth and stones in unstratified heaps or deposits, which may be further transported, abraded, and deposited by the stream that flows from the glacier. The mass of such deposits dropped at the foot of a glacier is called the terminal moraine. River, lake, and coast ice also transport material. When a glacier enters the sea, it plows along the bottom until the buoyant power of the water breaks off great fragments of it, which float away as icebergs. These are often of gigantic size, veritable islands of ice, and huge as they appear, only about 1/9 of their bulk is above the water. As icebergs are derived from glaciers, they carry away whatever debris the parent glacier had upon or within it, and, wherever they melt, they drop all to the ocean's bottom. The sea about the Newfoundland banks is one of the regions of melting icebergs, and there is no doubt that vast submarine accumulations of such material have been made there by this means. Organic forces also play a part. Seeds germinating in the crevices of rocks, or the roots of trees which invade such crevices from above, wedge the rocks apart with the same irresistible power as is displayed by frost, and often large areas of rock are thus most effectively broken up. Many marine animals bore into rocks, even the hardest, and cause them to crumble, and on the land great numbers of animals continually bore and tunnel through the soil, allowing a freer access of air and water. In the tropics, the soil is fairly alive with the multitude of burrowers. Earthworms are among the most important agents in work of this kind. The worms swallow quantities of earth for the sake of the organic material which it contains, and grind it exceedingly fine in their muscular gizzards. This ground-up soil is always deposited on the surface in the form of the coiled worm castings so abundant in grassy places. In England, material thus yearly brought to the surface varies from 7 to 18 tons per acre, which means an average annual addition of 1/10 to 1/6 of an inch. In the tropics, ants and termites, so-called white ants, are even more active than worms in tunneling the soil, and in many semi-arid plains, burrowing mammals in incredible multitudes are continually working over the soil to great depths, as in the prairie dog villages of our western plains. The occasional heavy rains thus penetrate to depths which could not otherwise be reached. The immense influence exerted by man upon the changing condition of physical geography has been summarized by Geikie. The great geologist regards him as a factor antagonistic to the methods and designs of nature. Not content with gathering the fruits and capturing the animals she has offered for his subsistence, he says, man has, with advancing civilization, engaged in a contest to subdue the earth and possess it. His warfare, indeed, has often been a blind one, successful for the moment, but leading to sure and sad disaster. He has, for instance, stripped off the woodland from many a region of hill and mountain, gaining his immediate object in the possession of their stores of timber, but thereby laying bare the slopes to parching droughts and fierce rains. Countries once rich in beauty and plenteous in all that was needful for his support are now burnt and barren, or washed bare of their soil. It is only in comparatively recent years that he has learned the truth of the aphorism, Homo naturae minister et interpres. Human interference affects meteorological conditions by removing forests and laying bare to the sun and winds areas which were previously kept cool and damp under trees, or which, lying on the lee side, were protected from tempests. By drainage, the effect of this operation being to remove rapidly the discharged rainfall, to raise the temperature of the soil, to lessen the evaporation and thereby diminish the rainfall and somewhat increase the general temperature of the country. By the other processes of agriculture, such as the transformation of moor and bog into cultivated land, and the clothing of bare hillsides with green crops or plantations of coniferous and hardwood trees. By increasing or diminishing the rainfall, man directly affects the circulation of water over the land. By the drainage operations, which cause the rain to run off more rapidly than before, he increases floods in rivers. By wells, bores, mines, or other subterranean works, he interferes with underground waters, and consequently with the discharge of springs. By embanking rivers, he confines them to narrow channels, enabling them to carry their sediment farther seaward, and in 1,000 other ways his influence is felt.
It has been pointed out in the work of destruction that in the true sense of the word it is not destruction at all, but rather a preparation for building anew. It is, at the same time, the closing of one period of existence for a certain group of particles of matter, and the beginning of another. But while the active agencies that lead to the breaking down of former masses are numerous, in the strict sense of the word, the reconstruction agency is only one, that of sedimentation. The new rock is built out of the old, though under differing conditions and with different results. At the present time, it is estimated about 1/2 of the waste of the land is carried directly into the sea, while the remainder is arrested in its journey and deposited upon the land. The accessible rocks of the Earth's crust are more largely composed of marine deposits than those laid down in other ways. Yet the non-marine sedimentary rocks are also extensively represented. A natural division of the sedimentary accumulations is into the marine and the continental, including in the latter the deposits which are made upon the land, or in such bodies of water as are not parts of the sea. It is an almost universal characteristic of sedimentary accumulations, says Scott, whether modern deposits or ancient rocks, that they are stratified, that is, divided into more or less parallel layers or beds. Stratification is due to the sorting power of water, or of the wind, by which, so long as conditions remain the same, particles or fragments of similar size and weight are thrown down at the same spot. Layers clearly demarcated from one another may be produced in either one of two ways. 1. By such a change of conditions that the material deposited changes abruptly, though perhaps only as a mere film of a different substance, or 2. By pause, however brief, in the process of deposition. The planes of contact between the successive layers, which may be indistinct or very sharply defined, are called the bedding or stratification planes. Each bed is made up of some predominant substance in a state of greater or less purity, such as gravel, sand, or clay, due to the sorting powers of the water, and thus heterogeneous material is separated into its constituent parts, though the separation is rarely quite complete, and sometimes there is hardly any separation at all. In the sea or a large lake, the material on the bottom grows finer outward from the shore, while a river, whose velocity diminishes from headwaters to mouth, lays down material of decreasing coarseness from the boulders and cobbles of the headwaters to the fine silt of the lower course. Wherever a sandy soil occurs unprotected by vegetation, as in deserts or along the seacoast, the wind drifts the sand and piles it up into hills or sand dunes. When the sands are mixed with pieces of shells or other calcareous material, percolating waters, by dissolving and redepositing the carbonate of lime, may cement the sands into firm rock. This is more conspicuous when the whole material is calcareous, as in the shell sands of Bermuda. Springs also form siliceous deposits, but they are rare, and the carbonate of iron is deposited as chalybeate. Phosphate deposits are also made in rainless regions, where guano, the accumulated excrement of birds, piles up to great thickness without the loss of its soluble matter. Cave deposits are usually chemically formed, and are due to the solution and redisposition of carbonate of lime. At first, the deposit is white, opaque, and very friable, crumbling at a touch, but repeated depositions fill up the interstices of the porous mass and convert it into a hard, translucent stone, which assumes a crystalline structure through the development of calcite or aragonite crystals. The masses thus formed that depend from the roof of the cavern are called stalactites. After hanging for a time from the roof, the drop of water falls onto the floor of the cave, and there, in similar fashion, deposits a little layer of carbonate of lime, which gradually grows into a cone. This is a stalagmite, and differs from the stalactite only in the fact that it grows upward from the floor, instead of downward from the roof. The stalagmite is, of course, exactly beneath the stalactite, and as long as the water continues to follow the same path, the two cones are steadily, though very slowly, increased both in height and thickness, until they meet, unite, and form a pillar extending from the floor to the roof of the cavern. These deposits form the curious and beautiful features of limestone caverns. The vegetable accumulations are the most important of the swamp and bog deposits, for the preservation of which a certain amount of water is necessary. The vast quantities of coal which occur in so many parts of the world testify to the significance of the part which bog and swamp accumulations of vegetable matter have played in the Earth's history. The nearest approach to coal in process of formation at the present day is in the peat bogs, which are especially abundant and extensive in cool, damp climates, as in Ireland, Scandinavia, and the northern parts of South America. The Great Dismal Swamp of Virginia and North Carolina probably more nearly reproduces than do most existing peat bogs the condition of the ancient coal swamps. The swamp, which measures 30 miles by 10, is a dense growth of vegetation upon a water-covered soil of pure peat about 15 feet deep and with no admixture of settlement. The swamp cypress grows abundantly in the bog and prevents, by its dense shade, the evaporation which would take place in summer could the sun's rays penetrate the wet soil. The shallow layer of water which covers the ground receives the fallen leaves, twigs, and branches, and sometimes even the trunks of fallen trees, preventing their complete decomposition, while the dense covering of mosses, reeds, and ferns, which carpet the ground, add their quota to the mass of decaying vegetable matter. The accumulations at the mouths of rivers, generally known as deltas, have, from ancient times, been the means of showing man in what manner the configurations of the surface of the earth was changing. The delta at the mouth of the Nile is a typical case in many ways, and its working was observed by the older nations that bordered the Mediterranean. This is more especially noticeable in the Nile, for there was added to the problem the question of why the delta did not advance further into the sea due to a swift current along the seafront, and this led to an investigation of the Mediterranean currents. But the delta of the Mississippi, on the other hand, is advancing rapidly, about 110 yards a year, or 27 feet a month, a speed which, if to be extended to long geological ages, is amazing. Extraordinarily though it may seem, a week's stay at the mouth of the Mississippi is enough to see perceptibly the surface of the earth changing shape. Debris brought down by the Indus, a swifter stream, instead of forming a delta with a sluggish current, has been carried to the ocean, where it has made a shoal covering an area of 700,000 square miles, a little larger in size than all the states north of Mason and Dixon's line and west of the Mississippi, or 5 times as large as the British Isles. In the course of time, this shoal will arise to the surface, and a new country will have been formed. The delta formation is seen in small streams entering lakes, and accumulations in the same manner as are made in the ocean beds are to be found in the lake basins. In small lakes, the coalescence of deltas, or the advance of a single one, will eventually fill up the basin, forming first swamps, and then smooth, grassy meadows, through which flow the streams, keeping their own channels clear. Such filled-up lakes are common in many mountain valleys. Lake deposits betray the form of the basin in which they are laid down. Around the old shoreline are masses of coarse materials, with deltas interspersed, to mark the mouth of the streams, while toward the middle of the basin quantities of fine mud and clay have accumulated. An excellent example of such a deserted lake basin is that known as Lake Bonneville in Utah, of which Salt Lake is the shrunken remnant. The drying up of this lake, which was once fresh and had an outlet northward to the Snake River, is an event geologically so recent that its form and size, its shores and islands, its high and low stages, in short, its history, can be made out with great clearance, as has been admirably done so by Mr. Gilbert of the United States Geological Survey. At its time of greatest extension, Lake Bonneville had an area of 19,750 square miles and a maximum depth of 1,050 feet, while Salt Lake, which is variable, had, in 1869, an area of 2,170 miles and an extreme depth of 46 feet. Around the ancient shores are reserved the terraces, embankments, and deltas of the various stages of water, which the gravels and the sands appropriate to the shallow water. The sea is the great theater of sedimentary accumulation, says W.B. Scott in his Introduction to Geology, and rocks of marine origin form the larger part of the present land surfaces. Important as other classes of deposits may be, they are less so than those laid down in the ocean and the waters immediately connected with it. Marine deposits may be classified primarily in accordance with the depth of water in which they are laid down. One of the most valuable guides to the history of ancient rocks, and secondarily in accordance with the nature of the materials of which they are composed and the processes by which they were accumulated. Ripple marks are formed by the wind or by the rippling movements of water, and may be seen on any sandy beach. They occur especially in sands, in shoal water deposits, as well as in those made on floodplains and in lakes and on sand dunes. They are found in rocks of all geological periods, and though most frequent in sandstones, occur in other kinds of rocks. Wave marks and rill marks, sun cracks, rain prints, and the tracks of land animals are preserved in a similar way. It might seem incredible that such slight marks could be preserved for ages in the solid rocks, were it not for the fact that their occurrence is so common. Where for long distances no large rivers enter the sea, and the material is all derived from the wear of the coast, the arrangement of coarse and fine deposits is quite regular, and gravel beds may extend as far as 10 miles from land. Waves and currents sweep sediment not only toward the shore but parallel with it, and tend to simplify the coastline by building barriers and spits across the mouths of bays, which the waves may pile up above high tide, as is seen along the eastern coast of the United States. Behind these barriers, streams bring in sediments, filling up the bays and converting them into salt marshes, and eventually into land. Very near shore currents produce irregularities of stratification, especially the structure known as cross-bedding. Nor are the deposits of lime which go to make limestones deposited at the bottom of the sea by organic forms with calcareous exteriors, such as shellfish, starfish, and the coral polyps, to be forgotten. For example, the chalk white cliffs of Dover, which are so characteristic a feature of the coasts of the south of England, are composed mainly of tiny shells, many of them so unbroken that they can be picked out by hand, while the whole structure under a microscope is seen to be of this order. The creation of huge groups of islands and the extension of the mainland in tropical and subtropical waters by the coral polyp is constant. The fine material derived from the land is generally termed mud. The color of the mud is different on different parts of the ocean floor. It is blue, red, and green, according to the prevailing coloring matter. The abysmal deposits are those the materials of which are not directly derived from the land, but consist of matters carried to the sea in solution and extracted from the seawater by the agency of organisms, together with volcanic substances in a more or less advanced stage of decomposition. They are generally termed oozes, the most important of which is foraminiferal ooze. The foraminifera are minute animals, each one a tiny speck of jelly, most of which, in spite of their extreme simplicity of structure, have the power of secreting very beautiful and complex shells of carbonate of lime. As the animals die, the shells settle to the bottom in myriads. Silica is also dissolved in seawater, and various organisms construct their tests of that substance. The radiolaria are, like the foraminifera, a group of microscopic, unicellular animals, which secrete siliceous tests of the most exquisite delicacy and beauty. They live both at the surface and at the bottom of the sea. Radiolarian tests may be detected in all sorts of marine deposits of both deep and shallow water, but it is only in very profound depths that they occur in quantities sufficient to give character to the deposit. In the Antarctic Ocean, there is an extensive belt of diatom ooze, resembling the freshwater deposit, but may be distinguished by the presence of foraminiferal and radiolarian shells and tests. The profoundest abysses of the ocean, far from any land, are covered with a deposit of red clay, which, though varying much in composition and color, is yet of a quite uniform character. The clay is derived from the disintegration and decay of volcanic substances, especially pumice, which floats upon water, often for months, and drifts long distances in the ocean currents. Of all the oceanic deposits, the red clay is the most widely extended, covering 51,500,000 square miles of the bottom. The excessive slowness with which this abysmal deposit is formed is shown by the occurrence in recognizable quantities of meteoric iron. Comparing the marine deposits now accumulating in the sea with the rocks of evidently marine origin which form most of the land, concludes Scott, we find that the great bulk of these rocks, the sandstones, slates, and limestones, are such as are formed in water of shallow and moderate depths, while only rarely do we discover a rock that implies really deep water.
Structural geology in many ways is the most intricate of all the divisions of the science, for the reason that all the various factors come into play. Thus, while it deals with the substances of which the Earth's crust is composed, it is far from being merely descriptive. It must at the same time present as far as possible the causes of their placement and the forces which have gone to make up their structure. The object of structural geology is to learn not only the agencies which have produced the structures and the way in which they operated, but also the successive steps by which the rocks originated, the order in which they occurred, and their geological date. The distinction between a rock and a mineral is not always an easy one to grasp, yet it is essential that it should be so. A rock is any extensive constituent of the Earth's crust, which may consist, though rarely, of a single mineral, but in the great majority of cases is a mechanical mixture of two or more minerals. A rock thus has seldom a definite chemical composition or homogeneous internal structure. An examination with the microscope almost always shows that a rock is an aggregate of distinct mineral particles, which may be all of one kind, or many different kinds in varying proportions. Geologically, incoherent masses of sand and clay are regarded as being rocks, quite as much as the hardest granites. The igneous rocks wherein heat is the chief factor in their making, as the name shows, are truly primary rocks, in the sense that it seems that all others have been made from them. The particles of matter now composing sedimentary and metamorphic rocks have been changed so often that in many cases the relationship to the igneous rock is not easy to trace, but it is there. As geology is primarily a historical study, the most logical scheme of classification is obviously one that, so far as possible, is genetic. That is to say, one which expresses in brief the history and mode of formation of the rocks. This genetic principle would suggest the division of all rocks into three primary classes or groups. A. Igneous rocks, those which were melted and have solidified by cooling. B. Sedimentary rocks, laid down underwater by mechanical, chemical, and organic processes. And C. Metamorphic rocks, which have been profoundly changed from their original sedimentary or igneous character, often with the formation of new mineral compounds in them. The rocks of earliest times, called igneous, have a deep-seated origin and have either forced their way to the surface or have cooled and solidified at varying depths beneath it. They were the first to be formed, and all the others have been derived, either directly or indirectly, from them. The products of the chemical decomposition or mechanical abrasion of the rocks have furnished the materials out of which the sedimentary rocks were formed, at least in the first instance. The igneous rocks are massive, as distinguished from stratified, and though sometimes presenting a deceptive appearance of stratification, may always be distinguished from the truly stratified rocks. Characteristic differences appear between those igneous masses which have solidified deep within the earth, called plutonic, and have been brought to light only by the denudation and removal of the overlying rock masses, and those which have cooled at or near the surface of the ground, known as volcanic. In order to determine the circumstances under which the rock was formed, the texture of a rock must be observed, and hence great attention is paid to it, and in the igneous group, 5 principal types of texture will be found. 1. Glassy. A glass or slag without distinct minerals in it, though the incipient stages of crystallization, in the form of globules and hair-like rods, are often observable with the microscope. When the glass or slag is made frothy by the bubbles of escaping steam and gas, the texture is said to be vesicular, scoriaceous, or pumiceous, according to the abundance of the bubbles. 2. Compact or felsitic, characterized by the formation of exceedingly minute crystals, too small to be seen by the unassisted eye, giving the rock a homogeneous but stony and not glassy appearance. 3. Porphyritic. In rocks of this texture are large isolated crystals called phenocrysts embedded in a ground mass, which may be glassy or made up of small crystals. They have usually solidified near the surface of the ground. 4. Granitoid. In this texture, the rock is wholly crystalline without ground mass or interstitial paste. The component grains, which may be fine or very coarse, are of quite uniform size, and as the crystals have interfered with one another in the process of formation, they have really acquired their proper crystalline shape. They have solidified slowly and at great depths. And 5. Fragmental. This is represented by the accumulations of the fragmental products ejected by volcanoes, agglomerates, bombs, lapilli, ashes, etc. The texture of an igneous rock is determined by the several factors which affect the molten mass during consolidation. Of such factors may be mentioned the chemical composition, temperature, rate of cooling, degree of pressure, and the quantity present of dissolved vapors and gases, which are called mineralizers. Chemical composition determines the fusibility of a rock at a given temperature. The effect of chemical composition upon texture is seen in the rapidity with which the less fusible rocks chill and stiffen, and therefore the greater frequency with which they form glasses. Hence, very rapid cooling results in a glass, but the microscope reveals the incipient stages of crystallization in many of even the glassy rocks. A somewhat slower rate of solidification produces a cryptocrystalline rock, and successively slower rates bring about the porphyritic, microcrystalline, and granitoid textures. Pressure is of importance in preventing the rapid escape of the vapors and gases contained in the molten mass, and hence frothy, scoriaceous, and vesicular textures cannot be produced under high pressures. The mineralizers, such as steam, hydrochloric acid, and other vapors, determine the crystallization of many minerals which refuse to crystallize in the absence of such vapors. It must not be supposed that a molten magma consists merely of a number of fused minerals mechanically mixed together and having no effect upon one another. Petrographers believe that a molten magma is a solution of certain compounds in others, and that crystallization occurs in the order of solubility, as the point of saturation for particular compounds is successively reached by the cooling mass. Professor Kemp has determined the order of formation of minerals in a solidifying magma. First to form are apatite, the metallic oxides magnetite, ilmenite, and sulfides pyrite, zircon, and titanite. Next, he says, come the ferromagnesian silicates, olivine, biotite, and the pyroxenes and hornblende. Next follow the feldspars and felspathoids, nepheline and leucite, but their period often laps well back into that of the ferromagnesian group. Last of all, if excess of silica remains, it yields quartz. It results from what has been said that the residual magma is increasingly siliceous up to the final consolidation, for the earliest crystallizations are largely pure oxides. It is also a striking fact that the least fusible minerals, the feldspars and quartz, are the last to crystallize. The classification of the igneous rocks now most generally adopted is made upon a threefold method according to texture and chemical and mineralogical composition. In the following table, modified for Kemp's, the textures are given in vertical order, while transversely the arrangement is mineralogical, chiefly in accordance with the principal feldspar. The division of the igneous rocks into families is made primarily in accordance with the mineralogical composition, with subdivisions according to texture. This method gives us 5 principal groups. 1. The granite family. This family includes the dark volcanic glass, obsidian, pumice, which is generally known, rhyolite, quartz, porphyry, and granite. 2. The syenite family. The chief rocks included are syenite obsidian, trachyte, phonolite, syenite, and nepheline syenite. 3. The diorite family. There are but 3 important rocks in this class: andesites, dacites, and the diorites. 4. The gabbro family. This includes basalt, which is a name covering many varieties. They are common volcanic rocks and are thrown out now by the most active volcanoes. And 5. The peridotite family, embracing pyroxenite, hornblendite, and, after alteration, the serpentites. The sedimentary rocks are secondary formations. They are formed of the debris of the igneous rocks, as the latter have been worn away by the destructive agencies of the atmosphere and water, so that, having been laid down usually underwater, they are almost always stratified, and are formed with rounded fragments, rarely crystalline. The great bulk of the sedimentary materials consists of simpler and more stable compounds than the igneous minerals, from the decomposition of which they have been derived. The most useful classification of the sedimentary rocks is primarily according to the mode of their formation. This gives 2 principal divisions. 1. The aqueous rocks, or those laid down underwater, and 2. The aeolian rocks, those which were accumulated on land, which are of more limited extent and importance. The rocks laid down underwater form the larger and more important part of the sedimentary series. From the accumulation of debris derived from the destruction of pre-existing rocks, carried in mechanical suspension by moving water, whether waves, currents, or streams, and dropped when the velocity of the moving water was no longer sufficient to carry them, a certain group of the aqueous rocks has been formed. Such accumulations are forming today in all kinds of bodies of water, and an examination of the rocks will show that similar accumulations have been made since the beginning of recorded geological time. Mineralogically, the mechanical deposits are of two principal kinds, the siliceous and the argillaceous. The sorting power of water has been sufficient to separate them more or less completely. Sand, sandstone, gravel, and conglomerate are in the siliceous group, and clay, mud, mudstone, and shale are the argillaceous rocks. The chemical precipitates are locally restricted and not at all comparable to the great masses of mechanical and organic sediments. This arises from the fact that the chemical processes occur in a conspicuous way only around the mouths of certain classes of springs and enclosed bodies of water without outlet and subject to evaporation. Thus, calcareous tufa, oolite, gypsum, and rock salt are alkaline. Geyserite and chert, flint, are siliceous, while bog and lake iron ore are ferruginous precipitates. Limestone, shell marl, chalk, dolomite, and green sand are calcareous accumulations, formed almost entirely by the accumulation of vegetable matter and its progressive, though incomplete, decay underwater. This decay is of such a nature that the gaseous constituents diminish while the carbon is removed much less rapidly. Consequently, the proportion of the latter substance steadily rises. All the varieties of carbonaceous rocks pass into one another so gradually that the distinction between them seems somewhat arbitrary. From fresh and unchanged vegetable matter to the hardest anthracite, there is an unbroken series of transitions. The three main divisions are peat, lignite or brown coal, and black coal. Aeolian rocks form less of the Earth's crust than do the aqueous rocks, but they have a special importance because of the hints which they often give as to the physical geography of the place and time of their formation. Blown sand, forming dunes, drift sand rock, talus, soil, and loess are of all Aeolian origin. Examined with the reference to the simplest and broadest facts of structure, it will be noted that rock masses fall into two categories: 1. Stratified rocks, and 2. Unstratified or massive rocks. The stratified rocks form more than 9/10 of the Earth's surface, and if the entire series of them were present at any one place, they would have a maximum thickness of about 30 miles, but no such place is known. As sedimentary strata were laid down upon one another in a more or less nearly horizontal position, the underlying beds must be older than those which cover them. This simple and obvious truth is termed the law of superposition. It furnishes the means of determining the chronology of rocks, and though other methods of ascertaining this point are employed, they must all be based originally upon the observed order of superposition. The only case, says Geikie, in which the apparent superposition may be deceptive is when the strata have been inverted, as in the Alps, where the rocks composing huge mountain masses have been so completely overturned that the highest beds appear as if regularly covered by others, which ought properly to underlie them. But these are exceptional occurrences, wherein the true order can usually be made out from other sources of evidence. The stratified rocks which form the land have been changed, at least relatively, from the position which they originally occupied, since the great bulk of them were laid down under the sea. Originally, they must have been nearly horizontal, for this is a necessary result of the operation of gravity, just as a deep fall of snow, when not drifted by the wind, gradually covers up the minor inequalities of the ground and leaves a level surface. So on the sea bottom, the sediments are spread out in nearly level layers, disregarding ordinary inequalities. The displacements to which strata have been subjected after their formation are of two principal kinds. 1. In the first kind, the strata have been lifted vertically upward, often to great heights, without losing their horizontality. In some of the lofty plateaus through which the Grand Canyon of the Colorado has been cut, almost horizontal strata are found 10,000 feet above the sea level. 2. More frequent and typical are the displacements of the second class, by which the beds are tilted and inclined at various angles. The double condition of a semi-rigid crust with a fluid strata below, coupled with the phenomenon of cooling and contracting, renders the rocks of the Earth susceptible to intensely heavy stresses, and breakage is inevitable, dislocation often occurring. But in all parts of the Earth's surface, the rocks are to be found in strata, so that when such a break occurs, it interferes with the continuity of the strata. Where such is not the case, but the rock merely cracks open without any alteration of the levels of the various strata, it is called a fissure. But when the strain has been vertical as well as horizontal, it is usually so, the result is to change the consecution of the strata. This is called a fault. Whenever the rocks of the Earth's crust are subjected to strain, says J.E. Spur, fractures take place in them as in any other body under similar conditions, and the different parts of the rock tend to move past one another along the fracture planes, seeking to obtain relief from the strain and to accommodate themselves to new conditions. In this movement, one part of the fractured rock mass may move upon the other in any direction, up, down, sideways, or obliquely, according to the conditions, which are different in each instance. The throw of faults varies greatly in different cases, from a fraction of an inch up to thousands of feet. In those of small throw, the plane of fracture is frequently a clean, sharp break, but in the greater faults, the rocks in the neighborhood of the fault are often bent, crushed, and broken, forming a confused mass of fragments. In the present state of knowledge, however, any scheme of classification has an undue appearance of exactness. Radial faults are those in which the principal component of the movement has been upward, downward, or both, though subordinate movements of tilting and rotation frequently occur. Normal faults, also called gravity faults, are those in which the fault plane inclines towards the downthrow side, which forms the hanging wall. It seems best to use the term normal, says J.A. Reid, to cover those faults in which, using the horizontal plane as datum, the hanging wall has dropped relative to the foot. Strike faults are those which run parallel or nearly so to the strike of the beds. Dip faults are, in general, parallel to the dip of the beds and therefore cross or branch out from the strike faults of the same region more or less at right angles. They are less important than strike faults, having generally a smaller throw and less length. Dip faults do not always follow the dip, and strike faults often deviate considerably from the strike of the beds. And sometimes the fault is neither one nor the other, but midway between the two, and then it is called an oblique fault. A reversed fault, which almost always coincides with the strike of the beds, implies a local compression, for the beds occupy less space than before dislocation. In horizontal faults, the principal direction of movement is horizontal, and in horizontal strata may readily escape detection. In faults of the preceding groups, there is apt to be more or less rotation because of unequal friction and resistance of the walls, but in certain cases, this movement of rotation is the principal one, exceeding any movement of translation, and these are the pivotal faults. A thrust is like a reversed fault, in that it is the result of compression, and that the inclination or height of the fault is toward the upthrow side, which is the hanging wall, but differs in the tendency to a horizontal position of the plane of fracture, and in the association with violent folding and plications. In his latest work on the subject, B. Willis divides thrusts into the following three groups. Scissors thrusts are those in which the fault plane is independent of any older structures and occur chiefly in the crystalline schists, metamorphic rocks, and granite, and, as a rule, depart but little from horizontality. Thrusts of this kind are developed on a great scale in the southern Appalachians, especially in eastern Tennessee, where thrusts of 20 miles or more have been observed. On an even more gigantic scale, they occurred in the highlands of Scotland and Norway, where the movement of translation amounts to 75 miles. Fold thrusts are intimately connected with folds and occur only among folded sedimentary rocks. They may rise by plication and inversion, usually between an overturned anticline and the adjoining synclines. Surface thrusts, as their name implies, are formed at the Earth's surface, where a rigid, gently inclined stratum that crops out of the ground is subjected to lateral compression and thrust forward over the underlying beds. The causes of crustal deformations are very obscure, and there is much difference of opinion concerning them. When strata are buried under a sufficient depth of overlying rock, to crush them they become virtually plastic and yield to the compressive force by bending. The movement would seem not to be a true molecular flow, but rather a gliding of the mineral particles one upon another. Geologists accordingly distinguish a shell of flowage, in which the rocks all yield plastically, a more superficial shell of fracture, in which all but the softest rocks break on compression, and between the two a shell of fracture and flowage, in which some rocks break and others bend according to their rigidity. The depth of the zone of flowage is estimated at 20,000 to 30,000 feet below the surface. One explanation made by Willis is that such phenomena are developed in regions that have been raised by upwarping above a position of adequate support, whence results a system of fractures and the settling and readjusting of the fault blocks. Quite a different type of explanation seeks to account for the phenomena of faulting by the transfers of molten magmas deep within the Earth. Not only are the violent migrations of igneous material the cause of complex faulting, says J.A. Reid, but also it is most reasonable to conceive that the deeper and more gradual movements of the subcrust are the cause of the larger fault systems. Given this cause of faulting, the heretofore puzzling facts are satisfactorily and easily explained. Compression and tension still remain true causes of faulting, but mainly as local and proximate ones. The common expression tilting of fault blocks attains a deeper significance, for this tilting may be more largely the result of subcrust migrations than of mere force of gravity. Cases of horizontal motion and pivotal motion become simple, for there is no necessary unchangeable relation between the direction of the force and the position of the fracture plane. A modification of this hypothesis has been proposed by Professor Chamberlain, who regards the downward movements of segments of the Earth's crust as primary and the horizontal movements as incidental to the former. Rocks are not to be considered as unbroken solids, even the hardest and most compressed of them, for the reason that they are all interspersed with tiny crevices and sometimes larger cracks, which, as they bear a definite relation to the structure of the whole strata, are known as joints. Some of these, known as master joints, extend immense distances below ground and form a natural beginning for quarrying stone, but there are usually also minor joints as well. In igneous rocks, this is obviously due to the contraction on cooling. But there is a great deal of irregularity or unconformity, as it is usually called, in the rocks themselves, strata which have been laid down with but little interruption, which are parallel to the bedding places, and on which the movements of the Earth's crust have operated in a uniform manner, show by their structure the comparative peace in which they have lain, and are said to be conformable. But where two groups are found which have been differently acted upon by reason of having been laid down in different periods, then these two groups are not conformable with each other, and their relation is known as unconformity. Volcanoes, like all other mountains, are subject to the destructive effects of the atmosphere, rivers, and the sea. In the Pacific states may be found admirable examples of volcanic cones in various stages of erosion, notably Mount Shasta and Mount Rainier. These mountains, however, merely exemplify the earliest stages of degradation. As time goes on, the loftiest cones will be worn away, and at last only the worn-down and hardly recognizable stump of the volcano remains, which is known as a volcanic neck. The neck consists of the funnel, or vent, filled up with the hardened lava of the last eruption. The diamond mines of South Africa are in almost cylindrical pipes, which are cut through stratified rocks and are filled with an irregular agglomerate. On the surface, the pipes show no topographical indication of their presence, but are quite level with the ground. Lava flows and sheets, which were poured out on the surface of the ground, may be recognized at a glance and traced to the vent whence they issued. Fragmental products are positive proof of volcanic action, for they cannot be formed underground. The plutonic rocks form a series which no one has ever observed in the course of formation because they were solidified at greater or less depths underground. Though these unstratified masses cannot be observed in the process of formation, as may the lavas and pyroclastic rocks, yet the nature of the rocks themselves and their relation to the volcanic and stratified rocks afford a satisfactory explanation of themselves. A primary division of the plutonic masses is into 1. Injected and 2. Subjacent bodies. An injected body, says R. Daly, is one which is entirely enclosed within the invaded formations, except along the relatively narrow openings to the chamber where the latter has been in communication with the feeding reservoir. Subjacent bodies, on the other hand, have no floor upon which the intrusive mass rests, the communication with the Earth's interior being by great openings, which enlarge downward indefinitely within the limits of observation. Injected bodies are of manifold variety of shapes and sizes, and differ in their relations to the enclosing or country rock, and different terms are accordingly used to describe them. A dike is a vertical or steeply inclined wall of igneous rock, which was forced up into a fissure when molten and there consolidated. Dikes of a certain kind may actually be seen in the making, as when the lava column of a volcano bursts its way through fissures in the cone. Intrusive veins are smaller and more irregular. Frequently branching fissures which have been filled with an igneous magma, they may only be a few inches in thickness, and may often be traced to the mass which gave them off. Sills or intrusive sheets are horizontal or moderately inclined masses of igneous rock, which have small thickness as compared with their lateral extent. Sheets conform to the bedding planes of the strata, often running long distances between the same two beds, but if they can be traced far enough, they may generally be found cutting across the strata at one point or another. In thickness, they vary from a few feet to several hundreds of feet. The Palisades of the Hudson are formed by a sheet of unusual thickness. Its outcrop is 70 miles long from north to south, and its thickness varies from 300 to 850 feet. A laccolith is a large lenticular mass of igneous rock filling a chamber which it has made for itself by lifting the overlying strata into a dome-like shape. The magma was supplied from below through a relatively small pipe or fissure. The rock of which laccoliths are made is nearly always of the highly siliceous and less fusible kinds, so that it can more easily lift the strata than force its way between them. Batholiths are great masses of plutonic rock, hundreds or even thousands of miles in extent. In general characteristics, they agree with stocks, except for their very much greater size. Granite is the commonest batholithic rock, and in such masses forms the core of many great mountain ranges like the Sierra Nevada and the Rocky Mountains. Much has been said of the manner in which rocks are cut down and built up again by the destructive agent of atmosphere and water, but there is another force which has led to the transformation of a rock from its original form, and this is known as metamorphism. The term is somewhat vague, for so many factors entering into the making of metamorphic rocks, and the process took place so many eons ago, that it is all but impossible to gain a clear conception of the manner in which they have come into being. An increase in hardness and in the degree of crystallization occurs, and not infrequently includes the generation of an entirely new set of minerals, characteristically arranged. Whether the original of the rock so metamorphosed was igneous or sedimentary cannot always be determined. Metamorphism, as classified by Scott, is of two quite distinct kinds. 1. Contact or local, and 2. Regional metamorphism. Contact metamorphism, he says, is the change effected in surrounding rocks by igneous magmas, There is a difference between the effects produced by a surface lava flow and those caused by a plutonic intrusive. In the former case, the results are usually not very striking because of the way in which a lava stream surrounds itself with non-conducting scoriae, and are such as may be referred to the action of dry heat. Bituminous coal is changed into a natural coke by the removal of its volatile constituents. Clay may be baked into a hard red rock looking like earthenware, and limestone changed to quicklime by driving off carbonic acid gas. Plutonic intrusions are more efficient agents of change because they are presumably of a higher temperature and retain their heat longer, and because the vapors and gases which they contain cannot escape into the atmosphere but strongly affect the invaded rocks. The rock invaded and metamorphosed may be either sedimentary, igneous, or already metamorphic, and the effects may be very marked or surprisingly small. Indeed, it is often quite impossible to say why the changes should be so insignificant. The distance to which the zone of change extends is wider when the intrusive mass cuts across the strata than when it follows the bedding plane, so that a dike or stock is more effective than a sill. Contact metamorphism, as its name implies, is a local phenomenon, but a widely ramifying and complex system of igneous intrusions may change large areas of sedimentary rocks. Regional or dynamic metamorphism applies to the reconstruction of rocks upon a great scale in areas covering, it may be, thousands of square miles, and evidently other processes in addition to those of contact metamorphism are needed to explain such widespread changes. Regionally, metamorphic rocks are, with the exception of the slates, thoroughly crystalline, and usually have lost all trace of whatever fossils and stratification planes they may originally have had. The first step in metamorphism consists in a mere hardening of the rock, accompanied with the loss of water and other volatile substances. In the second stage, the component minerals already present are crystallized, but new compounds are sparingly formed. The stage is frequently accompanied by cleavage, which, to distinguish it from that of minerals, is often called slaty cleavage. Cleavage, suggests C.R. Van Hise, is a capacity present in some rocks to break in certain directions more easily than in others, while fissility is a structure in some rocks by virtue of which they are already separated into parallel laminae in a state of nature. The term fissility thus complements cleavage, and the two are included under cleavage as ordinarily defined. Ordinary roofing slate is one of the best possible examples of a cleaved rock, and in beds of slate interstratified with other rocks, the cleavage is usually quite perfect in the former, absent or but partially developed in the latter. The causes of metamorphism have been summarized by W. B. Scott as follows. 1. Heat is evidently a very important factor of change, as is shown by the phenomena of contact metamorphism, and by numerous experiments by which the process has been imitated successfully. In contact metamorphism, the heat is derived from the igneous magmas, and in dynamic, it is in part mechanically generated, in part due to the interior heat of the Earth invading deeply buried masses. 2. Compression is believed to be the great agent of dynamic metamorphism, and the amount of the change depends upon the intensity of the compression and the depth at which it operates. Hence the varying results, ranging from gentle folding at one end of the series through violent folding to complete reconstruction, crystallization, and foliation at the other. 3. Moisture is another potent agent of reconstruction. Superheated water under pressure is able to attack and dissolve the most refractory substances and to build them up into new combinations. Many minerals, such as feldspars, which have never been artificially crystallized by dry heat alone, will crystallize readily in the presence of superheated water, and the water lowers the temperature necessary for metamorphism. Rocks which melt at 2,500 degrees Fahrenheit, dry heat becomes pasty at 750 degrees Fahrenheit in the presence of water. In contact metamorphism, steam is a very important factor of change, but other vapors and gases play an efficient part. 4. Pressure, as distinguished from active compression, is a necessity for any extensive metamorphic action, whether contact or dynamic. It is the difference of pressure which is responsible for the different effects of surface flows of lava and of subterranean intrusions, and which gives to depth its importance as a controlling factor. The deadweight pressure of overlying rocks prevents the rapid escape of the mineralizing vapors, and when sufficiently great, causes the rock to shear and flow without fracture. Limestone, heated at the pressure of the atmosphere in a lime kiln or an open vessel, becomes quicklime through the expulsion of carbonic acid gas. But, heated under pressure so that the gas cannot escape, it crystallizes into marble. Such pressure also is an essential factor in dynamic metamorphism, as a precondition in enabling the rock to behave more or less plastically under active compression and without shattering. Dynamic metamorphism must, therefore, take place at considerable depths below the surface. The non-foliated rocks represent the less advanced stages of metamorphism in which the forces of compression may have produced cleavage or fissility, but not foliation. The fissures, veins, and faults, which are to be found alike in igneous, sedimentary, and metamorphic rocks, afford an excellent opportunity for the intrusion into the rock of matter of a dissimilar character. Thus, waters-bearing mineral compounds in solution, passing over such crevice or fissure, might readily precipitate that which it bears each tiny grain of precipitated mineral forcing out water at the top. Sometimes these veins are filled in again with the same form of matter as that of which the main rock is composed, but different in structure. Sometimes the veins are filled by sediment which has been blown or washed in, and not infrequently fissures caused by earthquakes have been filled up from below by the intrusion of alien substances forced up by the interior pressure. Fissures thus filled vary greatly in dimensions, from a few inches to many miles in length. The minute veins are filled with material derived from the walls by solution and redeposited in the crevices, such as the veins of crystallized calcite in limestone. Great fissure veins, on the other hand, which may run unchanged for many miles and penetrate to depths beyond the reach of mining, are characterized, says Spur, by regular straight walls, by a fairly constant width, and by a definite direction of both strike and dip. A third class of mineral veins is composed of the veins of replacement, in which the circulating waters have not merely deposited minerals in an open fissure, but have gradually substituted one substance for another by dissolving out the latter and replacing it with the former. It may be molecule by molecule, so that the replacing minerals are pseudomorphs after the older series. A replacement vein represents a water channel of some kind, and so it has a more or less definite direction, but it seldom has sharply defined walls, for the new deposits impregnate the country rock and fade away into it. Replacement veins are most commonly found in limestones, since those are the most readily soluble rocks, but they also occur in rocks which are relatively very unsoluble, such as sandstones, and in igneous rocks like granite. Frequently, the ores of the commercially valuable metals are found in mineral veins, which then are called metalliferous veins. Structural geology, says W.B. Scott, in summarizing up the questions relative to the formation of the rocks, brings vividly before one the innumerable changes through which the Earth's surface has passed and which are recorded in the rocks. The sedimentary rocks, originally laid down underwater in approximately horizontal positions, have been upheaved into land surfaces, either without losing that horizontality or being tilted, folded, compressed, or even violently overturned. Or they may be fractured and dislocated in great faults and thrusts. These movements have been found to be due to enormous lateral compression set up within the crust of the earth, a compression generated in some manner not yet clearly understood. Whether folding or faulting shall result from a given compression depends upon the rigidity of the strata, upon the load which overlies them, and the sudden or gradual way in which compression is applied. The results of compression on a large scale are accompanied by certain minor changes not less characteristic. Compressed rocks are cleaved, fissile, or schistose, according to the intensity of the action and whether the rocks affected are in the shell of flowage or of fracture. These changes may go so far as completely to reconstruct the minerals of the rocks, destroying the old, generating new and obliterating the original character of the strata. Thus, displacements, dislocations, cleavage, fissility, and dynamic metamorphism are but the varying results of lateral compression acting under different conditions and at varying depths. Another class of rocks, the igneous, massive or unstratified, were found to have penetrated and overflowed the strata and to have consolidated in the fissures and cavities which they have made for themselves, or to have been poured out freely on the surface. According to the circumstances under which these masses have cooled, the resulting rock is of glassy, porphyritic, finely or coarsely crystalline texture. When solidified as sheets or dikes, the igneous rocks may be folded, faulted, cleaved, or metamorphosed like the strata, and when a region has been long and repeatedly subject to compression, its structure may become excessively complex and the metamorphosis of its rocks so complete that not even the most careful examination will suffice to distinguish those rocks which were originally sedimentary from those which were igneous. Highly heated waters circulating through fissures and along the joint planes of the rocks deposit the substances which form the mineral and metalliferous veins, though concerning the source of these substances and of the solvent waters there is much difference of opinion. Our study has taught us that many of these processes go on deep within the Earth's crust, and hence cannot be directly observed, but must be inferred from their results. Encouraging progress has already been made in this work, but very much more remains to be done before a knowledge of structure and its full meaning shall be even approximately complete.
The topographical features of the Earth, the mountains, plains, and river valleys, present a striking appearance to even the most casual observer, and the question as to the cause of their present arrangement is one that naturally arises. It has been suggested that this subject treated from the geological side should be called geomorphogeny, since the geologist makes use of the topography to determine the nature of the changes, while the physical geographer employs the conception of changes to explain the topography. It will be seen immediately how the two subjects interlock, but nonetheless there is a quite different principle involved. The questions involved in geomorphogeny then, are those of aggradation, or the elevation of the land, and diastrophism, the removal of land in one place for the purpose of building it up in another. A third class of factors, which, however, are passive rather than active, namely, the character, arrangement, and attitude of the rock masses. A partially degraded region in which the rocks are homogeneous will have a very different kind of relief from one in which the rocks are heterogeneous, and differ materially in their powers of resistance to the denuding agents. The topography of any region is the resultant of the very complex interaction of many different kinds of factors, and is subject to continual change according to definite laws. Suppose, in the first instance, a region newly upheaved from beneath the sea into dry land. The topography of such an area will be constructional, due entirely to the processes of diastrophism and accumulation, and characterized by the absence of a highly developed system of drainage by streams. The coastal plain of the middle and southern Atlantic states is an example of such topography, but slightly modified. Next, the processes of denudation begin their work upon the region. The sea attacks the coastline by cutting it back in one place and building it out in another, until a condition of equilibrium is attained. Rivers are established, adjusting themselves to the structure of the underlying rocks and cutting deep, trench-like valleys, while the atmospheric agencies widen out the valleys, slowly wearing down and washing away the sides and tops of the hills. The details of the cycle of topographical development, which is essential in geomorphological reasoning, says Scott, differ widely under different climatic conditions. If we take the successive stages as they are developed in a pluvial climate, with all basins filled, abundant rivers running to the sea, and the snows of winter melting in summer, to constitute the normal cycle, we shall find that the arid cycle of desert climates deviates from the normal in very important ways. Assume the elevation of a large area with more or less of deformation. The drainage will be consequent on the newly formed slopes, and the lowest part of each basin will form the local base level, for the streams of each basin of deformation are confined to the basin and die away in the floor without uniting into a permanent trunk system. In the youth of the cycle, the highlands are slowly eroded, and deposition takes place on the slopes and floor of each basin, diminishing the relief and raising the local base level, a strong contrast to the corresponding stage of the normal cycle, in which relief is increased by the excavation of stream valleys. Even in arid regions, however, valleys are cut on the highland slopes, while the basin floor is made nearly level by deposition. This stage is exemplified by the Great Basin and its mountains. Water is the chief agent of erosion and deposition during the period of youth, but the wind is also important in eroding the bare rocks and in distributing the finer waste, part of which it carries outside the arid region altogether. Extremely slow as this process of complete removal of the finer debris by the wind undoubtedly is, yet it is the only agency which actually lowers the average altitude of the region, for no water flows out of the area we are considering. Maturity of development is attained by the connection of the separate initial basins into a continuous whole. Erosion of the highlands and deposition on the basin floors may result in the formation of a continuous slope from a higher basin to a lower one, so that, even in the absence of any permanent stream connecting the two, the rain will wash material to the lower basin and a new and lower base level will be established for the higher one, while the lower basin floor will be built up by the transfer to it of the waste accumulated in that which lies at the higher level. As the coalescence of basins and the integration of stream systems progresses, says W. M. Davis, the changes of the local base levels will be fewer and slower, and the obliteration of the uplands, the development of graded Piedmont slopes, and the aggradation of the chief basins will be more and more extensive. In maturity, the relative efficiency of the eroding agents is not the same as in the earlier stages. The wasting away of the highlands diminishes the scanty rainfall, and the quantity and efficiency of the water decrease with the diminution of relief, but the activity of the wind is not affected, and hence its relative importance is increased. The period of old age, continues Scott, begins with the breaking up of the unified drainage system through the excavation of wind-made hollows in the softer rocks, a process unlike anything which we have found in pluvial climates, where a drainage system once established is not disintegrated during the progress of a normal cycle. If the desert were strictly rainless and erosion carried on by the wind alone, there would apparently be no limit to the excavation of such hollows, but no such instance is known, and the occasional heavy rains suffice to counteract it by filling up the hollows, but the drainage system is effectively disintegrated, and the waste, which in the stage of maturity gathered on the lower parts of the region, is washed about irregularly. The surface worn down by the wind may have no slope in any particular direction, for the wind has no base level and is not affected by the inclination of the ground, but this surface may be reduced to an essential plain-like character. Harder masses of rock, which have successively resisted wear, may rise above the plain as residual mountains, just as they sometimes do in the peneplain of the normal cycle. What has been aptly termed land sculpture, by which is meant the bizarre shapes that rocks assume when acted upon by physical agencies, is due to the effect of varying gradations of hardness in the rocks. When a peneplain or plain of marine denudation is lifted high above sea level, without folding or steep tilting of the strata, streams are soon established upon the new land and proceed to cut deep trenches across the plateau. If the surface layers resist weathering, the plateau will be gradually dissected into flat-topped mesas and table mountains, which in the progress of denudation are converted into pyramidal shapes, while if the whole mass of rocks be easily destructible, they weather down into dome-shaped and rounded hills. The badlands are carved out of soft and scarcely inundated rocks, but firm rocks of climates of similar aridity give rise to many vertical-sided mesas, as is so notably the case in the sandstones of New Mexico. The Uinta Mountains in northern Utah are formed by a great anticlinal arch, so broad and gently curved that in a given section the strata appear almost horizontal. Out of these immensely thick and nearly level masses, the subaerial denuding agencies have carved an infinite and most picturesque variety of peaks, pinnacles, columns, and amphitheaters, while the streams have cut profound and gloomy canyons. The Grand Canyon of the Colorado is regarded as the most impressive example of this kind. Inclined or tilted strata give rise to a different class of topographical forms. If, as is generally the case, harder and softer strata alternate, the latter will be swept away more rapidly than the former, which are left standing as ridges or cliffs. As the inclination departs from vertical, the more unequal do the two slopes of each ridge become, the longer and gentler one being in the direction of the dip. Ridges and valleys of this class are beautifully exemplified in the Appalachian Mountains. At Kittatinny Mountain, through which the Delaware River has cut the famous Water Gap, the crest of the ridge is formed by very hard and indestructible sandstones and conglomerates, while the broad valley above and below the gap is in slates or other destructible rock. Where, however, the structure of a topography is tectonic in its character, where the strata are folded, ridges and valleys are necessitated, the ridges by anticlines and the valleys by synclines. If the folding be of moderate degree, so as to produce undulations of sweeping and gentle curves, the tendency of denudation is to reverse the original topography and convert the anticlines into valleys and the synclines into ridges. This apparently paradoxical result is found, when examined, to be natural and simple enough. The crests of newly formed anticlines have been subjected to tensile stresses which open the joints in the strata and render them very easy prey to the denuding agents. The surface of the synclines, on the contrary, has been tightly compressed, and their joints are closed by crowding. Volcanic topography is primarily constructive. The cones vary in form and height in accordance with the amount and character of the material of which they are composed, and the nature of the eruptions. Cones are first furrowed with ravines and valleys, and then gradually degraded into rocks or into low hills of volcanic agglomerate. The infinite variety of combinations of soft tuffs, loose masses of scoriae and ash, hard sheets, streams, pipes, and dikes of lava give rise to the manifold forms of volcanic mountains and islands in the course of denudation, the harder elements resisting longer and standing in relief. The Adirondack Mountains display a topography which is strongly dominated by streams of faults. Their general character is thus clearly described by J.F.O. Kemp. The Adirondack region is mountainous in its eastern half and has its highest peaks near its center, but on the west the mountains disappear and the area becomes a plateau ranging from 2,000 feet above tide gradually downward to the west until it is but slightly higher than Lake Ontario and the St. Lawrence. The mountains are arranged in visible northeast and southwest lines, and are often very steep, if not positively precipitous, in the portions that look to the southeast or northwest. There are also other steep faces nearly at right angles with the above, but they are less pronounced. These features are due to three intersecting systems of faults, the principal one of which is northeast and southwest, and determines the general trend of the mountains. The second system, which trends northeast at right angles to the first, is less important and acts chiefly in cutting the ridges into separate blocks. The third series, with north and south trends, is quite subordinate in its effects. Faults frequently determine the location of valleys. The lower Hudson flows in a fault valley of which the Palisades form the scarp, and in the Adirondacks the drainage is so largely along intersecting fault lines that its regularity is very striking and has occasioned the descriptive term of lattice drainage. Brigham. The zigzag course of the Au Sable Chasm is determined partly by faults and partly by joints. The valley of the Rhine above Strasbourg is a great trough fault included between the Black Forest highlands on the east and the Vosges Mountains on the west. The most remarkable known instance of trough faulting is the Great Rift Valley of eastern Africa. The main valley continues northward from Lake Nyassa and contains Lake Rudolph and several smaller lakes, passing between the plateaus of Abyssinia and Somaliland. It extends to the Red Sea, which is itself regarded as being but a very deep part of the same great downthrow, inundated by the sea. At the northern end of the Great Sea, the Gulf of Aqaba, on the east side of the Sinai Peninsula, is an extension of the trough which, growing shallower, rises to the land and keeps its northerly direction for a long distance. Growing deeper again, it becomes the basin of the Dead Sea, the surface of which is 1,300 feet below sea level, and the valley of the Jordan, and north of that the valley of the Orontes, reaching nearly to Antioch. According to Seuss, this is not an erosion valley, but a tectonic depression. If this interpretation is correct, this vast dislocation extends through 50 degrees of latitude and is one of the most striking structural features of the Earth's surface. A river has its stages of development, youth, maturity, and old age, just as has a land surface, each stage displaying its characteristic marks. In a newly upheaved or newly folded land, the streams are determined entirely by the slopes of the new surface and are called consequent streams. As the river system becomes somewhat older, the stream channels are deepened, the larger ones being cut down to base level. And if the region be one of considerable elevation, deep gorges and canyons are excavated. A mature river system is characterized by the complete development of its tributaries and drainage, so that every part of its basin is reached by the ramifying channels. Valley floors are broadened and deposition begins upon them, and the streams, reaching a condition of equilibrium between erosion and deposition, are said to be graded. The final stages of river development are reached when the base level is attained and the drainage basin reduced to a peneplain by the combined action of the streams and weathering. As a river system approaches maturity, it will increase the number of its branches, and those branches which were not at all represented in the youthful stages of the system and are opened out along lines of yielding rocks are called subsequent. However the streams of a district may have been established in the first instance, whether they were consequent, antecedent, or superimposed, they are liable to changes more or less profound and far-reaching. The upstream extension of branches and the shifting of divides result in the capture of streams, or parts of such, by others more favorably situated, one master stream gradually absorbing many smaller ones which had originally been independent. Figure 30 shows two stages in the evolution of a river system. Figure 31 represents the first stage, in which several transverse streams, A, C, E, F, G, are breaching the escarpments indicated by the shaded lines. Of these streams, C carries the most water and will therefore deepen its gorges through the hard ridges more rapidly than the others and give its tributaries the advantage of the greater fall. In the second stage, C has captured the upper courses of all the other streams except G, which has not yet been reached. The branch 1 has captured A, beheading it, diverting the portion A double prime, and reversing the portion A prime. Similarly, M has captured and divided E. N has done the same with B and P with D, while G must eventually suffer the same fate. Wind gaps will be left in the ridges where the captured streams once crossed them. Coastlines are also of great physiographic importance. There is no greater mistake than to suppose the seacoast to be merely a line whereat the sea now washes. Yet it would be easy to find many people who would define the seacoast as being that stretch of land between high water and low water mark, with perhaps the addition of the former beach, in some cases, to the point of the beginning of land vegetation. Yet the coastline, truly speaking, may extend a long distance under the sea, and in a similar wise a wide range of marine beach formation may exist on land, even miles away from the sea. Regular coasts, says A. Penck, continue for great distances without notable indentations and, for the most part, in gentle curves, convex toward the land, which are connected by curved lines or meet at obtuse angles. The flatter the coast, the more perfectly is this type developed, and the coastline runs for many kilometers in the same curve. With a steep slope, the course is regular only in general. In detail, it seems as though drawn by a trembling hand, with numerous little prominences, which project but a few hundred meters beyond the general coastline, and separated from one another by shallow, curved indentations. The most conspicuous example of the irregular coast unquestionably is the fjord, seen in Norway and Scotland. They are irregular to a wonderful degree, possessing only this in common, that they are produced by the depression and submergence of the land surfaces, not by the throwing up of the high bluff, cliffs, and crags that remain. The fjords are long, narrow, frequently branched, and usually very deep. The ridges of land which separate adjoining fjords are frequently notched by low passes, which seaward become straits, connecting the fjords and cutting up the ridges into islands, which are always very numerous along coasts of this class. The famous Inside Passage from Puget Sound to Sitka, Alaska, is a network of deep waterways among countless islands. What are termed Rias coasts have frequently been regarded as fjord coasts, but the bays here are shorter, more funnel-shaped, and not nearly so deep as fjords. Moreover, they are not of glacial origin and hence are more widely distributed. Calais coasts are marked by numerous short, semicircular, and rather shallow bays, separated by narrow peninsulas, and owe their irregularities not to wave erosion, but to the submergence of land valleys. Those of the typical kind are due to the depression of mountain slopes, furrowed by numerous short ravines. Faults are probably the cause of deep, lobate coasts, such as are to be found in Greece and in Haiti and Japan. There the bays are not so much irregularities in the coast line as deep gulfs, which have taken into themselves hundreds of square miles of land surface, and where the interlocking gulfs are of the same order of magnitude. The popular use of the word mountain is another snare. For example, there are many so-called mountains which are nothing more than the tops of the original plain, the whole of the surrounding country having sunk. A well-known example of this is the Grand Canyon of the Colorado, where, although there are cliffs and buttes of immense height from their bases, yet a line from side to side of the great gorge will reveal that none are greatly higher than the surface of the plain from which the river cut itself down. Some so-called mountain peaks and ridges are merely the portions of dissected plateaus left standing, such as Lookout Mountain and Missionary Ridge in Tennessee and the Allegheny Front in Pennsylvania. A mountain range is made up of a series of more or less parallel ridges, all of which were formed within a single geosyncline or on its borders. The Appalachian Ridge, the Wasatch, the Coast Ridge are examples of typical mountain ranges. A mountain system is made up of a number of parallel or consecutive ranges formed in separate geosynclines, but of approximately similar dates of upheaval. The Appalachian system comprises the Appalachian Range, running from New York to Georgia, the Acadian Range in Nova Scotia and New Brunswick, and the Ouachita Range in Arkansas. Each of these ranges was formed in a different geosynclinal, but at the same geological date, and they are consecutive, having a common direction. A mountain chain comprises two or more systems in the same general region of elevation, but of different dates of origin. The Appalachian chain includes the Appalachian System, the Blue Ridge, the Highlands of New Jersey and the Hudson, a system of different date, and the Taconic System of western New England, which was not formed at the same time as either of the others. A cordillera consists of several mountain chains in the same part of the continent. Thus the chains of the Rocky Mountains, Sierra Nevada, Coast Range, and their prolongations in Canada together make up the Rocky Mountain or Western Cordillera. From these definitions it will appear that the mountain range has a unity of structure and origin which fits it especially for study. If the history of the ranges be understood, the systems and chains will offer little additional difficulty. The manner in which mountain ranges have been formed must be deduced from a careful study of their structure, for no one has ever witnessed the process of that formation. Mountain building may be going on at the present time. Indeed, there is no reason to suppose that it is not. But so slowly is the work carried on that it withdraws itself entirely from observation. Nevertheless, the general course of events may be inferred with much confidence from the structure of the range. The first step in the formation of a mountain range must evidently be the accumulation of an immensely thick body of strata. This, of course, must have taken place chiefly under shoal water, as thick strata can be accumulated only in rather shallow water and parallel with shorelines. To accumulate thick strata in shoal water, the bottom must subside as the sediments are piled upon it, else the water would be filled up and the deposition cease. Such a sinking trough is a geosyncline, and in geosynclines filled with sediments is the cradle of the mountains. The second stage in the building of a range is the upheaval of the thick masses of strata into a series of folds. This can be produced only by lateral compression, a conclusion which is sustained not only by the mechanics of folding and faulting, but also by the less obvious structures, such as cleavage and fissility, metamorphism, the microscopic crumplings and plications, and the crushing and flowage of the mineral particles. The compressing force does not raise anticlines with great cavities beneath them, for such arches could not well be self-supporting, but mashes together the whole mass of strata, raising them into folds and wrinkles, crowding the beds into a greatly reduced breadth, or, when they are not sufficiently loaded to be plastic, breaking and dislocating them in great thrusts. It is not necessary to suppose that a mountain range was thrown up by one steady movement. On the contrary, there is good reason to believe that repeated movements, separated, it may be, by long intervals of time, have been engaged in the work. There are certain mountain ranges which have a different structure and must have had a correspondingly different mode of origin. As already pointed out, the Great Basin, which lies between the Sierra Nevada and the Wasatch Mountains, are a number of parallel mountain ranges with a prevalent north and south trend, which are collectively called the Basin Ranges. These mountains are not folds of very thick strata, but tilted fault blocks, which have been made by normal faults, each upthrow side standing as a great escarpment, but with a tilted top that gradually slopes back to the foot of the next block, to which it stands as the downthrow side. The process of denudation have carved these tilted blocks into peaks and ridges of the ordinary kind. Every mountain range has been profoundly affected by the agencies of denudation, and their ridges and peaks, their cliffs and valleys, have been carved out of swelling folds and domes or angular tilted fault blocks. The general character of the structure of the American continent is extreme simplicity, says Geikie, as compared with that of the Old World. In part of the Rocky Mountain region, for example, while the Paleozoic formations lie uncomfortably upon Precambrian gneiss, there is, according to King, a regular conformable sequence from the lowest Paleozoic to the Jurassic rocks, though probably many local unconformabilities exist. During the enormous interval of time represented by these massive formations, what is now the present axis of the continent appears to have been exempt from any great orogenic paroxysm, and to have remained hardly disturbed by more than a gentle and protracted subsidence. In the Great Depression or geosyncline thus produced, all the Paleozoic and a great part of the Mesozoic rocks were accumulated. At the close of the Jurassic period, the first great upheavals took place. Two lofty ranges of mountains, the Sierra Nevada, now with summits more than 14,000 feet high, and the Wasatch, 400 miles apart, were pushed up from the great subsiding area. These movements were formed by a prolonged subsidence, during which the Cretaceous sediments accumulated over the Rocky Mountain region to a depth of 9,000 feet or more. Then came another vast uplift, whereby the Cretaceous sediments were elevated into the crests of the mountains, and a parallel coast range was formed fronting the Pacific. Intense metamorphism of the Cretaceous rocks is stated to have taken place. The Rocky Mountains, with the elevated tableland from which they rise, now permanently raised above the sea, were gradually elevated to their present height. Vast lakes filled depressions among them, in which, and on the plains in front of the mountains, as in the tertiary basins of the Alps and the Gondwana series of the Himalaya, enormous masses of sediment accumulated. The slopes of the land were clothed with an abundant vegetation in which we may trace the ancestors of many of the living trees of North America. One of the most striking features in the later phases of this history was the outpouring of great floods of trichyte, basalt, and other lavas from many points and fissures over a vast space of the Rocky Mountains and the tracts lying to the west. In the Snake River region alone, the basalts have a depth of 700 to 1,000 feet over an area 300 miles in breadth.
While the life history of organisms is truly biology, and the life history of extinct forms of animals belongs largely to paleontology, yet the geologist has an intimate relation to both, to the life history of present organisms because of their effects upon the Earth's surface, and to the relics of past organic life, because their presence in certain rocks reveals the conditions that prevailed when those rocks were laid down. Historical geology, says Geikie, deals with fossils or organic remains preserved in natural deposits and endeavors to gather from them information as to the history of the globe and its inhabitants. The term fossil, meaning literally anything dug up, was formerly applied indiscriminately to any mineral substance taken out of the Earth's crust, whether organized or not. Ordinary minerals and rocks were thus included as fossils. For many years, however, the meaning of the word has been so restricted as to include only the remains or traces of plants and animals preserved in any natural formation, whether hard rock or loose superficial deposit. The idea of antiquity or relative date is not necessarily involved in this conception of the term. Thus the bones of a sheep buried under gravel and silt by a modern flood, and the obscure crystalline traces of a coral in ancient masses of limestone are equally fossils. Nor has the term fossil any limitation as to its organic grade. It includes not merely the remains of organisms, but also whatever was directly connected with or produced by these organisms. Thus the resin which exuded from trees of long perished forests is as much a fossil as any portion of the stem, leaves, flowers, or fruit, and in some respects is even more valuable to the geologist than more determinable remains of its parent trees, because it has often preserved in admirable perfection the insects which flitted about in the woodlands. The burrows or trails of a worm in sandstone or shale claim recognition as fossils, and indeed are commonly the only indications to be met with of the existence of annelid life among old geological formations. The droppings, coprolites, of fishes and reptiles are excellent fossils, and tell their tale as to the presence and food of vertebrate life in ancient waters. The little agglutinated cases of the caddis worm remain as fossils in formations from which perchance most other traces of life may have passed away. Nay, the very handiwork of man, when preserved in any natural manner, is entitled to rank among fossils, as where his flint implements have been dropped into the prehistoric gravels of river valleys, or where his canoes have been buried in the silt of lake bottoms. The term fossil, moreover, suffers no restriction as to the condition or state of preservation of any organism. In some rare instances, the very flesh, skin, and hair of a mammal have been preserved for thousands of years, as in the case of mammoth carcasses entombed in the frozen mud cliffs of Siberia. Generally, all or most of the original animal matter has disappeared, and the organism has been more or less completely mineralized or petrified. It often happens that the whole organism has decayed, and a mere cast in amorphous mineral matter, as sand, clay, ironstone, silica, or limestone, remains. Yet all these variations must be comprised in the comprehensive term fossil. The conditions of the preservation of fossils, says Scott, are much more favorable to some kinds of organisms than to others. It is only under the rarest circumstances that soft gelatinous animals, which, like jellyfish, have no hard parts, can leave traces in the rocks. The vast majority of fossilized animals are those which have hard shells, scales, teeth, or bones, and of plants, those which contains a sufficient amount of woody tissue. Again, the conditions under which organisms live have a great influence upon the chances of their preservation as fossils. Land animals and plants are much less favorably situated than are aquatic forms, and since the greater number of sedimentary rocks were laid down in the sea, marine organisms are much more common as fossils than are those of fresh water. On land, fossils have been preserved, sometimes in astonishing numbers, under wind-made accumulations of sand, dust, or volcanic ash, and in the floodplain deposits of rivers. Peat bogs are excellent places for fossilization, and the coal seams have yielded great numbers of fossils, principally of plants. The remains of land animals and plants, especially of the latter, are sometimes swept out to the sea, sink to the bottom, and are there covered up and preserved in the deposits. But such occurrences are relatively uncommon. Small lakes offer more favorable conditions for the preservation of terrestrial organisms. Surrounding trees drop their leaves, flowers, and fruit upon the mud flats. Insects fall into the quiet waters, while quadrupeds are mired in mud or quicksand and soon buried out of sight. Flooded streams bring in quantities of vegetable debris, together with the carcasses of land animals drowned by the sudden rise of the flood. The great series of freshwater and volcanic ash deposits, which for long ages were formed in various parts of our West, have proved to be a marvelous museum of the land and freshwater life of that region. On the fine-grained shales are preserved innumerable insects and fishes, with multitudes of leaves, many fruits, and occasionally flowers, while in the sands, clays, and tufts are entombed the bones of the reptiles, mammals, and more rarely, birds of the land, mingled with those of the crocodiles, turtles, and fishes that lived in the water. Similar deposits are known in other continents, but it is on the seabed that the conditions are most favorable to the preservation of the greatest number and variety of fossils. Among the littoral deposits, ground by the ceaseless action of the surf, fossils are not likely to be abundant or well preserved, but in quieter and deeper waters, vast numbers of dead shells and the like accumulate and are buried in sediments. A geological chronology, says Scott again, is constructed by carefully determining, first of all, the order of superposition of the stratified rocks, and next by learning the fossils characteristic of each group of strata. To many it has seemed that this is reasoning in a circle, but that is because the argument is not fully stated, some of its steps being omitted. The order of succession among the fossils is determined from the order of superposition of the strata in which they occur. When that succession has been thus established, it may be employed as a general standard. Great physical events, such as the upheaval of mountain ranges, widespread transgressions of the sea, and changes of climate, often provide a means of correlating the strata of different continents with greater precision than can be done with the aid of fossils only. The latter are, however, indispensable means of first determining which of these events are comparable in different regions. The history is recorded partly in the nature and structure of the rocks, partly in the fossils, and partly in the topographical forms of the land and the courses of the streams. By combining these different lines of evidence, local histories are constructed for each region, until from these, the story of the whole continent may be compiled. The comparative study of the fossils then gives the clue for uniting the history of the different continents into the history of the earth. The method of making the divisions and subdivisions of geological time is not yet a fixed one, and there is much difference in the usage of various writers. The names of the divisions also have been given at various times and in many lands, according to no particular system. Most of these names have been taken from the locality or district where the rocks in question were first studied or are most typically displayed, as Devonian from Devonshire, Jurassic from the Jura Mountains. Some are named from a characteristic or prevalent kind of rock, such as Cretaceous, Latin Creta or chalk, and Carboniferous. Of late, there has been a tendency toward a more uniform method of nomenclature and to the use of one set of terms for the divisions of time and another and corresponding set for the divisions of the strata. The following table represents the divisions of the scale of time and the scale of rocks which have been adopted by the International Geological Congress. Time scale: era, period, epoch, age. Rock scale: group, system, series, stage, substage, zone. It will be observed that the subdivision is carried farther in the scale of rocks than in that of time, because of the generally local character of these minor subdivisions. The names employed are, as yet, the same for both scales, and we speak of the Paleozoic era, or group, and of the Silurian period, or system. It has been proposed to give separate names to the divisions of the two scales, and this would be an improvement in some respects. Table of major geological divisions. Cenozoic era, Quaternary period, Tertiary period. Mesozoic era, Cretaceous period, Jurassic period, Triassic period. Paleozoic era, Permian period, Carboniferous period, Devonian period, Silurian period, Ordovician period, Cambrian period. Precambrian eras, Algonquian period, Archean period. Tracing the history of mankind back to very ancient times, records become more and more scanty and less intelligible until history fades into myth and tradition. Of a still earlier age, there is not even a tradition. It is prehistoric. Similarly, among the geological records, the earliest are in a state of such excessive confusion that they are exceedingly difficult to understand, and between different observers, there are radical differences of opinion, both as to the facts and as to their interpretation. Furthermore, there must have been an inconceivably long time earlier than the most ancient recorded periods, as to which conjecture and inference are the only resource. In these difficult straits, astronomy offers valuable assistance to the baffled geologist. The nebular hypothesis is a scheme of the development of the solar system, which is generally accepted by astronomers in some form as essentially true. The term nebular hypothesis is usually, though not with exactness, limited to one particular form, according to which the place of the present solar system was originally occupied by a vast rotating nebula, a mass of intensely heated vapor, or possibly clouds of meteorites, extending beyond the orbit of the outermost planet. As the nebula cooled by radiation, it contracted, leaving behind it successive rings, like those of the planet Saturn, but on a vastly larger scale. The rings kept up the rotation imparted by the nebula, and all of them lay in nearly the same plane. Unequal contraction in various parts of each revolving ring caused it to break up and gather by mutual attraction into masses. If these rings were composed of relatively small solid masses, like meteorites, or if they had solidified by condensation of the vapors, the heat generated by the collision, as the broken ring was gathered into a mass, would suffice to raise the temperature and liquefy or vaporize the mass. By revolution, the nebulous masses would assume a spheroid shape and become planets. The central mass of the original nebula forms the Sun, which is still in its intensely heated, incandescent state. Another form of the nebular hypothesis, called for the sake of distinction the planetesimal hypothesis, has recently been proposed by Professor Chamberlain. This postulates, as the beginning of the solar system, a spiral nebula, and that the matter of this parent nebula was in a finely divided solid or liquid state before aggregation. It regards the knots of the nebula as the nuclei of the future planets, and the nebulous haze as matter, to be added to these nuclei to form the planets. It assumes that both the knots and the particles of the nebulous haze moved about the central mass in elliptical orbits of considerable but not excessive eccentricity. It deduces a relatively slow growth of the Earth, with a rising internal temperature developed in the central parts and creeping outward. From the strictly geological standpoint, the most important difference between the nebular and the planetesimal hypotheses is that, according to the former, the Earth has passed through a gaseous and a molten stage, and therefore must have formed a crust by solidification, while the latter leads to the conclusion that the Earth has been solid from the beginning, and consequently never formed a crust of solidification. It is unfortunate, says W. B. Scott in his Introduction to Geology, Macmillan Company, that an account of historical geology should begin with the most difficult and obscure part of the subject, but the treatment must be in accordance with the chronological order, and the oldest rocks are the least intelligible. The ordinary criteria of the historical method, namely the stratigraphical succession and comparison of fossils, fail us here almost entirely, and the only way of correlating the rocks of different regions and continents is by means of the characters of the rocks themselves. In the present state of knowledge, lithological similarity is not a safe guide. So many metamorphic rocks, once referred to the Archean, have proved to be of much later date, that some cautious geologists, who have no confidence in lithological similarities, prefer not to use the term Archean at all, but to employ local terms for the oldest crystalline rocks exposed in a given district. The Archean includes the most ancient rocks, often spoken of as the basement or basal complex. Its antiquity is best assured in regions where it is separated by thick series of sedimentary or metamorphic rocks from the lower Cambrian, which can be certainly identified by its fossils. The Archean is composed of completely crystalline rocks of various types, massive rocks such as granite and basic eruptives, and foliated rocks like gneissoid granite, gneiss, and many varieties of schists are intermingled in the most intricate way, a characteristic well expressed in the oft-used phrase of the basal or fundamental complex for the Archean. The component mineral particles show plainly the intense dynamic metamorphism to which they have been subjected in their extremely complex arrangement and in their laminated and crushed condition. The rocks thus referred to the Archean are not necessarily all of the same age, but they are all of vast antiquity and older than any other known series. They are of very great but unknown thickness, for the bottom of them is nowhere to be seen, and even when thrown up into mountain ranges, erosion has in no case cut so deeply into these rocks as to expose anything different below them. The origin of the Archean rocks, Scott resumes, is a problem which has given rise to a great deal of discussion, but a solution appears to be near. Independently, in many countries, observers have reached the conclusion that these rocks are divisible into two great series, a schist series composed chiefly of highly metamorphosed sedimentary and volcanic rocks, and a gneissoid granite series, which is intrusive and later than the former. Assuming that this conclusion is true, at least as a working hypothesis, it involves certain curious consequences. Surface lava flows and volcanic tuffs, and still more sedimentary rocks, necessarily imply a solid floor upon which they were laid, but of this floor not a trace has anywhere been found. The question immediately arises, what has become of it? No answer to this question can yet be given, but apparently the most likely suggestion is that the ascending floods of molten magma, which gave rise to the gneissoid granites, must have melted and assimilated it. If this were only a local phenomenon, there would be nothing very surprising about it, but it would seem to be true of the entire globe, and this is a startling conclusion. It would appear then that a solid crust, however formed, was for a very long time sufficiently rigid and stable to allow a great thickness of sedimentary and volcanic rocks to be accumulated upon it, and then was engulfed and destroyed by a universally ascending magma, though it is not necessary to suppose that this took place simultaneously over the whole earth, or even within a relatively short period of time. It may have required ages in the accomplishment. Furthermore, it must not be forgotten that remnants of the floor may yet be discovered in little-known regions. If this complete and universal assimilation actually took place, it is an absolutely unique phenomenon in the recorded history of the earth, though something more or less similar may have happened many times before that record began. The present writer is not entirely in agreement with Professor Scott as to the following division of geologic time, but in view of the fact that the sequence used in this summary is taken from his Introduction to Geology, no change will be made in the order of presentation. The Algonquian is the name proposed by the United States Geological Survey for the great series of sedimentary and metamorphic rocks which lie between the basal Archean complex and the oldest Paleozoic strata. It is but little used outside of this country and is not universally employed even here, but it is beginning to make its way in Europe and serves a useful, though possibly a temporary, purpose. While it is possible, though not very likely, that more advanced knowledge may make it possible to distribute these rocks partly into the Archean and partly into the Paleozoic, yet for the present at least, it is better to form a separate grand division for them. The Algonquian rocks, which are widely distributed in North America, form an immensely thick mass of strata and of metamorphic rocks, which are believed to represent those strata in other regions. These metamorphic rocks were long generally referred to as the Huronian, which was regarded as the upper portion of the Archean, but so far as can be learned, they occupy the same stratigraphical position as certain little changed sediments between the fundamental complex below and the Cambrian above. At the base of the magnificent section exposed in the Grand Canyon of the Colorado is a very thick mass of strata, separated by great unconformities from the Archean gneiss below and from the overlying Cambrian. This mass is again subdivided by minor unconformities into three series. The lower series, at least 1,000 feet thick, and perhaps more, is made up of stratified quartzites and semicrystalline schists cut by intrusive granite. Above this come nearly 7,000 feet of sandstones with included lava sheets, and at the top more than 5,000 feet of shales and limestones, in which a few fossils have been found. The two upper series are not at all metamorphic. All these strata are steeply inclined, and upon their truncated edges rests the sandstone referred to by Mr. Walcott to the Middle Cambrian. In the Grand Canyon and Montana, determinable fossils have been found in the less changed sediments, but they are too few and scanty to indicate much of the life of the times. Evidences of life are not wanting in the metamorphic rocks of the eastern and northern regions, but they are indirect. The strata of crystallized limestone are indications of the presence of animal life in the Algonquian seas. The great quantities of graphite diffused through many of the schists and the beds of iron ore likewise tend to show the existence of plants at the same time. More conclusive are the determinable fossils obtained in the Belt series of Montana and in the Grand Canyon series, which include the tracks of worms, brachiopods, and fragments of large crustacea referable to the Eurypterida. Such remains imply a long antecedent history of life, the records of which remain to be discovered. With regard to the comparative value of the Precambrian rocks in the chronology of geological history, no precise statement can be made, but various circumstances show that they must represent an enormous period of time. From the general character of the Cambrian fauna, it must be regarded as certain that life had existed on the earth for a long series of ages before that fauna appeared, in order that such well-advanced grades of organization should then have been reached. One of the most interesting chapters of geological history would be supplied if some adequate account could be given of the stages of this long Precambrian evolution. The Paleozoic is the oldest of the three main groups into which the normal fossiliferous strata are divided, continues Scott. It forms the first legible volume of the Earth's history, and in interpreting it, speculation and hypothesis play a much less prominent part than in the Precambrian volume. The Paleozoic rocks are conglomerates, sandstones, shales, and limestones, with quite extensive areas of metamorphic rocks and associated igneous masses, both volcanic and plutonic. The thickness of these rocks is very great, estimated in Europe at a maximum of 100,000 feet. This does not imply that such a thickness is found in any one place, but that if the maximum thicknesses of each of the subordinate divisions be added together, they will amount to that sum. In this country, more than 25,000 feet of Paleozoic strata are exposed in the much folded and profoundly denuded Appalachian Mountains, but in the Mississippi Valley they attain only a fraction of that thickness. These rocks are, in the vast majority of cases, of marine origin, but some freshwater beds are known, and very extensive swamp and river deposits have preserved a record of much of the land life of the era, especially of its later portions. That there must have been land surfaces is abundantly shown by the immense thickness and extent of the strata, all of which were derived from the waste of the land. Both in Europe and in North America, the land areas were prevailingly toward the north, and are doubtless indicated, in part, by the great regions of the Precambrian metamorphic rocks. The general character of the Paleozoic beds shows that they were, in large measure, laid down in shallow water in the neighborhood of land. Their great thickness indicates further the enormous denudation which the land areas underwent. The calculation has not been made for this country, but for Great Britain, Geikie states that the lower half of the Paleozoic group represents the waste of a plateau larger than Spain and 5,000 feet high, cut down to base level. Very widespread disturbances of the Earth's crust before the beginning of the Paleozoic era and at its close have produced well nigh universal unconformities with both the underlying Precambrian and the overlying Mesozoic rocks. At only a few points are the transitional series found. Early in Paleozoic time were established the main geographical outlines which dominated the growth of the North American continent, a growth which was for the most part steady and tranquil. These conditions may be briefly stated as the formation of a great interior continental sea, divided from the Atlantic and the Pacific by more or less extensive and variable land areas. There are thus three principal regions of continental development, those of the Atlantic and Pacific borders and the interior. In addition, the eastern border is subdivided by Precambrian ridges into subordinate areas of deposition. At the present time, the surface rocks over the eastern half of the continent are prevailingly Paleozoic, extending chiefly southward and southeastward from the great Precambrian mass of the north. Paleozoic time was of vast length, perhaps exceeding that of the combined Mesozoic and Cenozoic eras. The subdivisions of the Paleozoic are very clearly marked, locally often by unconformities, but on a wide scale by the changes in the character of the fossils. Paleozoic life possesses an individuality not less distinctly marked than that of the group of strata, which demarcates it very sharply from the life of succeeding periods and gives a certain unity of character to the successive assemblages of plants, floras, and of animals, faunas. The era is remarkable both for what it possesses and what it lacks. Among the plants, the vegetation is made up principally of cryptogams, seaweeds, ferns, club mosses, and horsetails. Especially characteristic are the gigantic tree-like club mosses and horsetails, which are now represented only by very small herbaceous forms. The only flowering plants known are the gymnosperms, the cyads, and their allies. No angiosperms have been discovered. Paleozoic forests must have been singularly gloomy and monotonous, lacking entirely the bright flowers and changing foliage of later periods. The Paleozoic fauna are largely made up of marine invertebrates, in the earlier periods entirely so. For example, so far as we have yet learned, though land life surely began before the oldest records of it yet discovered. Graptolites and hydroid corals, true corals, echinoderms, especially crinoids, cystidines and blastoids, long-hinged and hingeless brachiopods, mollusca, particularly of the nautiloid cephalopods, and the crustacean groups of trilobites and Eurypterida, are the most abundant and characteristic types of animal life. Insects, centipedes, and spiders are common toward the end of the era. Cambrian rocks contain no fossil vertebrates, but they make their appearance in the Ordovician. For long ages, the only vertebrates were fishes and certain low types allied to the fishes, but at the end of the Devonian and in the Carboniferous appeared the amphibia, followed in the Permian by true reptiles. Teleos, such as make up by far the largest part of the modern fish fauna, both marine and freshwater, as well as birds and mammals, are entirely absent from the Paleozoic. The overwhelming majority of Paleozoic species, and even genera, fail to pass over into the Mesozoic, and even in the larger groups, which continue to flourish almost always, a more or less complete change of structure occurs, so that Paleozoic corals, echinoderms and fishes, for example, are very markedly distinct from those which succeeded them. The difference is generally in the direction of greater primitiveness of structure in the older forms, Paleozoic types standing in somewhat the same relation to subsequent types as the embryo does to the adult. In the vast periods of time included in the Paleozoic era occurred some remarkable climatic vicissitudes. Times of widespread glaciation occurred in the Lower Cambrian of Norway and China, probably of Australia, and perhaps also of South Africa. In the Devonian of South Africa, and in the Permian of the latter region, India, Australia, and South America, perhaps also in Europe and North America. For most of the era, however, the climate appears to have been mild and equable on the whole, very much of the same kinds of animals and plants occurring in high as in low latitudes. In short, we can detect no evidence of climatic zones as being distinctly marked in those periods. So far as they are accessible to observation, the Cambrian rocks are chiefly such as are laid down in shallow water near shore, conglomerates, sandstones, and shales, which are ripple-marked in a way that betrays their shoal water origin. During Cambrian times, the sea was slowly advancing over the land in North America, and the geography of the continent was very different at the close of the period from what it had been at the beginning. In the Lower Cambrian, the land areas are inferred to have been somewhat as follows. First, there was the great northern mass of crystalline Archean and Algonquian rocks, but this was probably much more extensive than the present exposures of Precambrian rocks would indicate. It probably covered the whole Mississippi Valley down to 30 degrees north latitude and extended westward beyond the Rocky Mountains. Long narrow strips of land, alternating with narrow sounds, occupied part of New England and the maritime provinces of Canada, while an Appalachian land, whose western line is marked by the present Blue Ridge, extended eastward an unknown distance into the Atlantic. On the western shore of the Appalachian land was a narrow arm of the sea, which opened south and nearly separated this land area from the great mass of the continent. The site of the Sierra Nevada was occupied by a long narrow land, running from Puget Sound to Mexico, and another such area was found in eastern British Columbia. The Great Basin region was underwater. Around these shores were laid down the coarser deposits of the Lower Cambrian, with great masses of shales and thick limestones in deeper water. Much interest necessarily attaches to Cambrian fossils, for excepting the few and obscure organic remains obtained from Precambrian strata, they are the oldest assemblage of organisms yet known. They form no doubt only a meager representation of the fauna of which they were once a living part. One of the first reflections which they suggest is that they present far too varied and highly organized a suite of organisms to allow us for a moment to suppose that they indicate the first fauna of our Earth's surface. Unquestionably, they must have had a long series of ancestors, though of these still earlier forms such slight traces have yet been recovered. Thus, at the very outset of his study of stratigraphical geology, the observer is confronted with a proof of the imperfection of the geological record. When he begins the examination of the Cambrian fauna, so far as it has been preserved, he at once encounters further evidence of imperfection. Whole tribes of animals, which almost certainly were represented in Cambrian seas, have entirely disappeared, while those of which remains have been preserved belong to different and widely separated divisions of invertebrate life. Of the plants of the Cambrian strata, nothing is surely known. Certain marks on the bedding planes of strata have been regarded as seaweeds, but they are too obscure for determination, and many are worm tracks. The fauna is principally made up of trilobites and brachiopods, but many other types are represented also. Trilobites have a more or less distinctly three-lobed body, at one end of which is the head shield, usually with a pair of fixed compound eyes. At the other end is the tail shield, and between the two shields is a ringed or jointed body made up of a variable number of movable segments. The trilobites display an extraordinary variety in form and size, in the proportions of the head and tail shields, in the number of free segments, and in the development of spines. Brachiopods are among the most abundant of Cambrian fossils. Most of them belong to the lower order of the class Inarticulata, in which the shells are mostly horny and the two valves are not articulated together by a hinge. The horny-shelled types, Linarsonia, Lingulepsis, and Lingulella, are of great interest, as they differ but little from certain brachiopods which still exist. The second order of brachiopods, the Articulata, which have calcareous shells connected by an elaborate hinge, were more common in the Upper Cambrian. Sir Roderick Murchison divided his great Silurian system primarily into two parts, upper and lower. This method of classification is generally followed even at the present day, although it is widely recognized that the most decided break in the entire Paleozoic group is the one between these divisions. In 1879, Professor Lapworth proposed to give due emphasis to this distinction by erecting the Lower Silurian into a separate system, the Ordovician. The name is taken from the Ordovici, the ancient British tribe which dwelt in Wales during Roman times. Lapworth's example is now largely followed in England and the United States, but on the continent of Europe, the name Silurian is still retained for both systems. The passage from Cambrian to Ordovician was gradual, without any marked physical break. Only where the Upper Cambrian is sandy, as in New York, is a decided change in the character of sedimentation. In the latter part of the Cambrian, a large inland sea had been established over what is now the Mississippi Valley, and, with frequent fluctuations in depth and modifications in form, it was to persist for long periods as one of the salient features of Paleozoic geography. This sea was separated from the Atlantic by the landmass called Appalachia, and on the western side it was demarcated from the Pacific by islands of undetermined size. At the end of the period came a time of widespread disturbance, upheaval, and mountain making, the traces of which are still plain in North America and Europe, especially along the Atlantic slope of each continent. The interior sea appears to have been entirely drained. At all events, no deposits transitional to the Silurian are known from that region. In the west and northwest, large areas remained land for long periods, but the interior sea was soon re-established in the Mississippi Valley. Some narrow strips of land were added to the margin of the Cambrian coasts, and on a line running through southern Ohio, Kentucky, and Tennessee, a low, broad arch, the formation of which appears to have begun early in the Ordovician, was forced up by lateral compression. This is called the Cincinnati anticline or axis. Ordovician life displays a notable advance over the Cambrian, becoming not only very much more varied and luxuriant, but also of a distinctly higher grade. During the long ages of the period also, very decided progress was made, and when the Ordovician came to its close, all the great types of marine invertebrates and most of their important subdivisions had come into existence. In a general way, the life of the Ordovician is an expansion of that of the Cambrian, though but little direct connection between the two can yet be traced, and evidently there were great migrations of marine animals from some region which cannot yet be identified. Several groups of invertebrates attained their culmination and began to decline in the Ordovician, becoming much less important in subsequent periods. Thus the graptolites, the cystoidean order of echinoderms, the straight-shelled cephalopods, orthoceratites among mollusks, and the trilobites were never so abundant and so varied as during this period. In America, no plants above the grade of seaweeds and coralline algae have been discovered, but in Europe, a few of the higher cryptogams are doubtfully reported. The flora of the Devonian, however, renders it highly probable that land plants were already well advanced in the Ordovician, and their remains may be discovered at any time. This must remain a matter of accident, for the known Ordovician rocks are almost all marine, which is not a favorable circumstance for the preservation of land plants. Such discoveries have indeed already been reported, but the evidence for them is not satisfactory. The general disturbance which closed the Ordovician period appears to have greatly increased the extent of the continent. An important feature in the Silurian geography of eastern North America was the establishment of the Cumberland Basin, or Appalachian Mediterranean, as it has been called. This large sea lay at the eastward of the interior sea, from which it would seem to have been either completely separated, or so nearly so that the species of marine animals inhabiting the two bodies of water were very different. The Cumberland Basin was east of the Catskill-Helderberg line in New York, and its western shore crossed New Jersey and curved westward beyond the center of Pennsylvania, where it ran southwest more or less parallel with the Appalachian line, toward which it curved eastward in southern West Virginia. The interior sea underwent a succession of oscillations much like those which had affected it during the Ordovician. It was apparently closed at the south, but extended northwestward to the Arctic Sea, while its east-west diameter had been greatly reduced from that of the Ordovician. Silurian life is the continuation and advance of the same organic system as flourished in the Ordovician, certain groups diminishing, others expanding, and some new groups now make their first appearance. In parts of North America, the Silurian passed so gradually and gently into the Devonian that it is difficult to draw the line between the two systems. Some disturbances, however, took place in Ireland, Wales, and the north of England, for in these localities the Devonian lies unconformably upon the Silurian. In other parts of Europe, the transition is gradual. Comparing the rocks of the Ordovician, Silurian, and Devonian, as these are developed in the Appalachian and adjoining regions, a certain rhythmic or periodic recurrence of events may be discovered among them. Each system is characterized by a great and very widespread limestone formation, and in each the limestone is succeeded by shales or other clastic rocks, due to an increase of terragenous material, and each was closed by a more or less widespread emergence of the sea bottom. Each began with a subsidence which gradually extended to a maximum at the time when the great limestone was formed. The parallelisms are not exact, but they are certainly suggestive. The European Devonian appears in three different facies. One of these is the Old Red Sandstone, which is largely of continental origin and lies to the north. The second facies is of marine, shoal water deposits and runs from Devonshire through Belgium, the northern part of the Lower Rhenish, and the Harz Mountains to Poland. And the third, extending from northwestern France through Germany to Bohemia, was laid down in deeper water. The period began in Europe with an advance of the sea over the land in many places, reaching its maximum extension in the latter part of the period, but beginning to retire before the opening of the Carboniferous. This subsidence removed the barrier which in Ordovician and Silurian times had separated the northern and southern seas, but was accompanied by the formation of closed basins farther to the north. Europe then was largely an open sea with many islands, and where the waters were sufficiently clear and free from terragenous sediment, coral reefs were extensively formed. The Old Red Sandstone is of particular interest because owing to the peculiar circumstances of its formation, it has preserved a record of Devonian land life, which, though fragmentary, is far more complete than anything we possess from the more ancient periods. These strata were laid down in closed basins, sometimes perhaps in freshwater lakes, which had only a restricted communication with the sea, and it may be that these accumulations were partly made by the wind, though there is no gypsum or salt in the beds to indicate the prevalence of desert conditions. The life of the Devonian is, in its larger outlines, very like that of the Silurian, but with many significant differences, which are due, on the one hand, to the dying out of several of the older groups of animals, and on the other, to the great expansion of forms which in the Silurian had played but a subordinate role. The fossils show that in Devonian times the land was already clothed with a varied, rich, and luxuriant vegetation of the same general type as that of whose scanty traces are found in Silurian strata. All the higher cryptogams are represented, and by large tree-like forms as well as by small herbaceous plants. The Carboniferous system of rocks has received its name from the seams of coal, which formed one of its distinguishing characteristics in many parts of the world. Both in Europe and America it may be seen passing down conformably into the Devonian and Old Red Sandstone. So insensible indeed is the gradation in many consecutive sections where the two systems join each other that no sharp line can there be drawn between them. This stratigraphical passage is likewise frequently associated with a corresponding commingling of organic remains, either by the ascent of undoubted Devonian species into the lower parts of the Carboniferous series, or by the appearance in the upper Devonian beds of species which attained their maximum development in Carboniferous times. Hence there can be no doubt as to the true place of the Carboniferous system in the geological record. In some places, however, the higher members of this system are found resting unconformably upon Devonian or older rocks, so that local disturbances of considerable magnitude occurred before or during the Carboniferous period. In Russia, and still more in China and western North America, Carboniferous rocks cover thousands of square miles in horizontal or only very gently undulating sheets. The Carboniferous is divisible into two sharply marked portions, the lower or Mississippian and upper or Pennsylvanian, a distinction which is applicable in all the continents in which the strata of this period have been carefully studied. During this period, the interior sea expanded widely, probably covering nearly the whole of the Great Plains and most of the old land areas of the west and southwest, which had persisted through more or less of the Silurian and Devonian, were extensively submerged, probably including all of Mexico and the northern part of Central America. West of the Rocky Mountains, the Carboniferous is much the most widely extended of any of the Paleozoic systems, the sea reaching through British Columbia on both sides of the Gold Range into southeastern Alaska. The remarkable profusion of the vegetation of the Carboniferous period, not only in the Old World but in the New, suggested the idea that the atmosphere was then much more charged with carbonic acid than it now is. Undoubtedly there has been a continual abstraction of this gas from the atmosphere ever since land plants began to live on the Earth's surface, and it is allowable to infer that the proportion of it in the air in Paleozoic time may have been somewhat greater than now. But the difference could hardly have been serious, otherwise it seems incredible that the numerous insects, labyrinthodonts, and other air breathers could have existed. Most probably, the luxuriance of the flora is rather to be ascribed to the warm, moist climate, which in Carboniferous times appears to have spread over the globe, even into Arctic latitudes. On the other hand, evidence has been adduced to support the view that in spite of the genial temperature indicated by the vegetation, there were glaciers even in tropical and subtropical regions. The life of this period is thoroughly Paleozoic and continues along the lines already marked out in the Devonian, but there are some notable changes and advances which look toward the Mesozoic order of things. The Carboniferous vegetation, Scott points out, is of very much the same character as that of the Devonian, but owing to the peculiar physical geography of the times, the plants were preserved as fossils in a much more complete state and in vastly larger numbers. The flora is composed entirely of the higher cryptogams and the gymnosperms, no plant with conspicuous flowers having come into existence, as far as we yet know. By far the most abundant of Carboniferous plants are the ferns, phyllocales, which flourished in multitudes of species and individuals, both as tall trees and as lowly herbaceous plants. Many of these ferns cannot yet be compared with modern ones, because the organs necessary for trustworthy classification have not been recovered, and such are named in accordance with the venation of the leaves. In other cases, the comparison with existing ferns may be definitely made, and these remains show that many of the modern families have representatives in the Carboniferous forests and swamps. In North America, the Permian followed upon the Carboniferous with hardly a break, so that the distinction between the two systems must be made entirely upon the fossils, which change very gradually, by drawing a somewhat arbitrary line of demarcation. In various countries there is no general agreement regarding the upper boundary of the Carboniferous. The lower Permian of Europe is remarkable for the great masses of volcanic rocks, lava flows and tuffs which it contains, and which occur in Great Britain, France, Germany, and the Alps. This is in strong contrast to the corresponding American series, which gives no evidence of vulcanation. The animals and plants of the Permian are transitional between those of the Paleozoic and those of the Mesozoic eras. Here are found the last of many types which had persisted ever since Cambrian times, associated with forms which represent the incipient stages of characteristic Mesozoic types, together with others peculiar to the Permian. The flora of the lower Permian is decidedly Paleozoic in character, and that of the upper Permian is decidedly Mesozoic, so that if the line dividing these two great eras were drawn in accordance with the vegetation, it would pass through the Permian. Even in the lower Permian, however, the change from the Carboniferous flora is a marked one, a change which may be largely explained by the increasing aridity of the climate. Mesozoic formations have been grouped in three great divisions, which, though first defined in Europe, are found to have their representative series of rocks and fossils all over the world. The oldest of these is the Trias or Triassic system, followed by the Jurassic and Cretaceous. The life of the Mesozoic, Scott continues again, constitutes a very distinctly marked assemblage of types, differing both from their predecessors of the Paleozoic and their successors of the Cenozoic. In the course of the era, the plants and marine invertebrates attained substantially their modern condition, though the vertebrates remain throughout the era very different from later ones. Even in the vertebrates, however, the beginnings of the newer order of things may be traced. In the earlier two periods, the Triassic and Jurassic, vegetation is almost confined to the groups of ferns, cycads, and conifers, but with the Cretaceous come in the angiosperms, both monocotyledons and dicotyledons, and since then the changes have been merely in matters of detail. Among the Crustacea, the trilobites and eurypterids went out, but all of the modern groups were well represented, though many of the Mesozoic genera are no longer to be found in the seas of today. Insects reach nearly their modern condition, so far as the large groups are concerned: butterflies, bees, wasps, ants, flies, beetles, etc., being added to the older orthopters and neuropters. Fishes became modernized before the close of the era, the bony fishes having acquired their present predominance. The amphibia took a subordinate place, and after flourishing for a time, the great Stegocephalia died out, leaving only the pygmy salamanders and frogs of the present. Birds and mammals made their first appearance, the former advancing rapidly to the nearly present grade of organization, though not reaching their present diversity, while the mammals remained throughout the era very small, primitive, and inconspicuous. The most significant and characteristic feature of Mesozoic life is the dominance of the reptiles, which in size, in numbers, and in diversified adaptation to various conditions of life, attained an extraordinary height of development. The Mesozoic is called the era of reptiles because these were the dominant forms of life. They filled all the roles now taken by birds and mammals. They covered the land with gigantic herbivorous and carnivorous forms. They swarmed in the sea, and as literal flying dragons, they dominated the air. At the present time there are only 5 orders of reptiles in existence, and of these only the crocodiles and a few snakes attain really large size. In the Mesozoic era, no less than 25 reptilian orders flourished, and many of them were gigantic members. Some were the largest land animals that ever existed, and the sea dragons rivaled the whales in size. Nothing so clearly shows that the Mesozoic era is a great historical fact as the dominance of its reptiles. The Triassic period is so named from the very conspicuous threefold subdivision of this system of strata in Germany, where its rocks were first studied in detail and where they occupy a greater area than in any other European country. The German Trias is, however, not the usual facies of the system, but a very peculiar one, and cannot be taken as the standard of comparison for most other countries. In the early part at least of the period, both North and South America extended farther east than at present, and no marine Triassic rocks are known on the Atlantic slope of either continent, but they are extensively displayed on the Pacific side. The land barrier, which during the Paleozoic era had bounded the Great Basin Sea on the west, was submerged, and the Pacific extended over the site of the Sierras, covering western Nevada and sending a gulf into southeastern Idaho, and in British Columbia it transgressed eastward across the present mountains, and it covered part of the coast of Alaska. On the Atlantic side of North America, the course of events is entirely different. In the latter half of the period was formed a series of long narrow troughs, running closely parallel to the trend of the Appalachian Mountains, but separated from them by the ridges of metamorphic and crystalline rocks, which follow those mountains to the east, and which then probably had a considerable altitude, much greater than at present. In those troughs was laid down the enormous thickness of non-marine rocks, which constitute the Newark series, and are now found in several disconnected areas from Nova Scotia to North Carolina. Triassic life is entirely different from anything that had preceded it, though the way for the change was already preparing in the Permian. The Upper Permian, if classified by its plants alone, would be referred to the Mesozoic rather than to the Paleozoic. Therefore it is not surprising that the Triassic flora is very similar to that of the Upper Permian, though the Upper Trias marks a decided advance among the plants. Among the animals, a considerable number of surviving Paleozoic types persist into the Trias, which did not pass into the Jurassic. William Smith, the father of historical geology, was the first to work out the divisions of the Jurassic, which he did early in the last century. Smith's name for the system, Oolitic, has been abandoned in favor of the term Jurassic, which was first used by Brongniart and Humboldt. It was taken from the Jura Mountains of Switzerland, where the rocks of this system are admirably displayed. In Europe, the Jurassic has long been a favorite subject of study because of the marvelous wealth of beautifully preserved fossils which it contains. For this reason, the Jurassic is known with a fullness of detail such as has been acquired regarding very few of the other systems, and no less than 30 well-defined subdivisions have been traced through many countries of the Old World. In this country, the Jurassic is ill represented and its divisions are not clear. The life of the Jurassic has been preserved in wonderful fullness and variety, but with comparatively few exceptions, our knowledge of it has been principally derived from Europe, where a host of eminent geologists have long studied the great wealth of material. The contrast between North America and Europe in regard to the relative abundance of Jurassic marine fossils is seen from the fact that while in Great Britain alone more than 4,000 species have been described, in America hardly 1/10 of that number has so far been found. The flora of the Jurassic differs little on the whole from that of the Trias, and is made up of ferns, horsetails, cycads, conifers, and ginkgos. The name Cretaceous is derived from the Latin word for chalk, creta, because in England, where the name was early used, the thick masses of chalk are the most conspicuous members of the system. Though first made known in England, the main subdivisions of the Cretaceous, as employed in geological literature, bear French names, which have proved themselves better adapted to general use. In very marked contrast to the scanty development of the Jura, the Cretaceous strata of North America are displayed on a vast scale, and cover enormous areas of the continent, eloquent witnesses of the great geographical changes in that long period. Continental, estuarine, and marine rocks are all well represented, and in consequence, our information regarding the life of North America and its seas during Cretaceous times is incomparably more complete than it is for the Triassic and Jurassic. It was during the Upper Cretaceous that the great subsidence took place which affected nearly all parts of the continent and brought the sea in over vast areas where for ages had been dry land. South of New England, the Atlantic coastal plain was submerged, and in New Jersey at least, the waters covered even the nearly base-level Triassic belt, bringing the sea up to the foot of the crystalline highlands. The lowlands of Maryland, Virginia, and the Carolinas, and all of Florida, were under the ocean, and the Gulf of Mexico was extended northward in a great bay, the Mississippi embayment, covering western Tennessee and Kentucky, and extending into southern Illinois. In the southern region, the lower Cretaceous was terminated by an upheaval, which caused the Comanchian Sea to withdraw from Texas and the area to the west and north of it. This mid-Cretaceous land epoch must have continued for a considerable time, permitting extensive denudation and complete change in the fauna. Wherever the marine Upper Cretaceous is in contact with the Comanche limestones north of Mexico, the two are unconformable, and no species of animal is known to pass from one to the other. In Mexico, the lower Cretaceous passes into the upper without a break, the disturbances there taking place at a later date. The Mesozoic era was closed in the west, as the Paleozoic had been in the east, by a time of great mountain making, and to this movement is attributed the formation of most of the great western mountain chains. From the Arctic Ocean to Mexico, the effects of the disturbance are apparent. The Rocky Mountains, the Wasatch and Uinta Mountains, the great plateaus of Utah and Arizona, and the mountains of western Texas date from this time, though subsequent movements have greatly modified them. Vast volcanic outbreaks accompanied the upheaval, which was on a far grander scale than the Appalachian Revolution had been. The life of the Cretaceous displays so great an advance over that of the Jurassic that the change may fairly be called a revolution. In the latter part of the lower and in all of the Upper Cretaceous of North America, the flora assumes an almost completely modern character, and nearly all of our common kinds of forest trees are represented. Sassafras, poplars, willows, oaks, maples, elms, beeches, chestnuts, and very many others. A new element is the monocotyledonous group of palms, which speedily assumes great importance. Cretaceous animals are sufficiently different from those of the Jurassic, but change is not so revolutionary as has been found among the plants. The life of the Cenozoic era is very clearly demarcated from that of the Mesozoic, though many modern characteristics began in the Cretaceous or even earlier. The plants and invertebrate animals nearly all belong to genera which are still living, and the proportion of modern species steadily increases as we approximate the present time. The fishes, amphibia, and reptiles differ but little from those of modern times, and the birds take on the diversity and relative importance which characterize them now. Above all, the mammals undergo a wonderful expansion and take the place of the vanished reptiles, giving to Cenozoic time an altogether different character from all that went before it. The great geographical and climatic changes produce migrations of land animals and plants upon a grand scale, from continent to continent and from zone to zone, the result of which is the distribution of living beings over the Earth's surface as we find it today. The Tertiary period witnessed the development of the present distribution of land and sea and the final upheaval of most of the great mountain chains of the globe. Some of the most colossal disturbances of the terrestrial crust, of which any record remains, took place during these periods. Not only was the floor of the Cretaceous sea upraised into low lands with lagoons, estuaries, and lakes, but afterwards, throughout the heart of the Old World, from the Pyrenees to Japan, the bed of the early Tertiary or Nummulitic Sea was upheaved into a succession of giant mountains, some portions of that seafloor now standing at a height of at least 16,500 feet above the sea. During Tertiary time, there was an abundant manifestation of volcanic activity. After a long quiescence, during the succession of Mesozoic periods, volcanoes broke forth with great vigor, both in the Old and the New World. Vast floods of lava were poured out and a copious variety of rocks was produced, ranging from highly basic basalts, limburgites and periodites, to rhyolites, quartz felsites, and granites. The name Tertiary was given by Cuvier and Brongniart early in the last century to the succession of marine, brackish water, and freshwater beds in the Paris basin. Sir Charles Lyell, many years later, proposed the division of the Tertiary into three parts: Eocene, from the Greek eos, the dawn, and kainos, recent; Miocene, maion, less, and kainos; and Pliocene, plion, more, and kainos. A scheme which is still used today, modified by Bayreuth through the insertion of a fourth epoch, the Oligocene. Oligos little, or in small degree, and kainos. Last of all, the lower Eocene has been separated under the name Paleocene. Paleos, ancient, as in Paleozoic. A change proposed 30 years ago by the botanist Schimper, but only lately coming into wider favor. It has become customary to distinguish between the older and newer parts of the Tertiary by grouping together the Eocene and Oligocene into the Paleogene and the Miocene and Pliocene into the Neogene. The post-Tertiary or Quaternary portion of the geological record includes the various superficial deposits in which nearly all the mollusca are of still living species. It is usually subdivided into two series. 1. An older group of deposits in which many of the mammals are of extinct species. To this group, the names Pleistocene, Post-Pliocene, and Diluvian have been given. And 2. A latter series, wherein the mammals are all, or nearly all, of still living species, to which the names recent, alluvial, and human have been assigned. These subdivisions, however, are confessedly very artificial, and it is often exceedingly difficult to draw any line between them. The gradual refrigeration of climate at the close of the Tertiary ages affected the higher latitudes alike of the Old and the New World. As the cold increased, says Geikie, the whole of the north of Europe came eventually to be buried under ice, which, filling up the basins of the Baltic and North Sea, spread over the plains even as far south as close to the site of London, and in Silesia and Galatia to the 50th parallel of latitude. Beyond the limits reached by the northern ice sheet, the climate was so arctic that snowfields and glaciers stretched even over the comparatively low hills of the Lyonnais and Beaujolais in the heart of France. The Alps were loaded with vast snowfields, from which enormous glaciers descended into the plains on either side, overriding ranges of minor hills on their way. The Pyrenees were in like manner covered, while snowfields and glaciers extended southward for some distance over the Iberian Peninsula. In North America also, Canada and the eastern states of the American Union, down to about the 40th parallel of north latitude, lay under the northern ice sheet. Owing mainly to the direction of the prevalent moisture-bearing winds, the snowfall was greatest toward the west and northwest, and in the direction of Scandinavia, the ice sheets attained their greatest thickness. The Scandinavian ice joined that which spread over Britain, where the dimensions of the sheet were likewise great. Many mountains in the Scottish Highlands show marks of the ice sheet at heights of 3,000 feet and more. If to this depth be added that of the deep lakes and fjords, which were filled with ice, it is evident that the sheet may have been as much as 4,000 or 5,000 feet thick in the northern parts of Britain. This vast icy covering, like the Arctic and Antarctic ice sheets of the present day, was in continual motion, slowly draining downward to lower levels. Toward the west, its edge reached the sea, as in Greenland now, and must have advanced some distance along the seafloor until it broke off into bergs that floated away northward. Toward the south and east it ended off upon land, and no doubt discharged copious streams of glacier water over the ground in its front. In northern Germany, Denmark, Finland, and Scandinavia, The southern limits at which the ice rested a long while before retiring are indicated by long winding ramparts of detritus, or end moraine. In North America also, the southern edge of the ice sheet is marked by similar terminal moraines, which are well displayed from Pennsylvania to Dakota. When this glaciation took place, the terrestrial surface of the northern hemisphere had acquired the main configuration which it presents today. The same ranges of hills and lines of valleys, which now serve to carry off the rainfall, served then to direct the results of the snowfall seaward. The snowsheds of the Ice Age probably corresponded essentially with the watersheds of the present day. Yet there is evidence that the coincidence between them was not always exact. In some cases, the snow and ice accumulated to so much greater a depth on one side of a ridge than on the other, that the flow actually passed across the ridge, and the detritus was carried out of one basin into another. A remarkable instance of this kind has been observed in the north of Scotland, where so thick was the ice sheet that fragments of rock from the center of Sutherland have been carried up westward across the main water parting of the country and have been dropped on the western side. In North America also, abundant evidence is afforded of a northern ice sheet, which overrode Canada and the eastern states, southward to about the 40th parallel of latitude in the valley of the Missouri. Several centers of dispersion have been noted, from which this ice moved outward, chiefly in a general southerly direction, but in the middle part the ice streamed northward into the Arctic Ocean. The great mountain ranges farther south, likewise, nourished the numerous valley glaciers, which radiated outward from the high ground. As great oscillations of climate took place during the Ice Age, and in some cases probably lasted for a long time, the plants and animals both of land and sea could hardly fail to be seriously affected. During the cold intervals, northern forms would probably migrate southward, and in the warmer episodes, southern forms would push their way northward. The Arctic terrestrial animals include the mammoth, woolly rhinoceros, musk sheep, reindeer, Arctic fox, and lemming. The marine invertebrate fauna shared, though in a less degree, the effects of the meteorological and geographical changes. During the times of great cold, northern species found their way southward, some of them even as far as the basin of the Mediterranean. The cause of the remarkable change of climate during the late Tertiary and post-Tertiary time has given rise to much discussion, but is still without a completely satisfactory explanation. Some writers have favored the view that there has been a change in the position of the Earth's axis, or its center of gravity. Others have suggested that the Earth may have passed through hot and cold regions of space. Others again, and notably Lyell, have called in the effects of stupendous terrestrial changes in the distribution of land and sea, on the assumption that elevation of land about the poles must cool the temperature of the globe, while elevation round the equator would raise it. But the amount of geographical transformation thus involved was so great, and the evidence for it appeared to be so slender, that geologists generally have been reluctant to accept this explanation. In the difficulty of accounting for the phenomena by any feasible operation on the Earth itself, they by degrees accustomed themselves to the belief that the cold of the glacial period was not due to mere terrestrial changes, but was to be explained somehow as the result of cosmical causes. Among the recent attempts to deal with the problem of the Ice Age is the hypothesis proposed by Professor Chamberlain, on the basis of variations in the amount of carbon dioxide in the air. It is founded on the capacity of that gas for absorbing heat, and to the effect that might be produced on the temperature of the air by even a comparatively small increase or diminution in the proportion of the gas. The suggestion is that while there is a general tendency to the diminution of that proportion, there arise from time to time conditions, such as great volcanic discharges, whereby much carbonic dioxide is supplied to the atmosphere. On this view, the glacial period would mark a time of great depletion of the gas, while the Arctic Miocene flora would indicate a time of comparative enrichment. Other geologists have turned back to the idea of geographical changes. That considerable oscillations of the relative levels of land and sea took place during the Ice Age has been clearly determined. The general result of investigation favors the opinion that the land in the early part of that period stood much higher than now over the northern regions of Europe and North America. If one accepts the conclusions drawn from the prolongation of land valleys upon the sea floor to a depth of many hundred feet, and from the distribution of dead littoral and shallow water shells down to depths of 6,000 or 8,000 feet in the North Atlantic, it can be seen that a vast area of highland would, under these conditions, have existed. This higher elevation would undoubtedly tend to lower the temperature. Some of the upraised parts of the seafloor might deflect warm ocean currents and thus still further increase the cold in the higher latitudes. But no satisfactory attempt has yet been made to trace out these changes geographically on actual evidence of their having occurred and to connect them with the phenomena of the Pleistocene period. The long succession of Pleistocene ages, shaded without abrupt change of any kind into what is termed the human or recent period, the Ice Age or Glacial period, may indeed be said still to exist in Europe. The snowfields and glaciers have disappeared from Britain, France, the Vosges, and the Harz, but they still linger among the Pyrenees, remain in large mass among the Alps, and spread over wide areas of northern Scandinavia. This dovetailing or overlapping of geological periods has been the rule from the beginning of time, the apparently abrupt transitions in the geological record being due to imperfections in the chronicle. The human period, resumes Geikie, is above all distinguished by the presence and influence of man. It is difficult to determine how far back the limit of the period should be placed. The question has been asked whether man was coeval with the Ice Age. To give an answer, we must know within what limits the term Ice Age is used and to what particular country or district the question refers, for it is evident that even today man is contemporary with the Ice Age in the Alpine valleys and in Finland. There can be no doubt that he inhabited Europe after the greatest extension of the ice. He not improbably migrated with the animals that came from warmer climates into this continent during interglacial conditions, but that he remained when the climate again became cold enough to freeze the rivers and permit an Arctic fauna to roam far south into Europe is proved by the abundance of his flint implements in the thick river gravels, into which they no doubt often fell through holes in the ice as he was fishing. The proofs of the existence of man in former geological periods are not to be expected solely or mainly in the occurrence of his own bodily remains, as in the case of other animals. His bones are indeed now and then to be found, but in the vast majority of cases, his former presence is revealed by the implements he has left behind him, formed of stone, metal, or bone. The history of the Bronze and Iron Ages in Europe is told in great fullness, but belongs more fittingly to the domain of the archaeologist, who claims as his proper field of research the history of man upon the globe. The remains from which the records of these ages is compiled are objects of human manufacture, graves, cairns, sculptured stones, etc., and their relative dates have in most cases been decided, not upon geological, but upon archaeological grounds. When, however, the sequence of human relics can be shown by the order in which they have been successively entombed, the inquiry is strictly geological, and the reasoning is as logical and trustworthy as in the case of any other kind of fossils. The age of the earth is another matter which geologists must needs speak of in terms of extreme guardedness. Reasoning by analogy, it is true, there is a certain standard to be secured. Thus, for example, when it is discovered that water flowing at a certain speed cuts away the particles of a certain rock so many fractions of an inch in a decade, it is assumed that where so many feet have been cut away from a certain rock by the influence of water, the proportion so cut away must represent so many multiples of the fraction of an inch cut away in a decade, and therefore the time that has been since the beginning of the cutting away of that gorge, such as Niagara, is an equivalent number of multiples of the decade of years. But while this affords an excellent basis for rough estimation, it is not to be forgotten that it acts entirely on the assumption that matter was in those early days as it is now, and that the forces are unchanged. This assumption, however useful, cannot be termed strictly scientific, for there is no means of determining whether the original groove, for example, may not have been made in the time when the rock was in a viscous state, or even so superheated that water would cause violent fractures, since worn smooth. The same holds true for sedimentation. A certain land is regarded as being so many thousands or millions of years in age because of the rate at which it has been laid down in sediment. But geologists are becoming more wary of this, especially since the discovery of some coins in a bog in Germany, which, according to the estimates of the laying down of peat, must have been 18,000 years old, and yet which were found to have the stamp of Claudius Caesar. The physical argument, moreover, that changes in plants and animals have taken a long while to produce is purely dependent upon a certain theory of variation in biology, a theory by no means certain or approved. Thus, to give the best known modern instance, in the space of 10 years, Hugo de Vries, the great Amsterdam botanist, has observed a variation in the evening primrose, which is permanent and reproductive, yet which, according to the older ideas of infinitely slow variation, would have been presumed to have taken hundreds, if not thousands, of years. More, if the forces of life were stronger in their youth, as is not an impossible assumption, changes could and probably would occur with greater variation and at higher speeds than at the present time, when the force has been worked over and over for myriad centuries. An ingenious geological argument has been based by Professor J. Joly of Trinity College, Dublin, on the quantity of sodium present in the water of the ocean as a measure of the age of the earth. He assumes that the sodium contained in that water was not derived from the primeval atmosphere or the original constitution of the ocean, but has been supplied in the long course of geological time by the denudation of the land and the consequent removal of the material in solution from the terrestrial rocks. He arrives at the conclusion that if the present annual supply be taken as a measure of what has been the rate in past time, a period of between 90 and 100 millions of years has elapsed since the ocean began to receive its tribute of chemical solution from the land. The geological argument for the age of the earth may be summed up thus. The geological evidence indicates an interval of probably not much less than 100 million years since the earliest forms of life appeared upon the earth and the oldest stratified rocks began to be laid down. The physical argument as to the age of this planet is based upon three kinds of evidence. 1. The internal heat and rate of cooling of the earth. 2. The tidal retardation of the earth's rotation. And 3. The origin and age of the sun's heat. 1. Applying Fourier's theory of thermal conductivity, Lord Kelvin pointed out as far back as the year 1862 that the superficial consolidation of the globe could not have occurred less than 20 million years ago, or the underground heat would have been greater than it is, nor more than 400 million years ago, otherwise the underground temperature would have shown no sensible increase downward. He would now restrict the time to between 20 and 40 millions. 2. The reasoning from tidal retardation proceeds on the admitted fact that owing to the friction of the tidal wave, the rotation of the earth is retarded, and is therefore slower now than it must have been at one time. Lord Kelvin contends that had the globe become solid some 10,000 million years ago, or indeed any high antiquity beyond 100 million years, the centrifugal force, due to the more rapid rotation, must have given the planet a very much greater polar flattening than it actually possesses. 3. The third kind of evidence leads to results similar to those derived from the two previous lines of reasoning. It is based upon calculations as to the amount of heat that would be available by the falling together of masses from space, which by their impact gave rise to our sun, and the rate at which this heat has been radiated. Assuming that the sun has been cooling at a uniform rate, Professor Tate concluded that it cannot have supplied the earth, even at the present rate, for more than 15 or 20 million years. Lord Kelvin also believes that the sun's light will not last more than 5 or 6 millions of years longer. believing that almost anything is possible as to the present internal state of the Earth. Professor Perry concluded an article in Nature in these words: "To sum up, we can find no published record of any lower maximum age of life on Earth, as calculated by physicists, than 400 millions of years. From the three physical arguments, Lord Kelvin's higher limits are 1,000, 400, and 500 million years. I have shown that we have reasons for believing that the age, from all these, may be considerably underestimated. It is to be observed that if we exclude everything but the arguments from mere physics, the probable age of life on the Earth is much less than any of the above estimates. But if the paleontologists have good reasons for demanding much greater time, I see nothing from the physicist's point of view which denies them 4 times the greatest of these estimates."
The physicist, as a result of his studies into the structure of different kinds of matter, has concluded that every body is built up of minute particles called molecules, which are much too small to be perceived even by the strongest microscope. When a liquid turns into a solid because the temperature falls, as when water freezes, or liquid sulfur or molten iron hardens when cooling, the force of cohesion comes into play to bind these molecules together into a rigid mass. So also, when by slow evaporation from solution, as of salt or alum in water, the dissolving liquid is removed, the substance in solution also passes back into the solid form under the action of this same force of cohesion. Thus, the solid is formed from the liquid by the action of the forces acting between these little particles. Further, if the molecules are all of one kind, as in a given chemical substance, and if there are no hindering causes, these molecules will build themselves up after some regular pattern, and the external result is the geometrical form which is called a crystal. This regular building of the molecules, which may take place from a liquid, happens also, even more perfectly, when a solid is formed direct from a gas. Water vapor in the air, if cooled down sufficiently, is formed into the solid snow, and the little snow crystals that fall silently through the atmosphere are often of wonderful regularity and beauty of form. In nature, it often happens that the building process cannot go on freely, and imperfect crystals, or perhaps a mass with only a confused crystalline structure and without distinct external form, is all that is produced. The quartz, feldspar, and mica in the rock called granite usually have formed together in such a way that neither one has had an opportunity to build itself up into perfect crystals, and yet the scientist who understands the optical study of thin sections of a rock in polarized light can prove that each grain, formless though it may be externally, has all the internal molecular structure of the crystal. In the event of a cavity in the granite will be found crystals of quartz and feldspar, perhaps also of mica, as the cavity here means that each has had an opportunity to exercise its tendency to build itself regularly with something of the freedom which a perfect crystal requires. Another familiar example of crystallization is given by the ice covering a pond, which is as truly crystalline in structure as the perfect snow crystal, but here there are no crystals, and it is easy to understand why. The slow dissection of the mass, however, under the melting action of the sun, reveals something of the regularity in the molecular building, and the same thing is proved by an examination in polarized light. Sometimes, in the freezing of a little pool of water, the formation of the slender crystalline ribs of ice may be watched as they shoot out, forming a framework which may soon lose its distinctness as the entire surface is frozen over. Edward S. Dana, in his Minerals and How to Study Them, defines a crystal as the regular solid form which a chemical substance takes when it passes into the solid state from that of either a liquid or a gas, if under such conditions that the molecules are quite free to arrange themselves according to the direction of the attractive forces acting between them. The crystal is, therefore, the outward expression of the structure in the arrangement of those molecules, and its form is for this reason the most important of all the physical character of a given species, and the one which in general most definitely distinguishes it from others. Crystals are therefore, says Professor Dana, the perfect individuals of the mineral kingdom. The mineral quartz has a specific form and structure, as much as a dog or an elm, and is as distinct and unvarying as regards those characters, although owing to controlling causes during formation these forms are not always assumed. In whatever part of the world crystals of quartz may be obtained, they are fundamentally identical. It is interesting to note that a small crystal is just as perfect and complete an individual as a similar one of great size. There is among the crystals of a given species no such connection between size, on the one hand, and age and maturity on the other, that belongs to the individuals of a species in the animal and vegetable kingdoms. Some crystals are so minute as to be almost microscopic. Others may be of enormous size, as the gigantic quartz crystals occasionally found in the Alps, or the equally large beryl crystals from New Hampshire. A cave opened a few years ago at Maycomb, New York, contained 15 tons of great cubic crystals of fluorite. Another cave in Wayne County, Utah, contained a great number of enormous crystals of gypsum, some of them 3 feet or more in length. But the very small crystals and the like ones of enormous size are not essentially different, except in this comparatively unimportant respect of magnitude. It is seldom that any mineral crystallizes alone. Usually 2 or 3, under quite different crystalline laws, form together. They do this, comments Ruskin, absolutely without flaw or fault, when they are in fine temper, and observe what this signifies. It signifies that the 2 or more minerals of different natures agree somehow between themselves how much space each will want, agree which of them shall give way to the other at their junction, or in what measure each will accommodate itself to the other's shape. And then each takes its permitted shape and allotted share of space, yielding or being yielded to, as it builds till each crystal has fitted itself perfectly and gracefully to its differently natured neighbor. This seems to imply both concurrence and compromise, regulating all willfulness of design, and, more curious still, the crystals do not always give way to each other. They show exactly the same varieties of temper that human creatures might. Sometimes they yield the required place with perfect grace and courtesy, forming fantastic but exquisitely finished groups, and sometimes they will not yield at all, but fight furiously for their places, losing all shape and honor, and even their own likeness in the contest. All crystals belong to one of 6 classes or systems, which are named as follows: isometric, tetragonal, hexagonal, orthorhombic, monoclinic, and triclinic. The principal forms of the isometric system are the cube, octahedron, dodecahedron, the 2 trisoctahedrons, the tetrahexahedron, and the hexoctahedron. The cube has 6 equal faces, each one of which is a square, and the angle between any 2 faces is a right angle or 90 degrees. Galena and fluorite often occur in cubes. A regular octahedron has 8 like faces, each a triangle with equal sides and 3 equal angles, each 60 degrees. Magnetite is often in octahedrons. The rhombic dodecahedron has 12 equal faces, each of which is a rhomb with plane angles of 60 degrees and 120 degrees, while the angle between 2 adjacent faces is 120 degrees. This is a common form with garnet. A trapezohedron has 24 equal faces, each a 4-sided figure or trapezoid. There may be a large number of different trapezohedrons, all having the same general form but differing in the angles between the faces. A similar remark may be made about each of the other type forms of this system. A tetrahexahedron is a 24-faced solid, each face an isosceles triangle, and 4 together having the same position as the face of a cube. A hexoctahedron is a 48-faced solid. Each face is a scalene triangle, and 6 faces have the same general position as a face of an octahedron. The isometric system is defined as that system in which the faces are referred to 3 equal axes at right angles to each other. These axes pass through the centers of the crystals. It will be seen to be true of all these, as it is of all their combinations, that the arrangement of the faces is the same about each one of the 6 cubic faces, or in other words, about the ends of the 3 axes. There are also several other forms belonging to the isometric system, but which are described as half forms, or forms in which only half of the faces in the corresponding whole form are present. To them the rules of symmetry do not apply, but their faces are also referred to 3 equal axes at right angles to each other. The most important of these half forms are the tetrahedron and pyritohedron. The tetrahedron is a form with 4 equal triangular faces, each of them an equilateral triangle. The pyritohedron is a 12-sided solid, or dodecahedron, each face of which is a pentagon, but not here as with the pentagonal dodecahedron of geometry, a regular pentagon. In crystallography, the name dodecahedron is usually given only to the rhombic dodecahedron, and this form, the pyritohedron, takes its name from the species pyrite, or iron pyrites, because of common occurrence with it. The chief forms of the tetragonal system are the 2 square prisms and pyramids, and the right-sided prism and double 8-sided pyramid. The square prism has, like the cube, angles of 90 degrees between the faces, but it differs from the cube because the 4 vertical faces are not like the 2 end faces, or basal planes. This is often shown in a crystal by the difference in the smoothness of the 2 kinds of faces, or there may be an easy fracture or cleavage parallel to one set of planes and not to the other. The square pyramid looks somewhat like a regular octahedron, but here the faces are isosceles triangles, not equilateral, and the angle between 2 faces over a horizontal edge differs from that over one of the vertical edges. In fact, either angle is characteristic of a given species and differs from one species to another. The tetragonal system is defined as that in which the planes are referred to 3 axes at right angles, of which the 2 in the horizontal plane are equal, and the third or vertical axis is longer or shorter. In this system there are also some half forms, but only one, the sphenoid, is important. The sphenoid is a 4-faced solid looking like a tetrahedron, but differing from it since the faces are isosceles, not equilateral triangles. The chief forms of the hexagonal system are the 2 6-sided prisms, the 2 double 6-sided pyramids, and the 12-sided prism and double 12-sided pyramid. The angles of the hexagonal prism are exactly 120 degrees, and the terminal face or basal plane is a regular hexagon. The faces of the hexagonal pyramid are isosceles triangles, differing in angle according to whether the pyramid is more obtuse or acute. These angles, and the others that depend upon them, are characteristic for a given species. There is also another hexagonal prism and pyramid diagonal to the others and looking much like them. These 2 sets correspond to the 2 square prisms and pyramids of the tetragonal system. There is also a prism bounded by 12 similar faces, and a double pyramid bounded above and below by 12 triangular faces. This double 12-sided pyramid is often called a beryloid, because common with crystals of beryl. The hexagonal system is defined as that in which the planes are referred to 4 axes, 3 in a horizontal plane, equal and cutting each other at angles of 60 degrees, and the 4th vertical axis either longer or shorter. All hexagonal forms have 3 equal planes of symmetry, making angles of 60 degrees with each other. Also another set of 3 diagonal to the others, and a 7th plane parallel to the top or base of the crystal. There are several half forms in the hexagonal system, the most important being those of the rhombohedral system. The important forms are the rhombohedron and the scalenohedron. The rhombohedron is a 6-sided solid, each face of which is a rhomb. The scalenohedron is a 12-sided solid, looking a little like a double 6-sided pyramid, but the faces are scalene triangles and the edges zigzag up and down like that of a rhombohedron instead of horizontal as in the pyramid. The number of species crystallizing in the rhombohedral division of the hexagonal system is very large, and some of them, as for example calcite, are very highly complex. The characteristic forms of the orthorhombic system are the rhombic prism and pyramid. There are also other forms called domes. In a rhombic prism, the terminal face, formed by the basal plane, is a rhomb, not a square as in the square prism, which it somewhat resembles. There may be a great many rhombic prisms on the crystals of the same species, differing in the angles of their 2 edges. The rhombic pyramid in cross-section, like the prism, is a rhomb, and its edges belong in 3 sets, with different angles for each. These angles are characteristic for the crystals of a given species. The forms called domes derive their name from the Latin for house, domus, because when they meet above, they make a horizontal edge like a hip roof. These domes are often and very conveniently called horizontal prisms. In the orthorhombic system, the planes are referred to 3 unequal axes at right angles to each other. The grouping of faces about the extremities of each of the axes differs from that about the others, but there are 3 planes of symmetry which are all unlike. In an oblique rhombic prism, the end plane is rhombic in form, but it is oblique to the faces of the prism instead of being at right angles as described in the orthorhombic system. This oblique prism and a variety of other forms of the same group belong to the monoclinic system, in which the planes are referred to 3 unequal axes, 2 of the angles between which are right angles, while the third, in front, is obtuse. Monoclinic forms are very complex, and for technical description it is necessary to consult a larger work which has space to deal with the geometrical names of the prisms. They have only 1 plane of symmetry and appear as prisms, pyramids, and domes. Finally, there is one other group of forms which belong to the triclinic. In this system, the planes are referred to 3 unequal axes, all oblique to each other. Here all the intersections are oblique, and the like faces are in pairs only on opposite sides of a crystal. There is no plane of symmetry at all. Triclinic forms are even more complex than those of the preceding systems. Most of the crystals of minerals would give a very poor impression of nature's workmanship to one who expected always to see them exactly like carefully made models or like the regular geometrical figures drawn of them. The cubes of galena are often flattened or drawn out. But it is not really to be supposed that the forms are badly made, like a bad model. On the contrary, the size of the like faces on a crystal may vary, and so the shape of the solid as a whole, but the angles between them remain the same. Moreover, what is really essential is not the size or shape of each face, but the way in which the little molecules of which the whole is built up are arranged. For example, in a cube, the essential point is the fact that the structure is the same in the direction of the 3 cubic faces. It follows from this that in the cube not only are the angles between 2 adjacent faces always 90 degrees, but the 6 cubic faces are all similar, and therefore, if there is the easy fracture, called cleavage, parallel to one cubic face, there will be also the same cleavage parallel to the others. But the actual size of the faces is a matter of no importance. In fact, in one species the cubes are sometimes lengthened so as to be like fine hairs. Similar remarks can be made in regard to any distorted form. The symmetry in the molecular structure, and hence the angles between the faces, remain unchanged, although the symmetry of the external geometrical form is not that of the ideal crystal. A cube may in nature look like a square prism, for the angles between the faces are all right angles in both cases, but the molecular structure of the two is not to be confounded. In the square prism there is the same arrangement in the transverse directions, but a different one up and down. Hence, the square top of the crystal is not like the four similar oblong vertical faces, and there is cleavage parallel to one set and not to the other. From this variation it is evident that the practical study of natural crystals is much more difficult than the study of the models which gave the ideal forms. This is especially true because most crystals are so implanted on the rock or embedded in it that only part of the form has been developed. Thus, quartz crystals are often attached at one extremity, while only the other end has had a chance to grow freely. Or the crystals may be implanted upon a surface of rock so that only a series of minute faces and angles are visible. In such cases, the study of the form is really a difficult matter requiring much skill and experience. Besides the crystals that have been just spoken of, which, while they look at first irregular, are really perfect in the matter of the position of the faces and of the angles between them, there are others which are really deformed. Some peculiar condition attending the growth of the crystal, or perhaps some force which has acted upon it since it was formed, has resulted in bending or twisting it out of its normal shape, so that it may differ widely in angle from the regular form. Thus the faces may be curved as with the barrel-shaped crystals of pyromorphite, or like the peculiar convex faces common on crystals of the diamond, or the whole crystal may be bent, as is seen sometimes in crystals of quartz, stibnite, or of some kinds of chlorite. Aside from this curving and twisting, a crystal may have had its shape more or less changed by some force exerted in the rock since it was made. It may even have been broken and again cemented together, so that many irregularities may result. The salt crystals sometimes show distinctly one face only with the depression in the center, so that they are called hopper-shaped crystals. The cavernous crystals of pyromorphite and vanadinite give other examples. Crystals, often for the same reason, enclose foreign substances, sometimes in the form of liquids, as the quartz crystals that contain water, occasionally with a movable bubble of air. Or the liquid may be carbon dioxide, then often with a bubble of the same substance in the form of gas. In such cases the crystal must have been formed under great pressure, sufficient to keep the gas in the liquid form. Fragments of such crystals heated in the gas flame fly to pieces with great violence, because of the expansion of the gas formed from the liquid by heat. A peculiar class of false forms in which the crystalline shape does not belong to the chemical substance must be briefly described here. These are called pseudomorphs. Pseudomorph means false form, and the name is applied to a specimen having the form characteristic of one species and the chemical composition of another. This seemingly difficult contradiction is easily explained. Most chemical compounds are liable to undergo a change or alteration when subjected to certain conditions, as moisture, the action of alkaline waters, or acid vapors. Now, in these cases, if the original mineral was in crystals, the external form is usually preserved, often perfectly, while the chemical nature and the molecular structure have changed. The cases where the original substance has entirely disappeared and some other has come in to take its place are also called pseudomorphs. Thus, occasionally, quartz is found in the form of calcite, or of fluorite, or of barite, that is, pseudomorph after one of these. Also tinstone in the form of orthoclase feldspar, native copper in the form of aragonite. Even fossil wood may be said to be a pseudomorph of quartz or opal after the original wood, the structure of which it sometimes preserves with wonderful perfection. Some crystals occur isolated and alone, and then the form is usually developed on all sides, and with something of the regularity which the ideal model shows. Thus are found perfect garnets in mica schist or granite, and gypsum crystals in clay. But it is still more common to find crystals grouped together either irregularly, as in the majority of cases, or perhaps in parallel position, or again in the peculiar way called twinning. It is evident that, since the crystals on a single specimen of a species may be grouped in a great variety of ways, it is not always easy to decide whether a given case is a twin or not. This often becomes a matter requiring careful study, exact measurement of angles, and calculation, perhaps also of optical study. For example, it is common to find quartz crystals crossing each other at a great variety of angles, but true quartz twins are rare. The two parts of a true twin are usually symmetrical with reference to the twinning plane, and there is always the reversal of one half. One very common case of the grouping of crystals, which is apt to be confounded with twinning, is where the crystals or parts of crystals are parallel to each other, so that the axes of all have the same directions and are not inclined as in most twins. This is illustrated by a pile of cubes with faces parallel and having re-entrant angles between them. The crystals of many species are at times arranged in this way, but in every case it will be found that if the complex group is held so as to reflect the light from a window, the faces in adjoining crystals, which reflect at the same time, are always similar faces. An octahedron of fluorite, built up of a multitude of little cubes in parallel position, is a not very rare example of this. Parallel grouping is most interesting when the result is to build up a compound form with branching and rebranching parts like the limbs of a shrub or tree, and hence giving rise to a kind of structure called arborescent or dendritic. Here all the crystals or parts of crystals have their axes in the same direction. The common method of grouping of crystals, however, is quite irregular, and it is only exceptionally that twins or parallel groupings are noted. Minerals are not always in distinct crystals, like those of garnet or quartz, or even in aggregates of crystals. On the contrary, many of the specimens in a mineral cabinet show no crystalline faces at all, and then they are simply called massive. There are, however, important distinctions of structure between massive minerals. First of all, the distinction between crystalline and amorphous must be well understood. A piece of clear quartz, or rock crystal as it is often called, is said to be crystalline. A piece of glass, which very likely the eye alone could not distinguish from it, is amorphous or formless. For the mass of quartz, though it has no definite external form, but is bounded only by irregular fracture surfaces, is just as truly crystalline in structure as a perfect crystal. This is true because the essential idea about a crystallized mineral is that there should be the regular arrangement of the molecules out of which it is built up. It is not always easy, often impossible, with the eye alone to decide whether this regularity of structure exists. It is shown by the cleavage, but when there is no cleavage, it is usually by optical examination in what is called polarized light that this can be most easily proved. For example, the bright colors given by a thin fragment of a quartz crystal in polarized light shows at once, to one who understands the subject of optics, that it is crystalline in structure. In the glass, on the other hand, the molecules have no definite arrangement at all, and hence no action on polarized light. The changes of matter which appear in crystallization, distorted and denuded of their grace as they are often found to be, still reveal great laws which never fail, and to which all change is subordinate, and which appear as such to accomplish a gradual advance to lovelier order, and more calmly, yet more deeply animated rest. Nor has this conviction, says John Ruskin in his somewhat fantastic and humanizing, yet graceful Ethics of the Dust, ever fastened itself upon me more distinctly than during my endeavor to trace the laws which govern the lowly framework of the dust. For, through all the phases of its transition and dissolution, there seems to be a continual effort to raise itself to a higher state, and a measured gain through the fierce revulsion and slow renewal of the earth's frame in beauty and order and permanence. The soft white sediments of the sea draw themselves, in process of time, into smooth knots of sphered symmetry. Burdened and strained under increase of pressure, they pass into a nascent marble. Scorched by fervent heat, they brighten and blanch into the snowy rocks of Paris and Carrara. The dark drift of the inland river, or stagnant slime of inland pool and lake, divides or resolves itself as it dries, into layers of its several elements, slowly purifying each by the patient withdrawal of it from the anarchy of the mass in which it was mingled. Contracted by increasing drought till it must shatter into fragments, it infuses continually a finer ichor into the opening veins and finds in its weakness the first rudiments of a perfect strength. Rent at last, rock from rock, nay, atom from atom, and tormented in lambent fire, it knits, through the fusion, the fibres of a perennial endurance, and, during countless subsequent centuries, declining, or rather let me say, rising, to repose, finishes the infallible lustre of its crystalline beauty, under harmonies of law which are wholly beneficent, because wholly inexorable. All crystallization, says the same writer again, goes on under and partly records circumstances of this kind, circumstances of infinite variety, but always involving difficulty, interruption, and change of condition at different times. Observe, first, you have the whole mass of the rock in motion, either contracting itself and so gradually widening the cracks, or being compressed and thereby closing them and crushing their edges. And if one part of its substance be softer at the given temperature than another, probably squeezing that softer substance out into the veins. Then the veins themselves, when the rock leaves them open by its contraction, act with various powers of suction upon its substance, by capillary attraction when they are fine, by that of pure vacuity when they are larger, or by changes in the constitution and condensation of the mixed gases with which they have been originally filled. Those gases themselves may be supplied in all variation of volume and power from below, or slowly by the decomposition of the rocks themselves, and, at changing temperatures, must exert relatively changing forces of decomposition and combination on the walls of the veins they fill, while water, at every degree of heat and pressure, from beds of everlasting ice, alternate with cliffs of native rock, to volumes of red-hot or white-hot steam, congeals and drips and throbs and thrills from crag to crag, and breathes from pulse to pulse of foaming or fiery arteries, whose beating is felt through chains of the great islands of the Indian seas, and makes whole kingdoms of the world quiver in daily earthquake, as if they were light as aspen leaves. And remember, the poor little crystals have to live their lives and mind their own affairs in the midst of all this, as best they may. They are wonderfully like human creatures, forget all that is going on if they don't see it, however dreadful, and never think what is to happen tomorrow. They are spiteful or loving, and indolent or painstaking, with no thought whatever of the lava or the flood which may break over them any day, and evaporate them into air bubbles, or wash them into a solution of salts. And you may look at them, once understanding the surrounding conditions of their fate, with an endless interest. You will see crowds of unfortunate little crystals who have been forced to constitute themselves in a hurry, their dissolving element being fiercely scorched away. You will see them doing their best, bright and numberless, but tiny. Then you will find indulged crystals who have had centuries to form themselves in, and have changed their mind and ways continually, and have been tired and taken heart again, and have been sick and got well again, and thought they would try a different diet, and then thought better of it, and made but a poor use of their advantages after all. And sometimes you may see hypocritical crystals, pseudomorphs taking the shape of others, though they are nothing like in their minds, and vampire crystals eating out the hearts of others, and hermit crab crystals living in the shells of others, and parasite crystals living on the means of others, and courtier crystals glittering in attendance upon others, and all these besides the two great companies of war and peace, who ally themselves, resolutely to attack or resolutely to defend. And for the close you see the broad shadow and deadly force of inevitable fate. Above all this, you see the multitudes of crystals whose time has come, not a set time, as with us, but yet a time, sooner or later, when they all must give up their crystal ghosts, when the strength by which they grew, and the breath given them to breathe, pass away from them, and they fail and are consumed, and vanish away, and another generation is brought to life, framed out of their ashes.
There was a time when there was no life upon the earth, and therefore all matter was mineral. This lifeless period extended through untold ages, during which no organic substances were formed, and indeed could not have lived. When, however, the earth's surface became fit for organic introduction, life appeared, and thenceforward the mineral matter in earth, water, and air began to be acted upon by these new agencies, and the living vegetable and animal forms were produced. Life is continually evolving new forms and substance from apparently lifeless matter, endowing it with properties that in the earlier ages it did not possess, yet all life is based upon the mineral. In addition to the formation of living organisms from matter, it should be noted that these living organisms contain large quantities of such matter, such, for example, as carbonate of lime, the mineral which constitutes the limestones, the chalks, and the marbles, making up the shells of the shellfish and the calcareous covering of the coral polyp. And consequently, just as the animals owe a debt to the rocks, so quite a large portion of the rocks in the earth has been formed from the mineral remains of plants and animals, only again to be recombined into organic life. Thus it may be seen that in the same manner as there is a geographical cycle, there is also a mineralogical cycle, as the coral polyp takes the mineral calcium from the seawater and at death returns it to the mineral kingdom. Man is what he is today, not only because of the cell life of his ancestors, but also because of the mineral characteristics of the substances of which they were originally formed. A mineral has been well defined as a homogeneous substance of definite chemical composition, found ready-made in nature, and not directly a product of the decay or the life of an organism. It is evident from this definition that the term mineral would apply to an enormous variety of substances. However, only those which possess at least a fair economic importance will be treated in the following pages. One of the best known and at the same time one of the most valuable of minerals is the diamond. In regard to this stone, E.S. Dana, in his Minerals and How to Study Them, gives the following description. The diamond is usually found in distinct isolated crystals, most of them very small, but sometimes as large as a robin's egg or even larger. The crystals are commonly octahedrons, though less often some of the other forms of the isometric system are observed. The natural crystals before cutting, rough diamonds they are called, frequently have rounded edges and curved faces, or the faces show little pits. The hardness is higher than that of any other species, and the specific gravity is also high, 3.5. The luster is very brilliant. The brilliancy of the diamond, however, is much greater when cut with many facets than in the natural crystals. The most highly priced stones are colorless, but it sometimes occurs as pale yellow, green, pink, or blue. The diamond consists of pure carbon, and has thus the same composition as a piece of charcoal. Diamonds are used for cutting glass, and in the form of powder in grinding diamonds and other hard gems. The black, coal-like diamonds, set in a collar and rotated rapidly by machinery as a diamond drill, cut quickly through the hardest rocks, leaving a core behind, which is raised at intervals. A well boring is thus easily made. Graphite, or plumbago as it is often called, is usually found in massive forms which may be separated easily into thin leaves or plates, and hence are said to be foliated. Sometimes also it is finely granular and compact. It has the same composition as the diamond, consisting also of nearly pure carbon. It is, however, a different substance in its physical characters and is hence a distinct mineral. Note that they differ in crystalline form. Also, the diamond is hard and heavy, while graphite is soft and light. Graphite is the so-called black lead of the lead pencils, but it is only like lead in its color. It is an excellent lubricator because of its smooth, soapy character when pulverized. Also, mixed with clay, it is used for making crucibles because it is infusible and not affected by the heat of an ordinary furnace. In electroplating because it is a conductor of electricity. Carbon is also the element which forms the essential part of the different kinds of coal and of mineral oil or petroleum. Anthracite, the coal of eastern Pennsylvania, contains 85 to 95% of carbon and has a bright, shiny surface and conchoidal fracture. It burns with a pale, feeble flame without smoke. Bituminous coal is black to dark brown in color, often dull and with a pitchy luster. It contains less carbon than anthracite, usually 75%, and more hydrogen and oxygen. It burns with a yellow, smoky flame. Brown coal or lignite has a brown color, dull luster, often retains the structure of the original wood, and contains still less carbon, sometimes only 50%. These different kinds of coal and others related to them, though of great economic value, are not properly mineral species, since they have no definite chemical composition. The same remark applies to asphaltum, bitumen, mineral wax, or ozocerite, the many kinds of mineral resins including amber, and finally mineral oil or petroleum, all of which consist chiefly of carbon. Sulfur is another of the chemical elements occurring in nature. It is found in crystals of the orthorhombic system. A common form is an acute rhombic pyramid. It also occurs in masses and in powder. It is soft and, though brittle under the blow of a hammer, is easily cut by the knife. The specific gravity is about 2. It has a resinous luster and a bright sulfur yellow color and streak. The crystals are often clear and transparent. It is used for making sulfur matches. It is one of the 3 substances of which gunpowder is made, with charcoal and niter. It is used in preparing the rubber gum for overshoes and other purposes, also in making sulfuric acid, and in many other ways. Although it cannot be preserved in a mineral cabinet, ice, the solid form of water, is as truly a mineral as diamond or quartz. It occurs in crystalline forms of the hexagonal type, often of great complexity and beauty, as seen in snow crystals. The ice grains that make the pellets of hail, not infrequently occurring with summer thunderstorms, are also occasionally in clusters of crystals, somewhat resembling the hexagonal pyramids of quartz, though this is the exception. Generally, there is simply a concentric concretionary structure. The ice of the pools and ponds is always crystalline, though it is usually only in the first stages of the process of freezing that the crystals are separately visible. Arsenic is found occasionally as a mineral and then called native arsenic. It has a metallic luster and tin white color, but soon tarnishes on the surface to a dull dark gray. It is also brittle. It is used with copper and tin to form the alloy called speculum metal, useful for metallic mirrors because of the brilliant surface it takes when polished. The lead employed for making shot contains a small amount of arsenic. The compounds of arsenic find various uses, as pigments, sulfide, as a preservative, a poison for insects, white arsenic and Paris green, also in dyeing and medicine. Antimony, like bismuth, is usually included among the metals, for it has a high metallic luster, although its structure is crystalline and it is quite brittle. It is a very easily fusible metal and is useful in the arts because of the alloys which it forms with lead and tin, to which it imparts greater hardness and durability. Native antimony is a bright tin-white mineral with metallic luster and commonly showing brilliant cleavage surfaces. Bismuth is silver-white in color with a reddish tinge and has a bright metallic luster. It is rather brittle and shows a crystalline structure with perfect cleavages. It is, however, nearer to the true metals than either arsenic or antimony. Native bismuth is a rare mineral. Some of its alloys have the curious property of contracting instead of expanding with heat. Bismuth is also employed in medicine in the form of the subnitrate. Another compound is used as a cosmetic. Other uses are in calico printing and to give luster to porcelain. Molybdenite is the sulfide of the rare element molybdenum. Like graphite, which it much resembles, it occurs in foliated masses or in crystalline plates having a hexagonal outline, rarely in distinct hexagonal crystals. It is also very soft, with a soapy feel, and leaves a trace on paper. Gold is the most highly prized of the metals, valued because it serves as the money of all civilized people, and because of its use for ornaments. It is sometimes found in isometric crystals, as in octahedrons, but usually in plates or scales or wire-like forms. Also in larger masses, called nuggets. It is soft and can be cut by the knife. It is highly malleable and ductile, and especially remarkable because it can be hammered out into very thin sheets. The skillful gold beater can make the plate so thin as to transmit a faint greenish light. Gold occurs mostly in veins in the older crystalline rocks, especially associated with quartz. Gold quartz is quartz, often milky, which either shows little particles of gold scattered through it, or from which gold can be obtained, even if not visible to the eye, after the rock is crushed to powder and then washed to remove the lighter material. A large part of the gold of the world has been obtained from the sands and gravels produced by the disintegration of gold-bearing rocks. These gravels in the bed of a stream may be washed by the miner in his pan, or on a large scale where a powerful stream of water is thrown against the gravel bank, carrying away the lighter rock and leaving the heavy gold particles behind, usually in the form of little flattened scales. Platinum is reckoned among the nobler metals with gold, and like it is not attacked by any of the single acids. It has a rather dull gray color and is not a beautiful metal, although now more highly valued because of its practical uses than any of the metals except gold. It is rarely found in isometric crystals, as in cubes, more commonly in scales or in larger masses, up to 20 pounds, called nuggets, washed out of the gold sand. The fact that it is fused with great difficulty and is not attacked by ordinary chemical reagents makes it very valuable both to the chemist in the laboratory and in the chemical manufactories, where crucibles and dishes are made of it. It is also largely used by dentists. It has come into use of recent years for the attachments to the ends of the carbon wire in the incandescent electric lamp. Silver is one of the precious metals, useful alike as money, for ornaments of many kinds, and for utensils. The color is a fine silver-white when perfectly fresh, but it is easily tarnished, and the presence of sulfur in the atmosphere soon turns it black. Native silver is not an uncommon mineral, although the world's supply of the metal comes chiefly from its ores. It is like gold in its occurrence, sometimes, though rarely, in distinct isometric crystals, more frequently in arborescent or branching groups, in plates and scales or wire-like forms, sometimes in fine threads. It is highly malleable and ductile, and it is the best-known conductor for both heat and electricity. Mercury is a remarkable metal because it is a liquid at all ordinary temperatures, only freezing or becoming solid at -40 degrees. It has a silver-white color and brilliant metallic luster, and is so mobile that from early times it has been called quicksilver. Its density is high, 13.6, or higher than silver, 10.6, and lead, 11.4, and for this reason and because of its liquid form it is of great value for scientific purposes. It is used in most thermometers and barometers, and is employed in many experiments in the physical and chemical laboratories. It also has the property of forming a pasty mass or amalgam with some of the other metals, as gold and silver, also copper, zinc, tin, etc., but not iron, and is hence of great value in separating them from the rock in which they occur. Ordinary mirrors are made of glass, backed with an amalgam of mercury and tin. Mercury in various forms is also used in medicine, but in minute doses, for it is an active poison. Corrosive sublimate is a chloride of mercury. Native mercury is a rare mineral in nature, though occasionally found in minute globules scattered through the rock. The common ore is cinnabar, the sulfide of mercury, sometimes called natural vermilion, which is found in masses of a fine red color, and sometimes also in small rhombohedral or prismatic crystals. The luster is adamantine, and the color bright cochineal red, sometimes becoming dull and dark. The streak is scarlet. Crystals are usually perfectly transparent. Copper is one of the most useful of the metals, having been employed for utensils and in other forms, both as a metal and in different alloys since very early times. Of recent years, its use has been increased very largely because of its good conductivity for electricity. It thus forms the material of the wires of the dynamo machines, those by which the electrical current is carried for the electric light, the trolley, etc. Copper is also extensively used for electroplating, as in making stereotype plates. It forms further a large number of useful alloys, of which brass, an alloy of copper and zinc in the ratio of about 2:1, is the best known. In the various kinds of bronze, bell metal, gun metal, antique and metal bronze, etc., copper is also the prominent metal, alloyed with tin. In aluminium bronze, it is alloyed with aluminium. In German silver, it is alloyed with zinc and nickel. Copper is obtained in nature in the native state, and also from a variety of valuable ores, which are some of the most interesting and beautiful minerals. Fool's gold, chalcopyrite or copper pyrites, is the beautiful deep brass yellow copper mineral, often called yellow copper ore. The color is so golden that it is not infrequently mistaken for gold, especially when scattered in small particles through a mass of quartz. Malachite, the carbonate of copper, is a bright green mineral, often found with native copper, cuprite, and other copper ores because of the readiness with which they are converted into the carbonate by the action of the carbon dioxide present in the air or dissolved in the water. When close and compact, it can be cut and polished, and thus forms a handsome ornamental stone. Azurite, or the blue carbonate of copper, is not so common as malachite, but it is also a beautiful mineral, and when in large transparent crystals of a fine deep blue, it forms one of the most attractive specimens in a cabinet. The crystals are oblique rhombic prisms. Lead is one of the most important of the metals, and even pure is used for many purposes familiar to all, as for pipes to convey water and for shot and rifle balls. It has a dull blue-gray color. It is very soft and malleable. It is often alloyed with other metals, thus with tin in common solder and pewter, with antimony in type metal, with arsenic in small amount for making shot. White lead, the carbonate, is largely used in making paint, also the oxide, red lead. The supply of the metal, which is used so largely, is obtained from its ores, especially the sulfide, galena. The latter is one of the commonest of minerals, occurring in large deposits in many mining regions. It is also used for glazing common stoneware, and hence it is called potter's ore. Tin, one of the most important of metals for a great variety of technical purposes, occurs, if at all, only very rarely in nature in the native metallic state. The supply is obtained almost solely from a single ore, the mineral cassiterite or tin stone. The use of tin that first suggests itself is for tin plate, so largely employed for vessels, roofing, etc. This is simply sheet metal coated with metallic tin. Tin enters into many alloys, as the various forms of bronze, gunmetal and bell metal, etc., in which it is alloyed with copper. It also forms alloys with lead in pewter and several kinds of solder, with antimony in Britannia metal, with both lead and antimony in Queen's metal, and copper and antimony in Babbitt metal, with lead and bismuth in fusible metal. Cassiterite or tin stone occurs when crystallized in square prisms and pyramids and other related forms. Twin crystals are common. The crystals have a splendid adamantine luster and a brown color, sometimes nearly black. Iron may well be called the most important of all the metals. How large a place it takes in the work of the world is shown by the fact that each year some 50 million tons are produced from its various ores and turned into some of the many forms needed by man. The entire supply of iron which the world uses each year is obtained from its ores, in which the iron is in combination chiefly with oxygen. These ores are the minerals hematite, magnetite, and limonite. Siderite, the carbonate of iron, is also an important ore. The meteorites which occasionally fall to the earth often consist entirely of metallic iron. Magnetite suggests in its name its most striking character, that of being magnetic. All kinds are strongly attracted by a magnet, and one variety, called the lodestone, found for example at Magnet Cove, Arkansas, is a powerful magnet itself. It has a north and south pole, the power of picking up particles of iron or steel, as tacks, and also, when suspended, it sets with its poles north and south like a compass needle. Nickel, though formerly a little used metal, has become of much wider application in recent years. It is extensively employed now to plate many articles of steel, as knives, scissors, skates, etc., because unlike the steel, it does not tarnish or rust rapidly in the air. It is much used also when alloyed with copper for small coins, as the nickels or 5-cent pieces of this country, and similarly in Switzerland, Germany, and Belgium. Nickel steel has been found to be remarkably strong in withstanding the blow of a cannonball. The white alloy, called German silver, contains copper, zinc, and nickel in about the proportions of 5 to 3 to 2. There are not, however, many minerals which contain nickel. One of these is the sulfide millerite, another is nickelite or nickel arsenide. Cobalt is a metal related to nickel and often associated in nature with it in its various compounds, though of much more limited occurrence. As a metal, it is not used in the arts, but its salts, which are most brightly colored, have some applications. From the change in color that certain of them undergo on heating and on losing water depends their use as sympathetic ink. Cobalt glass, called smalt, has a beautiful blue ultramarine color, and ground up is used as pigment. Manganese is a metal which is closely allied to iron in physical characters and chemical relations. As obtained by the chemist, for it does not occur in nature, it is hard and brittle. Like iron, it forms numerous natural compounds, but they do not find many applications in the arts. Zinc is one of the most common and important of the metallic elements, but it is not certainly known to occur in the form of the metal in nature. It has a crystalline structure like metallic antimony, a white color and brilliant luster, soon however tarnishing. It is brittle at both low and high temperatures, but at 140 degrees centigrade it can be rolled into sheets. It is a most important metal in the arts. Iron in sheets and wire coated by zinc are protected from rusting, and are then said to be galvanized. A common use of the sheets is for roofing. Zinc is the negative metal in almost all forms of the chemical electric battery, that is, the metal at the expense of which the electric current is obtained. With copper it forms brass and related alloys. It is also one of the constituents in German silver. An alloy of zinc is used for making raised cuts in photo engraving. The white oxide is used for paint. Metallic zinc, as obtained from the furnace in ingots, is called spelter. Aluminium is one of the most remarkable of metals, because while it has great tenacity and is in a high degree sonorous and non-oxidizable in the air, it has a specific gravity of less than calcite, or only 2.5. In other words, it is only about 1/3 as dense as iron and 1/4 as dense as silver, which it somewhat resembles. Both as the pure metal, because of its low density, and in alloys, for example, with copper as aluminum bronze, because of their strength and other remarkable properties, it is highly useful. Corundum, oxide of aluminum, is, next to diamond, the hardest of minerals and one of great interest. Its clear blue varieties make the sapphire of jewelry, and the clear red the highly prized ruby, while the coarse and impure kinds, when pulverized, are emery, used for grinding. The luster, like that of most very hard minerals, is brilliant and adamantine, though rather dull in some massive kinds. The color is gray to brown or nearly black in many of the common varieties, called in part adamantine spar, bright blue in the variety called the sapphire, red in the ruby, purple in the oriental amethyst, yellow in the oriental topaz. Turquoise, the beautiful precious stone having the color of robin's egg blue, also bluish-green in less highly prized varieties, is a hydrated phosphate of aluminium, containing also a little copper phosphate, which is probably the source of the color. It occurs only in compact massive forms, filling seams and cavities in a volcanic rock. Calcium, whose oxide, CaO, is the familiar substance called lime, is a white metal somewhat resembling silver or tin. Its compounds are numerous and important, and it is indeed one of the most widely distributed of all the elements. Fluorite or fluorspar, calcium fluoride, is one of the most beautiful of minerals, occurring in cubic crystals and groups of crystals, sometimes very large and of a great variety of colors, from colorless to green, yellow, brown, red, and purple. The crystals are usually transparent and sometimes show on or near the surface a bright bluish color, quite different from that observed when they are looked directly through. The blue light extends within the crystal if it is placed in the direct sunlight. This phenomenon is called fluorescence, and having been first observed with fluorite, was named accordingly from it. Calcite, next to quartz, is the most common of mineral species, remarkable for its variety of form, both among the crystallized and uncrystallized varieties. It crystallizes in rhombohedrons and scalenohedrons of great variety and complexity of form, also in hexagonal prisms. A clear cleavage mass of high-grade calcite, such as that brought from Iceland, is called Iceland spar and is useful for optical prisms. This is because of its remarkable double refraction, or power of dividing a ray of light passing through it into two separate rays, so that a line seen through it appears double. Besides the crystallized kinds, there are those which have a granular structure, as statuary marble, and which sparkle in the light because of the multitude of cleavage faces. Other kinds are fibrous with a silky luster, like satin spar, also close and compact as an ordinary marble, and then of great variety of color, red, yellow, blue, black, and largely used for ornamental purposes. Some of these kinds of marble still contain shells, which come out distinctly when polished. Gypsum occurs in monoclinic crystals. Twin crystals are also common. Gypsum also occurs in fibrous forms called, like the similar variety of calcite, satin spar. It is easily distinguished from calcite because so much softer. The luster is pearly on the face of perfect cleavage, otherwise subvitreous. It is also silky in some fibrous forms, and in earthy kinds dull. When gypsum is heated and the water of crystallization driven off, gypsum becomes the anhydrous sulfate. This is done on a large scale and called plaster of Paris, which is extensively employed for making plaster casts, for the hard finish for walls, and for other uses. Gypsum is also largely used when ground up for improving soils. The variety alabaster is soft and easily cut into vases and other ornamental objects. Magnesium is the metal which is present in the oxide MgO called magnesia. It is a white metal resembling calcium and closely related to it chemically. In the form of a thin strip or ribbon, it burns readily in the air, yielding a very brilliant white light, which is often used as a source of illumination in photography. Barium is a metal only known in the laboratory, where it can be obtained from some of its compounds. It is a heavy metal, and takes its name from this fact from the Greek word for heavy, barush. All its salts have also high density. Strontium is the metal which is present in the various salts characterized by the beautiful red color which they give to the flame. The nitrate is thus used in fireworks and red fire. The hydrate is used for preparing and refining beet sugar and in extracting crystallized sugar from molasses. The metals sodium and potassium, though obtained with some difficulty, are interesting to the chemist because they combine so eagerly with oxygen. For this reason, they can be preserved only in some non-oxidizable medium, as oil, and a fragment of potassium placed in water takes fire and burns, uniting with the oxygen and liberating hydrogen. Sodium also decomposes water. Halite or rock salt, sodium chloride, is one of the few important minerals which is readily soluble in water and hence gives a decided taste. This taste is familiar to everyone, for halite is simply the natural form of table salt. It crystallizes in fine, clear, cubic crystals with perfect cubic cleavage. It is also found in granular cleavable masses. It has a vitreous luster and is colorless when perfectly pure, but from white it passes through various shades of red and yellow. Occasional patches of a deep blue are seen in the clear crystals. Borax, the sodium borate which is so familiar to the housekeeper, also occurs in nature, and on so large a scale in certain limited regions as to be extensively mined. It is found in monoclinic crystals, often of large size. They are clear at first, but lose water on exposure and become white and opaque. Borax finds many uses in the arts, as in making glass and soap, in soldering, and in medicine. Silicon is, next to oxygen, the most widely distributed of the chemical elements. In fact, it is estimated to make up about 1/4 of the Earth's crust. The element itself is known only to the chemist, who obtains it with some difficulty from its compounds. One form is that of reddish crystals, resembling those of the diamond and almost as hard. The common compound of silicon in nature is the oxide, SiO2, called usually simply silica. The well-known mineral quartz has this composition. Opal is another kind of silica, amorphous and containing some water. Quartz, the oxide of silicon, is the commonest of minerals, and in some of its varieties one of the most beautiful. It makes up most of the sand of the seashore. It occurs as a rock in the forms of sandstone and quartzite, and is a prominent part of many other important rocks, as granite and gneiss. It is a mineral which can be usually recognized by its form when crystallized, also by its hardness, conchoidal fracture, its glassy luster, and infusibility. The color varies widely. Crystals are usually colorless or nearly so, but also yellow and brown to nearly black. There are also pink, green, and red kinds. The massive forms vary still more, and the color is often in bands or clouds. Quartz appears under a great number of varieties, differing particularly in color and structure, and as many have been long used for ornamental purposes, they have received a number of distinct names. Rock crystal, the clear, colorless variety, when quite free from flaws, is used for spectacle glasses, and the Japanese make crystal spheres of rock crystal. Smoky quartz, having a smoky brown color, sometimes very dark. It is cut into ornaments, and in Scotland it is called cairngorm stone. Amethyst, a fine purple kind, also used for ornaments. A yellow variety of quartz crystal is called false topaz. Cat's eye may be mentioned, giving when polished a peculiar effect of opalescence, due to fibers of asbestos, which sometimes resembles the reflection from the eye of a cat. The same name is given to other stones having like effects. The highly prized cat's eye of jewelry is a variety of crystal beryl. Chalcedony is a kind having a waxy luster, either transparent or translucent, and varying in color from white to gray, blue, brown, and other shades. Agate is a variegated chalcedony, commonly with the colors arranged in delicate parallel bands, straight, curved, or zigzag. Onyx is, like much agate, made up of layers of different colors, usually white and black or white and brown, but the banding is straight, and the layers are in even planes. The stones may hence be used for cameos, the head being cut from one layer and the background formed by the other. Jasper is an impure opaque colored quartz, often red, colored by red iron sesquioxide, also brown or ochre yellow and dark green. Sometimes the red and green colors are shown in the same specimen, arranged in bands as in ribbon jasper. And flint, which is nearly opaque and has a dull color, usually gray, smoky brown, and brownish black. It breaks with a deeply conchoidal fracture and a sharp cutting edge, and is hence easily chipped, as by the Indians, into arrowheads or hatchets. Opal is a form of silica containing a few % of water. It does not occur in crystals, but in massive and amorphous forms only. These often show a peculiar effect called opalescence, like that of water containing a few drops of milk, and some varieties show a beautiful play of color. The color varies from white to yellow, red, brown, green, gray, and black. It is sometimes transparent, but more commonly only translucent. The most beautiful variety of opal is much admired because of the delicate play of colors, due to the optical effect of internal reflections. The colors are often seen on a white, also on a red ground. One kind of precious opal with a bright red flash of light is called the fire opal, and another kind is the harlequin opal. A beautiful opal found in Queensland shows an iridescent blue, sometimes like the effect of a peacock's wing. Infusorial earth is a kind of opal silica consisting of the microscopic shells of the minute vegetable organisms called diatoms, and as found in beds, sometimes of great extent, is properly ranked as a mineral and a variety of opal. Electrosilicon is the trade name of one kind much used for polishing silver. The siliceous shells are so fine that they do not scratch the surface. A layer of pure white infusorial earth is often found under a peat bed. It would not be easy to estimate the enormous number of the diatom shells which would be required to make up a cubic inch of it. Beryl is one of those species which are almost always in distinct crystals and usually in forms easy to recognize. It is also interesting because some varieties are used as a gem. The hardness of beryl is 7.5, or a little above that of quartz, and on this account and because of the beautiful color, it sometimes has its rank as one of the precious stones. The luster is vitreous or glassy. In this respect also it resembles quartz, and the color is usually some shade of green, bluish green in common beryl, clear mountain green in the variety called aquamarine, and a deep emerald green in the highly prized variety emerald. There are also light or dark yellow kinds, sometimes having a rich golden color, and occasionally white, and still more rare, pink kinds. Garnet is another species which, like beryl, is almost always in distinct crystals, and as these crystals are commonly isolated and scattered through the rock, it is not difficult to recognize them. There are, however, massive kinds needing some skill for their identification. These are occasionally used in the same way as emery, though much less hard. The luster is vitreous, and the color, while most commonly red, varies also from the colorless kinds to those which are yellow, brown, black, and green. The micas are characterized before all by their very perfect cleavage, in consequence of which they admit of being split into leaves much thinner than a sheet of paper. In fact, it is difficult to set any limit to the extent to which this process may be carried. These leaves or sheets are usually very elastic and spring back with force when bent. The micas are silicates of alumina with potash, rarely soda or lithia, also magnesia, iron, and some other elements. Chrysolite, or olivine, is a silicate of magnesia and iron having a vitreous luster and bright yellowish-green color. The luster is vitreous, and the color, besides that mentioned, may be yellow to olive-green and brown. Chrysolite, golden stone, from the Greek chrysos, gold, and lithos, stone, is an old term in the mineralogy of former times given to a number of yellow minerals used as gems, thus to beryl, topaz, chrysoberyl, and zircon. Tourmaline is one of the most attractive minerals among the silicates. Its varieties show a greater range of color than any other species, not even excepting fluorite, and some of the clear pink and green kinds make beautiful gems. It is also always found in prismatic crystals, bounded often by 3 sides, sometimes by 6, also by 9, and not infrequently rounded so that there are no distinct faces to be distinguished at all. Topaz is another gem silicate, beautiful in its fine crystals and in its brilliancy of luster and color. It occurs in prismatic crystals, terminated by rhombic pyramids, sometimes acute, sometimes obtuse. There are also coarse crystals and massive fibrous forms, but these last are not so common. The perfect basal cleavage of topaz is one of its most characteristic points. Hard as it is easily broken in a direction across the prism, and will yield thin plates with very smooth faces. The luster is vitreous, and the color varies from colorless to white, wine yellow, and blue. Pink topaz is sometimes found. Serpentine is a remarkable mineral because of the variety of massive forms it assumes, although it is not known to occur in crystals of its own. The crystals of serpentine which are found are what are called pseudomorphs, having been derived from some other species by chemical change. The most peculiar variety is the fine fibrous kind called chrysotile, not to be confounded with chrysolite. This usually occurs as thin seams in the mass of mineral. Chrysotile may be separated into fibers, very flexible and as soft as the finest silk. This variety is popularly called asbestos, but there is another kind of asbestos of rather similar appearance, which is a variety of the mineral amphibole. These brief descriptions of the principal minerals may serve in some measure to clarify and determine the reader's knowledge of the metals he handles and the stones and rocks whereon he treads. But even so, there are fields illimitable of investigation. These might be pointed out in almost any of the minerals, but the question has been so excellently well worded by Ruskin with regard to marble that it may serve for all. Quote, "Another singular point in the business to my mind," unquote, he says, quote, "is that these stones, which men have been cutting into slabs for thousands of years to ornament their principal buildings with, and which under the general name of marble have been the delight of the eyes, and the wealth of architecture among all civilized nations, are precisely those on which the signs and brands of these earth agonies have been chiefly struck, and there is not a purple vein nor flaming zone in them which is not the record of their ancient torture. What a boundless capacity for sleep and for serene stupidity there is in the human mind. Fancy reflective beings who cut and polish stones for 3,000 years for the sake of the pretty stains upon them, and educate themselves to an art at last, such as it is, of imitating these veins by dexterous painting, and never a curious soul of them all that while asks, what painted the rocks?" Unquote.
Among the many minerals which constitute the crust of the earth, there are some which are of such character and occur in such quantities that they possess commercial value, and it is profitable to separate them from their neighbors and apply them to the service of mankind. The process employed in the extraction of these useful minerals are classified under the term mining. The origin of mining retreats into such antiquity as to be most obscure. It is certain, however, that the Phoenicians and Egyptians at the earliest periods of history had an abundance of metals. The Egyptians had mines of copper, silver, and gold in productive operation both on the Ethiopian and Arabian border. The Sinaitic Desert contains the ruins of mining works, probably operated by the Egyptians. Abraham found gold and silver in use among them. In the time of Alexander, gold, silver, copper, and iron were obtained in Ethiopia. In Asia Minor, the gold mines formerly owned by Croesus were worked down to the time of Xenophon, but Strabo says that in his days they were exhausted. The Athenians worked rich silver mines in Attica and gold mines in Thrace. Before the time of the Romans, mining was carried out in many parts of Western Europe. After the conquest of Caesar, the tin of Cornwall was shipped first to the Isle of Wight and thence to the coast of Gaul, where it was loaded upon horses and transported to Marseilles. The early Romans did not work the mines of their native land, but by their numerous conquests gained control of all of the important mines of the ancient world. Traces of ancient mining in the United States are found to the copper region of Lake Superior and to certain districts in New Mexico. In both cases, the implements used seem to have been rude hammers of stone. It is evident that in ancient times muscular force, assisted only by applications of fire and occasionally by the power of water, was the miner's resource. A most suggestive picture of rude mining operations is given in the book of Job 28, 1-11, of which Conant's translation brings out the points very strikingly. "For there is a vein for the silver and a place for the gold which they refine. Iron is taken out of the dust, and stone is fused into copper. He puts an end to the darkness, and he searches out to the very end, stones of thick darkness and of death shade. He drives a shaft forgotten of the foot, they swing suspended far from men. The earth, out of it goes bread, and under it destroyed is with fire. A place of sapphires are its stones, and it has clods of gold. Against the flinty rock he puts forth his hand. He overturns mountains from the base. In the rocks he cleaves out rivers, and his eye sees every precious thing. He binds up streams that they drip not, and the hidden he brings out to the light." Pliny gives a similar description of shaft-sinking operations. Quote, "Elsewhere, pathless rocks are cut away and are hollowed out to furnish a rest for beams. He who cuts is suspended with ropes. They go where there is no place for the footprints of man." The removal of surface material by sluicing was also practiced in ancient times in Spain. The Aztecs had an extensive metallurgical industry. "They understood how to sink shafts and run tunnels," says John S. Hittel, "how to wash gold from alluvial deposits, how to use the bellows and furnace in smelting the ores of copper, tin, lead, and silver, and how to cast metals. They had a little tin and considerable quantities of lead." The Quecans were not less skillful, and they quarried stone with veins of silver on a large scale. They alloyed gold, silver, and tin with copper, so that these metals must have been mined. and a complete knowledge of fluxes in the fusion of ores was known to them. Barbarism, generally, which is often regarded as being coupled with the Bronze Age, was obviously possessed of mining, and not only of mining, but of smelting also. Before proceeding with any further discussion of the useful minerals, it is well to understand what is meant by the expression ore deposits. This is clearly set forth by Heinrich Ries in his Economic Geology. Quote, "The term ore deposits," he says, "is applied to concentrations of economically valuable metalliferous minerals found in the Earth's crust, while under the term ore are included those portions of the ore body of which the metallic minerals form a sufficiently large proportion to make their extraction profitable. A metalliferous mineral or rock might therefore not be an ore at the present day, but become so at a later date because improved methods of treatment or other conditions rendered the extraction of its metallic contents profitable." A few metallic minerals serving as ores, such as gold, copper, platinum, or mercury, sometimes occur in a native condition, but in most cases the metal is combined with other elements, forming sulfides, hydrous oxides, carbonates, sulfates, silicates, chlorides, phosphates, or rarer compounds, the first 5 of these being the most numerous. A deposit may contain the ores of one or several metals, and there may also be several compounds of the same metal present. The terms rich and poor, as applied to ores, are used with great frequency, although most indefinite and often meaningless. Under very favorable conditions, it is possible to profitably work an ore of given value at one locality, while if found under other less favorable conditions at another point, it might be almost worthless. The important ore deposits are not numerous. There are many other ores mined for the metal they contain, but they are either of small economic importance or occur in small quantities in nature. Iron is an abundant constituent of the Earth's crust, and yet few minerals are capable of serving as ores of this metal, and 5 ores supply the greatest amount of the world's iron: magnetite, hematite, limonite, siderite, and pyrite. Magnetite occurs in the United States, 1, as lenticular masses commonly in metamorphic rocks, 2, as more or less lens-shaped bodies in igneous rocks, 3, as sand on the shores of lakes and seas, and 4, as contact deposits, that is, those which form along the surface of contact of igneous and sedimentary rocks. The first class includes the most important deposits now worked in this country. The second and third groups run too high in titanium to have commercial value at the present time, and undoubted representatives of the fourth class of commercial value are not worked. There are some, it is true, which occur along the contact of an intrusive and sedimentary rock, but their origin is ascribed to meteoric circulations. Of all the iron ores, hematite is by far the most valuable, chiefly on account of its easier reduction, but also because of the greater richness of the known important deposits. Most of the deposits mined belong to the replacement type, that is, they are the result of the replacement of a fissure-filling material. Limonite may occur under a variety of conditions and associated with different kinds of rocks, but 2 important types are recognized, namely bog ores and residential limonites. The bog ores are formed by the precipitation of limonite in swamps, ponds, or lakes. Such ores are usually impure from an admixture of sand or clay, which has been deposited at the same time, and are rarely of any thickness. They are of no commercial value in the United States, but are mined more extensively in Sweden and Canada. The residual limonites are a much more important class and are formed by the weathering of pyritiferous veins, or more often from the weathering of ferruginous rocks. Siderite is the least important of all ores of iron mined in the United States, both on account of the small quantity and its low iron contents. When of concretionary structure, with clayey impurities, it is termed clay iron stone. Pyrite, though widely distributed in nature, is not used as an iron because of the large amount of sulfur contained. Copper-bearing minerals are not only numerous, but widely, although irregularly, distributed. More than this, copper is found associated with nearly every variety of ore or ore deposit. Nevertheless, but few minerals serve as ores of copper. All the largest copper deposits in the world may be divided into 2 groups. 1. Deposits formed by ascending, circulating, probably hot waters, the ores being deposited in fissures, pores, spaces of brecciation, or sometimes replacement of the rock. And 2. pod or lens-shaped deposits in crystalline schists, which may represent concentration of material from a disseminated condition in the surrounding rocks. The ores of lead and zinc occur very often associated with each other. Of these, galena is the commonest lead ore, while others are usually found where superficial oxidation of the deposit has taken place. Of the zinc ores, sphalerite, also known as blend, jack, or blackjack, is by far the most important. With few exceptions, zinc is constantly associated with lead, and at times, as in portions of the Cordilleran region, carries silver or even gold. Gold and silver are obtained from a variety of ores, in some of which the gold predominates, in others silver, while in still a third class, these two metals may be mixed with the baser metals, lead, copper, and zinc. Few gold ores are absolutely free from silver, so that a separate treatment of the two is more or less difficult. Gold occurs in nature chiefly as a native gold mechanically mixed with pyrite, or as a telluride, such as calaverite. Most of the gold and silver mined in the United States is obtained from fissure veins, or closely related deposits of irregular shape in which the gold and silver ores have been deposited from solution, either in fissures or other cavities or by replacement. Considerable gold and a little silver is obtained from gravel deposits. Some true contact deposits are known. Gold has been found to occur in rare instances as an original constituent of igneous rocks and also metamorphic ones, but there are no known deposits of commercial value belonging to this type. The gold and silver ores are sometimes grouped as placers or gravel deposits. These serve chiefly as a source of native gold, but may and often do contain a little silver, much of which is never separated from the ore in which it occurs. 2. Quartzose or dry ores, in which the gold and some silver are found in quartz gangue and are either freed or mixed with sulfides, commonly pyrite. 3. Gold and silver-bearing copper ores. These are widely distributed throughout the United States and exhibit great differences in form and age. Neither do all of the occurrences yield much gold or silver. And 4. Gold and silver-bearing lead ores. This class includes a variety of deposits containing much lead and also silver, with gold usually in subordinate amounts. Since gold and silver ores so vary in their mineralogical associations and richness, the metallurgical processes involved in their extraction are varied and often complex. Those ores whose precious metal contents can be readily extracted after crushing by amalgamation with quicksilver are termed free milling ores. This includes the ores which carry native gold or silver and often represent the oxidized portions of ore bodies. Others, containing the gold as telluride, or containing sulfides of the metals, are known as refractory ores and require more complex treatment. These, after mining, are sent directly to the smelter if sufficiently rich, but if not, they are often crushed and mechanically concentrated. The smelting process is also used for mixed ores, the latter being often smelted primarily for the lead or copper contents, from which the gold or silver is then separated. Low-grade ores may first be roasted, and the gold then extracted by leaching with cyanide or chlorine solutions. The introduction of the cyanide and chlorination process, which are applied chiefly to gold ores, has permitted the working of many deposits formerly looked upon as worthless, and in some regions, even the mine dumps are now being worked over for their gold contents. The silver-lead ores form a large class which are widely distributed in the Cordilleran region and not only supply most of the lead mined in the United States, but in addition may also, and often do, carry variable quantities of silver, gold, and copper. The deposits as a whole present a variety of forms. The associated rocks are often faulted, and the ore bodies are commonly oxidized above, so that the altered portions require the different metallurgical treatment from the sulfide ores found below. Secondary enrichment has in some cases raised the grade of the ore. Aluminium is one of the few metals whose ores do not present a metallic appearance. Many different minerals contain aluminium, but it can be profitably extracted from only a few. Common clay, for example, presents an inexhaustible supply, but the chemical combination of the aluminium in it is such that its extraction, up to the present time, has not been found practicable. While many different minerals contain manganese, practically the only ones of commercial value are the oxides and carbonates, and in this country only the former. The silicates are not used as a source of manganese owing to their high silica percentage. The several ores of manganese are often intimately associated, the pyrolusite generally assuming a crystalline and the silomelane a massive character. Manganese oxides are also often intermixed with more or less oxide of iron, and considerable amounts of the metal are obtained from magniferous zinc, silver, or iron ores. Since such manganese is used in iron reduction, the last association is of importance. Mercury ores are not confined to any particular formation, but are found in rocks ranging from the Ordovician to recent age in different parts of the world. Nor are they peculiar to any special type of rock. Although igneous rocks are often found in the vicinity of them, they occur as veins, disseminations, or as masses of irregular form. The most important ore of antimony is stibnite, and the metal is rarely obtained from any other mineral, although native antimony has been sparingly found. The stibnite, together with a gangue of quartz, and sometimes calcite, usually forms veins cutting igneous, sedimentary, or metamorphic rocks. Antimony has been found at a number of localities in the Cordilleran region, but the great distance of deposits from the railroad, together with the fact that the smelting plants are located in the east, make them of little commercial value, and no domestic production has been reported since 1901. Moreover, the large output of antimony ores and metal abroad, combined with low ocean freights and the absence of any import tax on crude antimony, are of themselves discouraging to domestic competition. Nickel and cobalt can best be treated together, for nearly all the ores containing one are apt to carry some of the other. And furthermore, in smelting, the two metals go into the same mat and are separated later in the refining process. The nickeliferous pyrrhotite is the most widely distributed of the nickel ores and may carry small amounts of cobalt. It is also called magnetic pyrites. The percentage of nickel ranges from a trace to 6%, but an increase above this brings it into pentlandite. The ores of platinum are native platinum and sperrylite. The former is commonly found in placer deposits, but has also been noted in basic igneous rocks rich in olivine, such as peridotite, or in serpentine derived from it. The sperrylite never occurs in large quantities, but has been found in association with nickel and copper ores. Iridosmine and osmiridium are also known to carry platinum. The nuggets found in placers are often regarded as being pure native platinum. This is only partly true. The chief ore of tin is cassiterite with 78.6% metallic tin, but owing to the presence of impurities, the ore rarely shows this composition. Its hardness, imperfect cleavage, non-magnetic character, high specific gravity, and brittleness help to distinguish it from other minerals that are liable to occur with it. Stream tin is the name applied to cassiterite found in placers. Metallurgy is defined as the art of extracting metals from their ores and adapting them to the various processes of manufacture. That this art was practiced in very early times is indicated by references to the use of metals in the oldest written records of the world's history. Among the many stages in the development of primeval man, none can have been of greater moment in the struggle for existence than the discovery of the metals and the means of working them. The names generally given to the three prehistoric periods of man's life on Earth, the Stone, the Bronze, and the Iron Age, imply the vast importance of the progressive steps from the flint knife to the bronze celt and lastly to the keen-edged steel weapon or tool. The metals chiefly used have been gold, silver, copper, and tin, the last two forming the alloy called bronze, iron, and lead. Of all metallurgical processes, that of separating of lead from its ores is the oldest. Lead smelting was known to the ancient Hebrews, and silver ornaments were found on the site of ancient Troy that were so pure as to show that the Trojans know how to separate silver from lead. Lead ores were wrought by the ancient Egyptians perhaps 3,000 years BC. The value of iron in ancient times is well brought out by the fact that in Homer's Iliad, a mass of iron is mentioned as being one of the prizes at the funeral games of Patroclus. Metallurgical processes of the present day may be divided into mechanical and chemical. Under mechanical are included the various processes of ore dressing or concentration, the object of which is to separate nearly pure mineral from what is of little or no value. The methods of extracting metals directly from the crude ore or from the mechanically separated concentrates fall under three classes. 1. Extraction of the metal from oxides and carbonates by the reducing action of carbon and the treatment of sulfides by the oxidation of the sulfur contained. 2. The extraction of a metal by getting it in solution and replacing it by another. And 3. Amalgamation, or bringing the metal in contact with quicksilver, in which it forms an amalgam. Most metals are obtained ultimately by the use of heat, either by treating the crude ore or the concentrates obtained by some method of ore dressing. It is well, however, before beginning a discussion of the metallurgy of iron and steel, to define just what is the iron and steel of commerce and industry. In Henry Marion Howe's Iron, Steel, and Other Alloys, they are described as composites of granitic substances, intimate mechanical mixtures or conglomerates of microscopic particles of certain quite distinct, well-defined, simple substances in widely varying proportions. The chief of these substances are ferrite, the microscopic particles of nearly and perhaps perfectly pure metallic iron. It is magnetic, very soft and ductile, but relatively weak, with a tensile strength of about 45,000 pounds per square inch. It is of the isometric system. It always forms a very important part of slowly cooled iron and steel in general. Cementite, a definite carbide of iron, Fe3C, containing 6.67% of carbon, very brittle, harder than hardened steel, scratching glass and feldspar but not quartz, and magnetic. The carbon in slowly cooled steel is chiefly or wholly present as cementite. Graphite, a characteristic component of gray cast iron, of which it usually forms from 2 to 3.5%. It is pure or nearly pure carbon. When it forms during the solidification of the metal, as is usually the case, it occurs in very thin laminated plates or flakes, often 1/8 inch or more in diameter. When it forms within the solid metal at temperatures materially below the freezing point, it occurs, at least under certain conditions, in very fine powder and is then called temper graphite, the temper carbon of Ladybur. Slag, the characteristic component of wrought iron, which usually contains from 0.2 to 2% of it. It is essentially a ferrous silicate, and it is present in wrought iron simply because this variety of iron is made by welding together pasty granules of iron in a bath of such slag, without subsequently melting the resultant mass or in any other way giving the envelopes of slag thus imprisoned a chance to escape completely. The great classes of iron and steel of chief value to the engineer, and probably to the world at large, are essentially intimate mixtures, or conglomerates of the first two strikingly different microscopic constituents, ferrite extremely soft and ductile, cementite extremely hard and brittle, the former like copper, the latter like glass. The properties of several of the classes may indeed be influenced, and very profoundly, by thermal and mechanical treatment, and by the presence in certain of them of slag or of graphite. But the fact of which our attention should be concentrated at first is this, that the difference in properties between the different industrial classes of iron and steel are due chiefly to differences in the ratio which the ferrite bears to the cementite. What has just been said does not apply, it is true, to what is called hardened steel, but it does apply to the great industrial classes of wrought iron and of steel, such as ship, rivet, fencing wire, tube, rail, and tin plate steel, and indeed all structural steels, whether for plates, beams, eye-bars, angle irons, or any like object. The steels which are especially soft and ductile, example the rivet and boilerplate steels, consist chiefly of the soft, ductile, copper-like ferrite, as do those with very high electric conductivity, such as telegraph and telephone wires. In these steels, the proportion of cementite may not exceed 1% of the whole, the rest consisting almost wholly of ferrite. The harder steels, like rail steels, which are called upon to resist abrasion, Example, the grinding action of the car wheels intensified by the presence of sand between wheel and rail, have a much larger proportion of cementite. About 93% of their total mass is made up of ferrite, and the remaining 7% consists of cementite. This quantity of cementite suffices to increase greatly the resistance to abrasion, while the loss of ductility, which it causes, though very marked, is not dangerously great. Naturally, as the proportion of cementite in steel increases and that of ferrite decreases, the ductility diminishes continuously and the hardness increases continuously. The tensile strength, however, reaches a maximum when the cementite amounts to about 15% of the whole and the ferrite is about 85%. With further increase of cementite, the tensile strength again decreases. The constitution of steel is not in general reported in the percentages of ferrite and cementite, nor indeed are most engineers and metallurgists of today sufficiently familiar with the aspect of the subject to speak of it with confidence. But this is the aspect with which the practitioners of the near future must face, and it is also that which makes possible an understanding of the relation between the composition and properties of these different classes of iron and steel. Instead of saying that a certain kind of steel, for instance rail steel, contains so much cementite and so much ferrite, it is customary to report simply the carbon which that cementite represents. Graphite is an important constituent of cast iron, especially of gray cast iron, but may be regarded as either absent from steel or, if present, only in unimportant quantities. Gray cast iron, the only kind of cast iron which can be widely used by engineers, may be regarded as a conglomerate of the second degree, for it consists first of a mechanical mixture of ferrite with cementite, quite as steel does, while through this mixture as a matrix there is scattered much free carbon in the form of sheets of graphite. White cast iron typically would consist of cementite and ferrite quite as structural steel does, but with a much larger proportion of cementite rising even to 67%. Say 4.5% of carbon. Hence the extreme hardness and brittleness of this class of cast iron, so extreme as to exclude it from most engineering uses. Wrought iron consists essentially of a metallic matrix identical with low carbon steel, in which is mechanically mixed a small quantity of slag, a silicate of iron. This slag is not unimportant, yet it is far less important than the ferrite and cementite of the matrix. Steel, hardened by sudden cooling from a red heat, consists essentially of austenite, a solid solution of carbon in iron of varying degrees of concentration. When austenite contains as much as 1% of carbon, it is intensely hard and brittle, and indeed its hardness and brittleness are roughly proportional to the quantity of carbon which it contains. Hence, steel for purposes which require extreme hardness, such as files and other tools for cutting metals and even wood, have from about 3/4 to 2% of carbon, enough to give the degree of hardness required for the special purpose, but not enough to cause a prohibitory degree of brittleness, and they are hardened by sudden cooling. Besides the cutting tools, armor plate and projectiles are made of hardened steel, and therefore consist essentially of austenite. Alloy steels have come into extensive use for important special purposes, and a very great increase of their use is to be expected. The chief ones are nickel steel, manganese steel, chrome steel, molybdenum steel, and tungsten steel. The general order of merit of a given variety or specimen of iron or steel may be measured by the degree to which it combines strength and hardness with ductility. Nickel steel, which endures well the effect of sudden shock, is used widely for marine shafting. It has been used tentatively for railroads, but while it has the stiffness and resistance to wear which they require, too many rails have broken in use. As actually made, manganese steel contains about 12% of manganese and 1.5% of carbon. Its ductility, to which it owes much of its value, is profoundly affected by the rate of cooling. Sudden cooling makes the metal extremely ductile, and slow cooling makes it brittle. Its behavior in this respect is thus the opposite of that of carbon steel. Its great hardness, however, is not materially affected by the rate of cooling. It is used extensively for objects which require hardness and ductility, such as rock-crushing machinery, railway crossings, minecar wheels, and safes. Chrome steel, which usually contains about 2% of chromium and 0.8 to 2% of carbon, owes its value to combining, When in the hardened or suddenly cooled state, intense hardness with a high elastic limit so that it is neither deformed permanently nor cracked by extremely violent shocks. For this reason, it is the material generally, if not always, used for armor-piercing projectiles. Tungsten steel, which usually contains from 5 to 10 and sometimes even 24% of tungsten and from 0.4 to 2% of carbon, is used for magnets because of its great retentivity, and for lathe and similar metal cutting tools, which are to cut off a very thick slice at each stroke. The great friction, due to the thickness of the cut, heats the tool to a temperature at which the temper of common or carbon steel is drawn. The merit of tungsten steel is that, like manganese steel, it retains its extreme hardness even after it has been heated to 400 degrees centigrade, or 750 degrees Fahrenheit. Under these conditions, the Taylor and White variety retains its cutting power even when the friction is so great that the chips of metal cut are so hot as to glow visibly, and even the edge of the tool itself grows red hot. Molybdenum steel is now often used instead of tungsten, 1% of the former element replacing 2% of the latter, so that the ratio between their effects appears to be that which their atomic weights would indicate as probable. In other words, 1 molecule of molybdenum appears to have the same effect as 1 molecule of tungsten. Today, practically all of the iron ore mined is smelted in the iron blast furnace, and there converted into cast or pig iron. And this is the case whether the resultant iron is to be used in the form of cast iron or whether it is to be converted into one of the two other great commercial classes of iron, wrought iron and steel. It is true that there are many direct processes by which wrought iron or steel may be made directly from the ore without first converting it into cast iron. For example, without first putting it into more carbon and silicon than it needs in its finished form, and then taking them out at great expense. But the processes of today are a little more than historical of scientific interest. Whatever promise that they may have made in recent decades has been killed by the great cheapening of the blast furnace process. The blast furnace is an enormous shaft, in many cases as much as 100 feet high and 25 feet maximum inside diameter. The furnace is at all times full from top to bottom of a column consisting of coke or other fuel, limestone, and iron ore, though the lower part of this column consists of fuel only. The ore, flux, and fuel are charged through a hopper at the top of the furnace and form a continuous column extending from the top to the bottom. Through openings called tuyeres at the bottom of the furnace, a powerful blast of air, usually highly preheated, is introduced. This burns the fuel, thereby generating an intensely high temperature sufficient to melt the ore, the iron of which has, by the time it has descended to this region, become reduced to the metallic state. Thus the whole column of solid materials descends slowly as its lower end is eaten away, the fuel which it contains being burned away by the blast and the rest of the material being melted away by the heat from the combustion of this fuel. In addition to the descending column of solid material, there is an ascending column of hot gases. The oxygen of the blast introduced at the tuyeres is quickly converted into carbonic oxide by its reaction with the carbon of the fuel which it there meets. Very soon after entering the furnace through the tuyeres, the atmospheric oxygen has been converted into carbonic oxide, which, together with the atmospheric nitrogen of the blast, sweeps up through the furnace in enormous columns at great velocity. There is thus two columns moving in opposite directions, a solid column of ore, flux, and fuel descending very slowly, and a swiftly rising column of hot gases. Any given lump of the solid material passes through the furnace in about 12 to 15 hours, while any given particle of oxygen or nitrogen entering at the tuyeres passes through and quickly escapes at the top, its passage occupying probably only a small fraction of a minute. The iron ore always contains, besides iron oxide, a considerable quantity of siliceous or earthy material called gangue, and the fuel also contains a certain amount of ash. These materials, the gangue and the ash, together with the lime of the limestone, unite to form a single molten mass, the slag, which floats on the top of the molten iron. Two deep holes are provided at the lower end of the furnace, one called the tap hole, at its very bottom for drawing off the molten iron at intervals, and the other called the cinder notch, a very little above this for drawing off the molten slag. These holes are closed with plugs of clay, except at a time when the molten materials are drawn through them. While these two columns, the descending solids and the ascending gases, pass each other, and the hot gas is sweeping up swiftly, the initially cold solid materials descending slowly, the heat of the gaseous column is recovered by being transferred to the descending solids, so that although the temperature of the gases in the neighborhood of the tuyeres is about 2,912 degrees Fahrenheit, the temperature of those which escape from the top of the furnace is only about 572 to 752 Fahrenheit, owing to the fact that the fuel is burned in immediate contact with the solid materials which it is to heat, and that the products of the combustion are thoroughly cooled in their long upward travel in which they are exposed to cooler and cooler masses of descending solid materials. The thermal efficiency of the blast furnace is very high. The purifying reactions are brought about by 1. In the puddling process by stirring iron oxide in the form of a silicate very rich in that oxide into the molten cast iron as it lies in the thin boiling layer on the hearth of the reverberatory furnace. 2. In the Bessemer process by blowing cold atmospheric air through the molten cast iron in a deep clay-lined or dolomite-lined retort called a converter, the rapidity of the oxidation itself raising the temperature rapidly. And 3. In the open hearth process by exposing the molten cast iron in a thin and very broad layer on the bottom of the reverberatory furnace to an overlying layer of slag containing iron oxide, and usually enriched in that oxide by throwing into lumps of iron ore. In the last process, in addition to this purification of the cast iron by these oxidizing reactions, its impurities are in most cases also greatly diluted by adding much relatively pure steel scrap. If steel is cooled suddenly, it is thereby made harder and less ductile, or even extremely brittle, and it is said to be hardened. The degree to which it is thus hardened increases with the carbon content, so that whereas very low carbon steel is affected only very slightly, steel with 1% of carbon is made as hard and nearly as brittle as glass. The hardness and brittleness induced increase with the rapidity of cooling without limit, but they are apparently nearly independent of the temperature from which the sudden cooling begins. The tensile strength at first increases with the intensity of hardening, but reaches a maximum and then declines. In case of high-carbon steel, a moderate rapidity of cooling may give the highest tensile strength, but in the case of low-carbon steel, the tensile strength seems to increase with rapidity of cooling without limit. Hardened steel is tempered, that is, the hardening is mitigated or let down by slight reheating, say to 200 or 300 degrees, and the steel is annealed, that is, the hardening is completely removed by reheating farther, say to 600 degrees. After this reheating to 200 or 300 degrees, it is immaterial whether the steel is then cooled suddenly or slowly. The degree of tempering is the same in either case, and the same is substantially true of the higher heating to 600 degrees or annealing. All the best cutlery and tool steel is made by the crucible process, and indeed all for which any considerable excellence is claimed is supposed to be, though often incorrectly. But the great mass of the steel of commerce is made by the Bessemer and the open hearth process, the latter being generally considered the best, and rising from 9 to 53% in the United States, it reveals in a wonderfully true proportion the advance of progress. End of section 32, volume 2, by Francis Rolt-Wheeler. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org.